Hello. 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 Hello.
Hello.
Can you hear me? Professor,
Yes.
Professor Selvam.
Yes, sir. Good morning, sir.
Good morning. Good morning.
We
Very
are
good morning.
able we are able to hear you, sir.
I just wanted to check before that.
Okay, fine, sir.
Can you check the screen whether you are able to see the screen?
Yes, we
I
are
just
able to
shared
hear
the
you,
screen.
sir. We are able to see the screen. Your presentation, everything is perfect, sir.
Okay. All right. Thank you very much.
Okay, thank you, sir.
So just inform me before we start. Okay.
Sir, could you please stop the screen share so that?
Yes. Yeah. I do that. I do that. I just wanted to check that one. I just stop.
Yes, yes. Thank you, sir.
Yeah. Just 1 second. Okay.
स्टार्ट करू का सर? हे बोलायला हो फोन आला तर सर त्यांचा. A very hearty good morning, ladies and gentlemen. We are happy to welcome our honorable dignitaries, guest speakers, and the enthusiastic audience once again for this day two of the International Conference on Nanomaterials and Sustainable Applications 2020. Warm greetings to all of you. As we are about to begin, may I request you all to kindly mute your microphones. Thank you. And again, like yesterday, we'll be running the question and answer session at the end of every lecture. So for this, we will be enabling the chat option throughout every talk. So the audience has to post them directly to the session chair. So please keep this in mind. And again, an information for the chair as well as all the speakers that every talk is of 55 minutes duration. So 45 minutes is reserved for the talk, while 10 minutes is for the question and answer session. So it is kindly requested to all the speakers to keep the track of time. So thank you. So ladies and gentlemen, it is our privilege to have with us Professor Bhaskar Sathe from BAMU, Aurangabad, to formally begin and chair this session 4. So Dr. Sathe is currently working as an assistant professor in the Department of Chemistry, BAMU, Aurangabad, India. His research areas are focused in the fields of nanoscience and nanotechnology, inorganic materials chemistry, nanomaterials, fuel cells, batteries and supercapacitors, sensors, water splitting, and biomass conversion reactions, electrocatalysts in fuel cells and catalysts for organic transformations, tunable optical electrochemical field emission and solid liquid interfacial studies on nanoelectrodes. Dr. Bhaskar is serving as an honorary reviewer for research and reviews, Journal of Engineering and Technology and other reputed journals, and has authored several articles along with chapters in different books related to polymer and advanced materials. So may I now invite Professor Sathe to carry forward the session 4. So ladies and gentlemen, please lend your ears to and put your hands together for Professor Sathe. Over to you, sir. Thank you. Ladies and gentlemen, please bear with us for a very short while. Dr. Sathe will be joining uh, like in few minutes. Thank you. So, ladies and gentlemen, we have Professor Sathe with us. He has joined us. So, may I again welcome Professor Sathe once again and request him to carry forward the session 4. So, ladies and gentlemen, please lend your ears to and put your hands together for Professor Sathe. Over to you, sir. Thank you.
Hello, Dr. Sate, are you there? Hello.
Hello? Hello? Hello?
Hello.
Yeah.
Yeah. Please introduce the next speaker and can
Yeah.
you
Okay. Good morning, you all. And I'm here to introduce speaker for this session, Professor Selvam. Professor Selvam is currently professor in Department of Chemistry, Indian Institute of Technology, Madras. Head National Center for Catalysis Research, IIT Madras, Chennai. Visiting professor at School of Chemical Engineering and Analytical Science, MIT, UK. Prior to this, Professor Shalom was a faculty at Indian Institute of Technology, Bombay, and Tokyo University, Sydney, Japan. Professor Shalom obtained his PhD from Indian Institute of Technology, Madras. Before joining IIT Bombay as a faculty, he was a postdoctoral fellow in the Department of Condensed Matter Physics and Laboratory of X-ray Crystallography. Professor Selvan's research work mainly involves on the development of novel synthetic procedures for preparation of order nanoporous geolytic materials, including silicates, aluminosilicates, carbons, and a variety of transient metal oxides, as well as size and shape controlled nanomaterials. His research interests also include nanostructures material, heterogeneous catalysis for green chemical routes, environmental remediation processes, and energy conversion, that is biomass, solar, hydrogen, and storage where the methanol fuel cell, lithium ion batteries methods. Professor Selvan's major contribution also includes in the design and development of novel heterogeneous catalysis for a variety of industrially important organic transformations, which have received overwhelming response both in academia and industry. Several industrial consultancy and sponsored projects that he has brought to the institute has helped him to build a strong and vibrant catalysis research group at IIT Madras. Professor Selvam published over 300 original research papers, international peer-reviewed journals, and conference proceedings, and about 20 patents to his credit. Professor Selvam held several visiting adjunct faculty positions in various universities, institutes, both in India and abroad. He has also been bestowed with several national and international awards and honors. With this, welcome Professor Selvam for his talk. Title of the talk is Green Chemistry and Catalysis for Sustainability. Welcome, Selvam.
Thank you, Dr. Sate, for your kind words and the introduction. And at the outset, can you hear me now?
Yeah.
Yeah, at the outset, let me thank the organizer for giving me an opportunity to speak in this conference, and particularly Professor Manoj Gavandeso for accommodating my request in the last minute, and the committee members or ICT members. Thank you very much again. Today I'm going to just share the slides. The title of my talk is the Green Chemistry and Analysis for Sustainability. In particular, the conferences on nanomaterials. So I'm going to speak on nanoporous materials, because many people would have talked about the nanomaterials, the one which is the magic of what we call it as the revolutionized the chemical industry, the porous materials. nanoporous
Mr. Selvam, can I
materials,
interrupt? Hello.
namely the zeolite type materials. So
Professor Selvam.
I'm going to focus on some of those things. Before going to this one, maybe many of the young audience are there. So just
Hello.
give the
Professor Selvam.
genesis of this work
Hello.
and
Hello. Hello.
Hi, Dr. Sate. I think he has some internet problem. I think he will
Yeah,
join.
is some echo is coming.
Yes, yes. So once if he joins soon, just please inform him once again. This is the problem sometimes.
hello. Hello.
Hello, sir. We can hear you.
Can you hear me?
Yes, yes, we can hear you, sir.
Suddenly stopped. I'm not. Okay. Can I go ahead?
Professor Selvam, there is some echo in your
Yes.
voice. So
Again, same echo is coming.
Echo is coming now. Hello.
Hello. Yeah,
Echo
you
is
can.
coming.
Yeah, you can start now. Hello, Professor Selvam sir. Again, same problem. Hello, sir. Again, same problem is there. Either maybe echo problem or maybe internet connectivity is there. Connectivity issue is there.
I think please log off and log in again once again. Let's try this way.
Hello. Is it all right now?
Hello, Professor Selvam. Sir, if you could please log off and then log in again, then it might resolve a little bit. Hello.
Professor Selvam, we are not able to hear you. You are not audible.
Hello?
Yes, yes, we can hear you now.
Okay, fine. Just only 1 second. Hello? Hello, can you hear me now?
Yes, yes, we can hear you.
Okay, I'm sorry, I'm extremely sorry because of the recent cyclone, a lot of disturbances here.
Oh.
Because of that, I know. So, although I checked everything in the morning, but it worked. Suddenly it has happened. Okay, fine. I'll quickly rush through the presentation. Okay, the role of catalysis in the national economy. If you can see in the slide, about 24% of GDP. So, because we always talk about the GDP, you can see this one 24% of GDP from products made using catalysts, whether it is a food, fuels, clothes, polymers, drug, agrochemical, and so on. So that is the importance of the catalysis. Unfortunately, what happens, we do not give enough credit to the catalysis in this country. You can see this one, 90% of petrol refining, petrochemicals uses catalysts, and the chemical industry product, 90% of the processes and products, or even pollution control technologies, in particular the catalysis in the production of alternative fuels like natural gas, DME, hydrogen, fuel cell, biofuels, and so on, alternative sources. So everywhere catalysis plays an important role. What happens, this is a subject of say multidisciplinary. It's neither practiced in chemistry or chemical engineering, because conveniently we avoid that in the name of right, the other person will look into this one. That's how the catalysis is not practiced, particularly in India. Maybe very few centers or very few groups are out of their own interest they are following. Otherwise, there is no real policy on the catalysis. Before going to the catalysis, so the important thing is mathematics is important. That's how mathematics is mother of all sciences. We all know this one. Chemistry is the central science. Without chemistry, nothing happens. Why I'm showing this slide is chemistry. Even if you practice catalysis, chemistry is important, at most important. Without chemistry, nothing happens. If you know maths and chemistry, physics and biology is a consequence. So, and chemistry without catalysis, nothing, almost nothing. You can see in the 1948 in Journal of Education, Chemical Education, you can see this is, it has appeared. I just picked up from there. So chemistry without catalysis, almost nothing. So catalysis, whether it is a homogeneous, heterogeneous, or enzyme catalysis, or name any catalysis is important. Without any, all process are catalyst-driven process. So why we need to practice today's context? Why we need to practice this one, catalysis? Look at this slide. It's self-explanatory. We all know about it. We don't need to talk about it. You would have heard many places. Pollution, environmental issues. As a consequence, you are seeing many things are happening, right? You can see here, particularly in India, so we have, whether it's industry or your festivals or the agricultural products, we just unwantedly, we are throwing all the garbage to the environment. We all know that one. We all know how to stop it, but we don't want to do it. That's the only problem. Okay, so because each one of us, our own way of, in a country like us, this one, so we have freedom, too much of freedom. We can practice what we want, but we don't know. If you see the rest of the world, what they do, the same thing, we can see this one, okay, because all these are consequence. We see all these things, consequence of all these things, too much of population in the country, everywhere, whether it is this one, okay, automobile, or you can see anywhere. So people, a lot of people, we pollute the subcontinent. Subcontinent, we are the highest pollution race, contributors, right? Because the number game, it's simply the number game. Because of that, we are not able to do control anything. But of course, it can be practiced. Like, for example, all these things which we have shown these two slides. very well can be avoided with the catalytic process, because everything is originating from the catalyst. If you practice it properly, so we can do this. For example, one sector, organic synthesis. See, the catalyst in the past, by and large, the homogeneous catalyst used, and slowly it is changing to heterogeneous catalysis. But heterogeneous catalysis, the knowledge is not there because it's the solid state material. Mostly the heterogeneous catalysts are solid state materials. Not even the courses are taught in the Indian universities or institutes. Without the knowledge of the solid state materials, we cannot practice catalysis. How much ever you know your organic chemistry, how much ever you know inorganic chemistry, it's not going to fetch anything. So it's important to know that solid state chemistry and then solid state materials, and that is the leaders today. That is change this one. So to show this one, we will look at the slides. This is that's why the slogan has come today: the sustainability through catalysis. If at all you want to sustain catalysis, you have to practice, and you can see all the catalytic process. 85 the chemical process, 85% are catalytic process. Even in this catalytic process, over 80% are heterogeneous catalysts. So you can see this one, how many people practice heterogeneous catalysis in this country. How many centers are there? Just by practicing now, just homogeneous catalysis all through, it's not going to fetch anything in the years to come. The whole world has changed towards heterogeneous catalysis, and we have to move towards the heterogeneous catalysis. So in this context, you can see the porous materials revolutionized, not today, decades back, revolutionized the chemical industry, namely the zeolites, perfectly ordered porous system wherein we can get exclusive selectivity, whatever we want. One product, we get it one product. The other byproducts we can completely avoid. But the problem is the materials making is slightly complex process, but it's not all that complex. We don't focus our attention in this one because by and large, we are biased in this country so with organic chemistry and homogeneous catalysis because it's easy to practice and we carry on with that. But if you see this one, I'll show you one more slide where we understand why I said this is a revolutionized the chemical industry. Today you go any chemical industry, without zeolite, nothing happens. Zeolites used as a catalyst, support, separating materials or many other processes or just drying agent. So the knowledge of the porous material is important, but unfortunately we don't even have any of those knowledge. I mean, I'm sorry to say that one because it is the reality, because you can see this one, maybe you can see commercial because the organic chemists always buy the commercial catalyst and then do the reactions, or at the most they go to the organometallics or the coordination compounds. They don't go beyond. So that's why the integration is important. Chemistry cannot be compartmentalized, at least at the master's level. So we need to know everything and then we can move on. So that's why the concept came, green chemistry and catalysis. This is not new concept. We all know this one. Only thing is unless the legislation comes or some strict rule comes, we don't follow. Even in life, it is like that. The pollution, basically it is a pollution prevention. Don't create, make extra this one, okay? Or just for a want of money, so you don't dump everything onto the environment. This is what pollution prevention, we all know this one. Any chemical process, whatever the product you want, you target that one, you get only that over 90%, 95%. That is what all about green chemistry. Or if it is inevitable, remediate it. That is after the process, you can see to that how best we can get away with those unwanted products, unwanted things. Okay. So to practice this one, so we need to have the energy efficient technologies. Of course, the engineers will contribute on that. Utilize renewable raw materials because largely we use fossil fuels, and then okay, renewable materials are important. We need to focus on that. Even if it is expensive to start with, it is worth looking at those things and reduce or eliminate the use of hazardous chemicals. Whichever is unwanted, we don't use it. Even if it brings laurels to your individual or to the other ways also. So we should avoid all these things. That is where this one legislation comes or your policy comes, right? So opportunities for catalysis plenty. So basically what we do, catalyst minimize the byproduct and waste. This is what we are looking for. How do I reduce my byproduct or waste materials? So catalyst helps you. Particularly today, the heterogeneous catalysis are the leaders in this one. So with all these things, sustainability should be our goal. Yes, we need to sustainable. The future generation should enjoy whatever we are enjoying today, the comforts, life, everything, etc. So if you at all you want to sustain it, you need to practice green chemistry. That means, I said simple term, that is over 90% anything you put the product, that's good enough to say it's a greener process. And green chemistry is the main. And if you want to practice green chemistry, it is catalysis will help you. Catalysis is the key. Without catalysis, you cannot say green chemistry, right? So, as I said earlier, the porous materials revolution of the chemical industry, it is simply the perfectly ordered system. You can make the pores of the nanometer dimension. This is what is important. Today, we can make till 10 nanometer pores with the same 3.3 to 10 nanometer or 10 nanometer. We can make it porous. These are all basically naturally occurring aluminosilicates, zeolites. And then synthetic analogs, people have understood their chemistry, and then synthetic analogs developed, and they are ruling today the chemical industry, petrochemical industry, any industry for that matter, they are ruling that one. But unfortunately, neither the chemists or chemical engineers in our place don't practice any of those things. Even to give a course, it is with a great difficulty. We have to fight the system, because system is not allowing us to do at some point of time, right? So, but you see this wonderful material. These are all porous material. Same, you can make aluminosilicate dense material, aluminosilicate porous material. The porous materials are prepared the templating techniques. Template the potter, like the potter makes the pot with using a mold or template like that. So we need to make the template, but the templates are in general organic molecules, quaternary ammonium salts, surfactants, ionic lipids, and so on. So you need to have the knowledge of the organic chemistry knowledge here. That knowledge we don't spend properly utilize it, but we only think of only new molecules. All through our think of new molecules. But it's how to, even if you make a new molecules, how to make it in the large scale. That is where the problem comes. Large scale scaling up. That is where the chemical engineering comes into the picture, and we all look into the various processes. So to show the importance of zeolites, this is a standard textbook example. You can see this one. Typically, the organic chemistry used aluminum chloride to this particular reaction, and of course, this is, you can see this one, the homogeneous process. The disadvantage of homogeneous process, you can see this one, for every 4 kg of your product, you get about 4.5 kg of aqueous effluent. That is the problem. Disposal is the problem, number one. Number two, you use the solvent, and then also you use aluminum chloride and so on. Whereas if you use the zeolite, heterogeneous catalyst, number one, it's a recyclable, it is biocompatible, and so on. Nothing will happen because it's simply an aluminosilicate, number one. Number two, you get over 95% of the yield of your product, and then you can see the waste, the aqueous effluent which is generated, it's almost negligible amount. In the chemical engineering terms, it is 3 unit operations, whereas the homogeneous catalytic process 12 unit operations. So that is where it's important to look at this one. So heterogeneous catalysis is the key. As I said earlier, catalysis is the key. Heterogeneous catalysis is the key. If at all you want to have sustainable processes. The next example, green caprolactam process. This is also very well known textbook example. You can see this one. The use of the TS1 is nothing but silicate, titanium containing silicate, silicalite, what we call a silicalite. It's a zeolitic structure. And then this is a pure silicalite structure, and which gives you this, atom efficiency of 75%, the byproduct being only water. Whereas the commercial process, conventional process, it was working even operation with the 29% efficiency, and with the E factor, which is nothing but the generation of waste, about 4.5 kgs of waste per 1 kg of the product. So you can look at this one, the homogeneous process and the heterogeneous process. This is very clear why we have to move towards heterogeneous catalysis, why I said it is a revolutionary chemical industry. Likewise, we can show many examples. The quinones, important intermediates. This is, you can see this one, the process worked on with 1 kg of the product to 10 kg of your waste product. It was working. Classical process, industry was working. Later, with one or less, and then with this one, zeolitic based catalyst, completely eliminated all this process. The plant operates in Italy or many other places now, this kind of restaurant. Okay. So to make it much more clear, you can see this one, the zeolite, which is nothing but the famous ZSM file, which is the Mobile Corporation, which developed the aluminum silicate, and which is the pore size. The pore size is around 5 angstrom or 5.5 angstrom. Okay. So take, for example, alkylation of toluene. We all know this one, it will give you the orthometa para product, byproduct, the xylenes, right? Orthometa para xylenes. You can see the chemical industry operated with 30, because para-xylene is important for your PET production. So even with 34% efficient selectivity, the chemical industry was operating with HCl and aluminum chloride. But when the zeolite came, you can see there's a ZSM5 zeolite. It's exclusively we can tune it to the 96.7. Over 95% I was telling it's this one. So this is a wonderful process. That's why it is revolutionized the chemical industry. You can see this in the same process. It can happen in the pores. The reaction happens in the pore. All three, orthometa, para, you can see. But what happens by virtue of the geometry inside, it allows only the para product out, number one. Number two, it is acid catalyst. So the ortho and meta is isomerized to this one. So this is a dual functional catalyst. So this is one typical textbook example why zeolites are superior to any other catalyst. So likewise, the silicates, aluminum silicates, people have developed aluminum phosphates. The aluminum phosphates, ion containing aluminum phosphates, you can see this one, we can generate different kinds of pores, 7.3 angstrom and 5.4 angstrom. And the pore geometry is important for controlling the products, whether it is adipic acid or cyclohexanol, we can see this one, we can control it by pore size engineering. We may call it as a pore size engineering. You can tune these pores, dimensionality of the pores, we can tune that one, right? And zeolites, not only that catalysis, it can also separation process, wonderful. You can see this by pore geometry, we can separate the molecules, desired molecules we can get, and then the others can be trapped. This is again, chemical engineers would like to have such kind of materials, simple this one, separation materials. Okay. So going to this, all this importance of catalysis, you can see this one, even the conferences are making the titles, exotic titles like the catalysis making the world a better place. It is not this one, it is even the discussion meeting with the top four, the UK scientists like the Graham Aching, Richard Catlow, Chris Odecker, and Matthew Davidson. The general, like us, the Center for Catalysis, they have a catalysis hub in the US, in the UK. So they practice catalysis and then they popularize catalysis because of the importance of the chemical industry and so on. Even you can see one of the recent international zeolite conference. See the title, zeolites make tomorrow better. So realize the importance of zeolites or zeolite type materials in the chemical industry, and then picking up a lot of interest worldwide. Okay, that is one aspect of it. Second is alternative approaches. What are the alternative approaches? Because as I said, it's a fossil fuels we are using for our majority of our energy sources, or the economy is driven by the fossil fuels. Basically the oil, and you can see the other one is biomass. The biomass largely ignored in this country because this bio means, okay, we all give only healthcare. Due credit to all these things, whatever we have undergoing now, but biomass, spent lots and lots of money, but only for healthcare, because biomass, see, it's a complex molecule. You need to understand the chemistry, because if you don't understand the chemistry, you cannot break it. Basically, we have to break this one. One route we all know, very well known, the fermentation route, but the other routes, there are many other routes. For example, pyrolysis, controlled pyrolysis. You get mixed organics, and that forms a biomass platform molecules. That's why I said in one of the earlier slides, the agricultural waste, we simply burn. We don't know what to do. Or we know some few groups we know what to do, but the whole of the country, we still do this one. But the rest of the world, they make fuels and chemicals using that one. So what is important is the knowledge is important. We are not spreading the knowledge. We are not inculcating the knowledge to the younger generation to go into this one. We always preach only the organic chemistry fetches you the job. People go only in that direction, but these directions are important if at all you want to do this one alternative process. The renewable source, we have plenty, because as I said, shown earlier, the plenty of population, we plenty of waste we generate, the waste we can use it, utilize it in a better purpose, but we don't do that one. So biomass sources, this is a, again, textbook example, or everywhere people show this one, whether green or brown or whatever it is, unwanted biomass sources, we can make into fuels and chemicals. It's quite possible using the catalyst. You can see one simple example you can hear in this slide, renewable fuels and chemicals. Right, you can see this one, how the greens are turned into the crudes, dirty crude, billions of years. Now today we take that crude and then also we can get into the fuels. C1 chemistry, methane, for example, methanol, ethanol, we can make it from the dirty crudes. The same thing we can practice it. For example, if I take this agricultural waste, it took so much of year, but in less than a year, it can be converted into a bio oil. So you can make a bio oil. Once you have this oil, which is equal to the bio crude, and we can get whatever we got from the crude oil, whatever we are getting today from the crude oil, we can get all those things. So this is what, okay, we can do the pyrolysis oil, we can do liquid upgrading or gasification, we can do many things the way similar to the crude. But the knowledge is not there. The knowledge is not there. We don't take any risk to go into this direction. But one of the issues with this bio oil, you can see large amount of oxygen contents, unlike the crude oil. Crude oil contents, because it's that show there is a difference always, 1 year process and billions of year process. You can see the bio oil content large amount of oxygen. So we need to remove chemistry. If you know your chemistry, we can do this one, deoxygenation, nothing like that. It's a deoxygenation. If we can know how to do the deoxygenation, then wonderful, we can have that one. So you can see here, the same thing we can do a deoxygenation. We can get using a catalyst, zeolite-based catalyst, aromatics. If I want, I can get only aromatics. Today we can get the bio oil with all kinds of this one. We can remove that one. Over 95% we can remove the oxygen, and then we get aromatics, or we can tune with alumina catalyst to hydrocarbon. This is what we want. Either aromatics or hydrocarbons, we can tune it. This is the knowledge of the materials, the solid state materials. If you know that, you don't know that, we cannot practice it. We can only practice it, okay, whatever is available, take that and do that. That's what we are doing it. Okay, the other example, not only that, we can also do many other things. See, for example, the biomass. If you know your chemistry, your organic chemistry, well, you can practice it, because biomass are much complex molecules. That is where your organic chemistry knowledge is important, where to break, how to break the molecules. So lignocellulose biomass, we can get into use. This is a enzymatic process where we get the xylose, the small 2, 3, or 4, 5, we can get small fragments, we can get, but catalytically we can do this one. Today we can do that one, catalytically we can do that one. So for that we need to know the knowledge of your catalyst, and then which catalyst. You have to make your own catalyst. If you look for all the time commercial catalyst, then you're not going to be the leader. So the enzyme, we can say, for example, the porous materials, because you can take large porous material. To start with, I can immobilize the enzymes and then, okay, recycle that one a number of times, and then we can get the process. The xylem, we can get the xylems with the numbers, what X2 to X6, we can get it, and then these are important, prebiotic, right? So not only that, we can also valorize. There are plenty of opportunity in biomolecules, but unfortunately, all our efforts are going only in the healthcare, because of course, healthcare gives a lot of money and then a lot of immediate results. But if you want to really look at this work and the environmental energy issues, we need to look into this all aspects. This one, lignin, cellulose, the same. And then we can make fuels and chemicals. I can valorize using the catalyst. Again, you need to know you look at this one, organic chemistry is still, it's important. Without that, nothing we can do, right? Sorry, just okay. So we can valorize biomass, and for example, okay, so any kind of waste, you can see that any kind of waste today can be converted into beautiful way, the chemicals and fuels. It's all known, very well established. Only thing is, what is not established is the catalyst, the heterogeneous catalyst. That is what the multinational companies are trying, and then they are always support some of these ventures, right? Sorry. So not only that, biomass, we all know this one, biomass can be another way we can convert trans-esterification, again chemistry, the chemistry knowledge we can do the biodiesel, and the large amount of glycerol is coming byproducts. If I valorize the glycerol into value-added chemicals, then it's wonderful, but you need to have a catalytic conversion. The catalyst is required. You can make acrolein because it's important. We can say this is a bioacrolein, biopropendiols, bioglyceric acid. We can make that one from renewable resources. Plenty of opportunity. Again, the catalyst, the heterogeneous catalysts are required. To show one or two examples from our own examples, to show this one how we have done, we have developed copper-based zinc oxide nanomaterials and supported on a porous alumina. And you can see this one, the hydrogenolysis reaction. The hydrogenolysis reactions we have done with the propendiols, glycerol to propendiols. Even after 140 hours, you get wonderful good conversion and selectivity using this catalyst. Okay, so another example, dehydration. Dehydration, as I showed you earlier, this aluminas or the silicas, we can do that one, and acrolein selectivity. You can see the acrolein selectivity. You can see if I use a silica, it is not giving after few cycles, activity goes back, whereas alumina, it goes quite good. So again, this catalyst is important. The development of process chemistry is known. If I talk to any organic chemist, they say, oh, still you are doing the same chemistry. It is not all about it. It is all about how to scale it up, how to take it to the next level. This is what's important. Then you can see the third example, selective oxidation of glycerol. You can do the glycerol into glyceric acid using the nanomaterials. The gold in this case on activated carbon or the porous carbon which we make it, which is robust catalyst. So there are many ways. What is important is, again, I'm trying to say this catalysts are important. Catalytic process is important. But the reactions are all very well known. No new reactions needed. All the know what is the chemicals we require, and accordingly we can always target it. So next to move on to the next, this one is there are other issues, global issues, plastics and PETs. You can see this one, production capacity, millions of tons, or almost it will go billions, right? So you can see this in the contributor, the Asian country, you can see this one, 50% of coming from Asia. So we are having a lot of problems to disposal of this one, or plastic degradation of plastics, or making plastics into chemicals and fuels again. So again, if we want to do that one, again, you need the catalyst. Catalyst is important. Today only heterogeneous catalysis. So you need to practice heterogeneous catalysis. The knowledge is, see, plenty of opportunity. The knowledge is not there. And then even I can say this one, okay, last 10-15 years, we are not able to get a good faculty members in catalysis because the industry attracts immediately. They take away all our, that means we are not producing enough. That's what we are not producing enough catalyst chemistry. So recycling polymeric waste, it's an important issue. You can see that India itself, we generate 50 million ton per year waste, right? So all this, the plastics is about 1.5 million or 2 million tons. So what we do is waste is dumped in landfills or incinerated and so on, many other issues. But you have the wonderful way of converting into chemicals and fuels. But we don't make any attempt in that one. Very few people do it here and there something. But there should be a focus. The biomass, there should be a focus. This plastic, there should be a focus. And chemical industry, there should be a focus. Otherwise, we cannot move forward. The other one is, if you say at some point of time, we say plastic is bad, and then okay, we ban everything, and today everything is open. You come to Chennai, everything is open. Whatever is banned yesterday, today is open, everything, right? But there is no need to do this one. If you do the biodegradable plastics, again, it comes into the biodegradable plastics, we can do this one, what we call polyhydroxy alkanates. You can see these molecules. You have to make this molecule, but it's difficult, not easy. But no, so we don't even make any attempt on this one to make this wonderful plastic product. The same thing you can do, it's biodegradable. Biodegradable, you can see this one. Today, all these multinationals, they get all those, whether you like it or not, say all this liquids, the water, even take a simple water. So they use it because it's convenient. Life is like that. Now we cannot curtail anything, but that's what happened here. Some point of time banned, and today everything is open. So we cannot sustain it. Sustainability is okay. Allow everything in a better way, in a better world. So okay, we have to live in a better world, and then to live in a better world, catalysis is important. Without catalysis, nothing happens. So the knowledge of catalysis is most important. These are all very well known. All molecules known how to transfer it. What is most important? Whatever is written above the arrows, but we don't even give any importance to all those things, right? Then this one, pharmaceuticals. Today, everybody takes without medicine, we cannot live. It has come to a situation. You can see all these things, all of you, maybe one of these things you may be using it day-to-day basis. Large amounts of waste pollutants produced all goes into the stream, because when you take it, it is only certain percentage absorbs, the rest comes out. And all these things are in the stream, and it is the biggest problem to aquatic plants or other issues. So pharmaceuticals and personal care products, you don't need to tell anything about it. You go to any market, any supermarket, or any even simple the health personal care products, people use it, but all these are containing some of this dangerous, because we wash away after that, it goes into the stream, whatever. So contaminated everything, we need to do this one. So we can do it photocatalytically. We can develop, again, catalysis is important. We need to do this photocatalysis. Okay. Photocatalysis, and then we can see this one here, titanium-based materials are important. Here we have developed a titanium-based porous material. Titanium is okay, even it's all decade-old subject, titanium. But today what is important is titanium can be made very many forms. That is where the materials science or material chemistry plays an important role. You can make spheres, you can make rods, you can make particles, you can make tubes, you can make perfectly ordered systems. All these things you have to make it, and then you can see here the same pharmaceutical, typically the famotidine drug. We have just shown that how it can be degraded, and then this is an HPLC showing that completely removed. Of course, the byproducts are there that can also be removed simultaneously, right? So catalysis plays an important role in every, whatever, whether it's a polymer, bio, or the pharmaceutical, and so on. So photocatalysis, the dream reaction, solar hydrogen. You can split water, the same titanium, we can use it, water, or the flow chemistry, whatever, the integrating bio, solar refineries and effective. So these are all, again, we have to come together. The chemists and chemical engineers come together, work together, and then develop the process, right? So we have plenty of the changing scenario. That's why today we, as I said earlier, fossil fuels largely we use for all our gas, oil, coal, but particularly the oil we use large extent. And then today the future, you have to move away from oil, and then coal and natural gas, you have to exploit it as an alternative fuel, as a raw material. It's difficult to work. It's not nothing easy, because even oil, people have worked a century, right? And then only we get everything today. Likewise, coal and natural gas, plenty is available. We have to work on this one. Then other alternatives, CO2, C1 chemistry. Now, earlier we broke all this large complex molecules into smaller molecules. Now today we have C1, one carbon atom. So we have to make into the polymeric, this one, the reverse, whether we can do. And biomass, as I said earlier, biomass is there, and then waste is there. All those things, new materials for us to look into those things. Plenty of opportunities, the biomass, CO2, and so on. And then in addition to this one, the solar energy, we have to use solar energy in an efficient way. Wherever the photocatalysis, photoelectric catalysis, and so on, we can do this one to have a sustainable chemical and chemical engineering industries. So keeping in that mind, our group focuses on new materials. That's why we work on new materials, particularly porous materials, nanoporous materials. And then if you work in nanomaterials, shape and size control materials, if you work on those things, then the energy conversion process or energy storage and all consequence. If I have this one, this is the key. If you have the knowledge in this one, anything you can practice it and take it to the next level. So that's why we largely focus on those things. Basically, they work on the genetic materials. Name anything like, for example, carbon, silica, alumina, titanium. In my student days, these are all taught as a amorphous material. Today, we make a crystalline material, porous material with high surface area. So that's the beauty of those things. And metal oxides can also be similarly, we can do that one. We can combine all those things. And of course, nanomaterials, we can use it for all kinds of energy conversion, energy storage, and green chemistry and catalysis process. We can do all those things if you know this part of it. This first two is most important. Just a few examples. I'm going to show you that one. Ordered mesoporous materials. Look at this one. Perfectly ordered system. You can see this one schematic is on a one-dimensional force system or interconnected force, two or three-dimensional force system or interconnected small and large force. We can make it at the nanometer scale. You can see all these things in a nanometer scale. This is a TEM image, and then you can see parallel direction and perpendicular direction. We can see this one beautiful, the pore structure. In that inside the molecules, the reaction takes place inside the pore, and that's why we control the selectivity beautifully, wonderfully. We can control those things. So making this material now, these are all made exotic surfactants or kind of this one. That is a limiting factor. So we can move on to this one. To some other, again, if you have an organic chemistry knowledge is there, okay, templating molecules, you can see this. You need a head group, and then you can make, this is an ionic liquid, we can make it this one, again, the porous material. With the ionic liquid, you get even much better than the surfactant, the CTAB or any other, the surfactants, you can get much better materials. Quality of the material relatively cheaper, we can design and get the materials. Not only that, today we can make even the micropore. This is a mesopore material, and the micropore material area I have shown the GSM5. We can also make hierarchical structure. You can see this micro and meso combination. We can make it, and then now this okay. The reaction can happen in the micropore, and then the mesopore can act as the kinetics. It can improve the kinetics or other aspects. So what we call hierarchical zeolites. Micro and mesopore combination, not the size. It is the pore size. It's important here. So you can see this one. This is today. It is possible. You can see this one. This is the grossly. If you see the mesopore 3.1 nanometer. If you can see closely in this one, you can see in the small this one micropore and mesopore coexist. Even this one, we can do a tomography and then see this one. Really, the pores are there. And then in addition to that, we can look at the absorption studies like the BET. So you can see the micropore and the mesopore. You can see these two different pores and they coexisting on the same structure. So we can have wonderful materials. We can also make nanozeolite, what we call a nanozeolite. That is also another, that is a nanoporous, and this is the porous zeolite. Even it make it smaller and smaller particles where we can generate the micro, meso, macro combinations. We can generate all those things. All right, we can see this one. We can have the product, whatever we want, the ortho product, we can increase. Sometimes it's difficult to get this ortho the products. We can also make zeolites, zeolite with this one. Okay, the non-templated techniques. The non-templated techniques are, because the templates are expensive, we can have beautiful. Because what is important, uniform. The particle size is important. We can make this one, the zeolites, and then perfectly, one of the LTL structure, we could make it, and then the industry wanted without, because template is expensive. We can also do very many other things, like for example, we can functionalize it. Sulfonic acid, typically the organic chemists use silica sulfuric acid for the strong acid, but now because we have to throw it away, but if you functionalize it on a silica matrix, the sulfonic acid, wonderfully we can functionalize it. And then again, the chemistry knowledge is important. Without the chemistry knowledge, we cannot do all those things. The chemistry knowledge helps us to do this one, and then okay, make it you can completely replace the silica sulfuric acid by the sulfonic acid, functionalized silica material, right? And which is important. For example, here one of the pharmaceutical intermediate product, the glucose acetonation, this one, the 1,2 monoacetone. Even today, it is diacetone is you can get it easily. 1,2 monoacetone is today. Even today, it's enzymatic process. The industry wanted to move away from enzymatic process. You can see the silica sulfuric acid with the controlled acidity. We can get into this one. Both this one. Okay, you can get this diacetone and monoacetone. So it's a good 50-50 we get. So we can demonstrate how it is important, the catalyst. Okay, we are successful by making the functionalization. We can also functionalize some of the visible light photocatalysts, like for example, uranyl, molybdenal, vanadiol, all these are absorbs light in the visible region. Wonderfully, we can functionalize it, and then so you can see this, and it absorbs after functionalization, it absorbs light in the visible region, and then it does wonderfully well the photocatalyst compared to the conventional, the photocatalyst TiO2. It gives you much faster and then a complete oxidation of the unwanted, the volatile organic compounds. So we can demonstrate, keep demonstrating it, the many other things. So I have shown the aluminosilicates, silicates, aluminophosphates, and then they can be used as a template to make this ordered carbons. Wonderful. the perfectly ordered carbons. The same template is the silicate template. You can take it and then use the carbon-rich source, polymerize, carbonize. See, you see, there's a lot of chemistry is involved. The chemistry knowledge is utmost important. Without that one, you cannot do it. You form an organic-inorganic hybrid, remove your inorganic, and then get, sorry, organic, and then you get your, this one, okay, beautifully organic, sorry, here inorganic templates. You remove your inorganic, you get beautiful organic ordered mesoporous carbons. You can make this carbon. Carbon is a versatile material. Many places you can use it. You can see this one, how we made it. This is your template, silicate, and then you made organic and inorganic composite and removed your template, and then parallel direction, perpendicular direction, you can see honeycomb structure. So you get beautiful, the mesoporous carbon, and then these are the evidences, either the absorption evidence to show this one, it is in the mesoporous 4 nanometer pore size. We can get the this one.
Professor Selvam, 5 minutes are you?
Yeah, yes, I'll finish it. Thank you. So, as I said, carbon is a versatile material. So the porous material we can do gas absorption studies. That one, okay, we can do a gas. We can use it as a support material. We can also use a gas absorption studies. For example, this one, hydrogen absorption or the CO2 absorption, we can make it. And since we are making the porous material, so there is other. See, simultaneously we have to look into this one. This okay, this one MOFs. People are a lot of the inorganic chemists keep working on this MOF, metal organic polymers. We are interested in this geolytic type framework because similar framework structure, it can be used to absorb hydrogen and or any gas molecules. Similar things we can also do. Keep open. The next one is, as I said earlier, the titania is an important one. We can make the mesoporous. We can see this one. This is the first example of the mesoporous structure. You can see, like your silicates, aluminum silicates, you can get the large pore structure or the mesopore structure, perfectly ordered system, and then you can get. So we use the photocatalytic degradation famotidine, and then you can see this one wonderfully. It degrades all this famotidine compared to your conventional catalyst. So not only that, okay, any effluent, we can treat it. This, for example, the phenols, one of the important, this one, it's difficult to degrade it, but we can degrade it photocatalytically using this titania, the high surface area titania or porous titania, we can use this one. And more importantly, catalytic reduction of CO2 into chemicals and fuels. Carbon 1 chemistry, as I was talking about the carbon 1 chemistry, you can make the fuels and chemicals using this photocatalyst. You can see this on all the commercial catalysts. Compared to the commercial catalyst, our newly developed catalyst shows 1 order of magnitude higher than the this activity higher than this or any of the commercial. So this is by virtue of the defects and the high surface area we create in those materials. All right. We can even make the colored materials. Titania is very well known. It's a white pigment. Today we can make the blue, black, or whatever the color you want. Make it by chemistry, the chemistry knowledge. You can see the titania starting material. You can make all these colors, wonderful colors, inorganic pigments. You can use as inorganic pigments, or they are also as a wonderful catalyst. So there are many other possibilities exist. So once we establish this procedure, we have done many other materials. Like for example, we did the iron oxide. We made the ceria zirconia oxides, all porous oxides, and then even lithium-ion battery, the olivine structure we could make it. And then, so everywhere you make the porous material wonderfully reduce the activity. Likewise, the nanomaterials also perfectly ordered. You can see the same size and shape. You can make it, put it inside the pore of this. You can use this one. You can use the catalyst, electrocatalyst, the current density. You can the fuel cell. You can see this in commercial catalyst contains 40%, whereas our developed catalyst 10% platinum is good enough, so that you get the equivalent activity or double the activity of that one. So this is just to demonstrate how we can use this porous material. If I introduce a nitrogen functionality, the density is even increasing more, kind of this one. So all this chemistry we can practice it. And what is more important is you have to make the large pore materials, the porous materials, and then perfectly the size and shape control material introduced into the pores, and then that's a robust. It will not leach out, it will not come out of this one. So you can recycle it. You can see this in the particle sizes about 4 nanometers, and then you make a 5 nanometer pore size and then introduce inside, and then you can get one last example to show this one. Glycerol, how this is important. The gold supported and activated carbon. You can see this is the first cycle, it gives you good activity, and the recycled one completely drastically goes down. Whereas in the porous structure, the same gold is introduced in the porous structure, And then even after recycling it, you get the same activity. So that means it's intact. Whereas here, particle is agglomerated. You can see the next slide. This is the before the reaction, after the reaction of the activated carbon, much larger particle size because it agglomerates. Whereas in the porous structure, you can see this one, the pore, it is introduced inside, and then before reaction, after reaction, it retains the same particle size. It's simple, but only thing is to make it this one. That is what's important. How do I go make the uniform particle size and the pore structure introduced inside? That's a challenge. Okay. So to sum it up, so we work mostly on the porous materials, on geolytic type materials, to some extent MOF, wherever the gas absorption is important. Make silicates, aluminosilicates, carbons, any transition metal oxide or any metal oxide for that matter, we can make it. And then we also make the size and shape control nanomaterials. And more importantly, our target is smaller, much smaller particles, 1 to 2 nanometers, because that is the most where we can look at the atomic level resolution. We can see this and where we want, what is the surface, because catalysis is a surface driven process. I need a particular surface to generate that one. Nanomaterials are the best because we try to mimic the enzymes, which is the less than 2 nanometer, which is important to stabilize certain structure, particularly in this case, the icosahedron. If you see the icosahedron structure, which is the most of the virus or the enzymes possess that kind of structure. So that's why they're most active, because all three connected, we have the facets are open, and the facets you can make whatever they say, whether you want a 111, 100, 110, you can make it depending on what kind of a geometry you want. This is a target today. So we can see this one. Even here, we can make it the atomic level resolution of the particle. You can the scale, about 5 nanometer scale. This is a 2 nanometer. This is a 1 nanometer particle size. In that one, you can see that very closely how the atoms are arranged in the crystal lattice. Wonderfully, we are targeting on some of those things. So finally, I would like to thank all those contributors. This is not simply this one. I just collected the data from all my students who worked very hard. Some of them, even we have the overseas visitors, and many universities support our activity. Many of the funding agencies, both national and international funding agencies, industries, and of course, Professor B. Viswanathan is instrumental in establishing the center. Without that, we would not have got all the facilities. And I would like to thank some of the hosts of the universities like Manchester, Cardiff, Tohoku universities. All through last 15 years, they were supporting me unconditionally. So finally, I would like to thank you, all of you, and the organizer in particular, the Manoj Gawande, for giving me the last minute change. Thank you very much.
Hello. Excellent presentation by Professor Selva.
Yes.
1 or 2 quick question, please, from audience.
Yeah, so I would like to ask a question.
Okay.
Yes.
Professor Selvam, I was looking the slide, the paper you published in Chemistry Select. I think sulfonic acid supported on silica. So it is a protic acid, right?
Yeah.
So what do you think
Yeah.
that, like, first thing I would like to ask whether the reaction is really performed in heterogeneous medium, and if the catalyst is really reusable after the first cycle or not?
Yes, we are. You can see this on the first run, second run. We have done it.
Okay, so there is no leaching of H plus or nothing, right?
No leaching. This is a chem, so it is not leaching. That's why it is appeared as a cover page on that journal.
Okay, that's great. Yeah, thank you. I think I missed that slide. Yeah, thank you.
Yes, please. Yeah.
Thank you so much. Yeah.
Any more?
Sir, can I ask one question?
Yeah.
Hello?
Please go ahead.
Sir, am I audible? Sir, I would like to ask regarding
Yes.
furanic compounds obtained from biomass.
Yes.
Most of the furanic compounds are facing difficulty regarding separation. Could you please help me?
That is where the problem, no? That is where the problem, no? So we see separation is the problem. So we have to work on that. And no, it's not readily available. See, what we look always readily available solution. Of course, readily available solution, we get good, quick results, and then publish it, we perish. That is what we say in this country. But it is, we have to look for that one. See, we struggle now, even for separating products, we struggle it. But it takes time. That's why we have to spend time. But a ready solution is not available in any of these end solutions. Most of it.
Thank you.
Okay.
Thank you, sir.
Sir, I have one question.
Yes.
Sir, I'm Subhakan Das from Odisha. Sir, I'm working in the field of fly ash to develop geolite. Sir, my question is, can you use geolite? Can you use geolite for gas absorption?
Well, yes, I told you, no, the gas separation, gas activation, everywhere you can use it. You need to know the right zeolite, which kind of zeolite you want, whether you want the alumina silicate, silicates or carbons or metal oxides, you have to choose that one. Zeolitic structure is wonderful. You can do this one, but you need to know which is your active site and then whether I can have the active site in my zeolite. That is what the prerequisite.
Okay.
Good.
Thank you.
Okay, there are no more questions. Join me to thank Professor Selvam for his wonderful talk. Thank you.
Yeah, thank you very much. Have a wonderful day.
Yeah, thank you, Dr. Sate, for chairing these sessions. My special thanks to Professor Selvam for delivering very informative lecture on basic chemistry and sustainable catalysis. We all that it is very important to bridge the gap between homogeneous catalysis as well as in heterogeneous catalysis. And I think nanomaterials or single atom or sub nanoparticles are the best choice or best substitute to replace them. So it was great to hear of zeolite, its selective catalytic applications, porous materials, biomass, and valorization of various processes. So thank you very much once again for your talk on catalysis for sustainability. Thank you so much.
Now moving on to the next two lectures by Professor Srivastav and Professor Jayaram. It is our honor to have with us Dr. Anand Kapadi from ICT Mumbai to chair this session 4 and take it further. May I now invite Dr. So Dr. Anand Kapadi was born in Mumbai. Dr. Anand Kapadi was born in Mumbai, Maharashtra in 1980 and studied chemistry at the University of Mumbai and York University under Dr. Ian Fairlamb. He completed his PhD in 2008 under the supervision of Dr. Fairlamb at York University before starting his postdoctoral work in the research group of Professor Lutz Ackermann at the George August University, Göttingen as an Alexander von Humboldt Fellow. He returned to India in 2010 and was appointed as DST SERC Fast Track Fellow 2011 and DST Inspire Faculty 2012 at the Institute of Chemical Technology before taking up UGC FRP Assistant Professor position in 2014. The unifying theme of his research program is the development of synthetically efficient processes using novel metallocycles. So may I now invite Dr. Kapadi to carry forward the session 4. So ladies and gentlemen, please lend your ears to and put your hands together for Dr. Kapadi. Over to you, sir. Thank you.
Anand, you are.
Am I audible?
Yes.
Yeah. So good morning, everyone. It's my pleasure to be the chairperson of this second session. The morning session, we have already seen a fantastic lecture by Professor Selvam about how heterogeneous catalysis is very important, not just from the academic point of view, even from the industry point of view. And in the second session as well, we have two very good, researchers, very good speakers. And we are starting off with the first one. He is Professor Rajendra Srivastav. He's from IIT Ropar, and he joined the Department of Chemistry IIT Ropar as an assistant professor. And he headed the department from March 2015 to 2018. He's currently working as an associate professor there. Professor Srivastav completed his PhD from CSI National Chemical Laboratories, Pune, 2005, and then he moved on to KAIST, South Korea, as a postdoctoral fellow from 2005 to 2007. He also received a very prestigious JSPS fellowship and was working as a postdoctoral fellow in Hokkaido University from 2007 to 2009. He has worked extensively in the area of physical chemistry and has received several awards, such as the NACI Scopus Young Scientist Award in 2017, the Catalysis Society of India Young Scientist Award in 2018, and Mid-Career Faculty Research and Innovation Award 2019 by IIT Roper. His field of interest includes the design and synthesis of nanostructured functional materials for catalytic applications, including photocatalysis and electrocatalysis. He has till now published 140 publications in peer-reviewed journals and has been also granted 8 patents. Recently, Stanford University has enlisted the top 2% scientists of the world, and India was also represented there. So it's a privilege to tell you all that Professor Srivastav was ranked 5th in the discipline of physical chemistry in India, and he also holds the 242nd rank in the world for his work, which has been done over the last several years. So I would like to now hand over the dais to, or should I say this is a virtual dais, to Professor Srivastav and give his talk on the title, Designing the Heterogeneous Catalyst by Introducing the Porosity and Implanting Active Sites. Just to let you know, Professor Srivastav, so as already mentioned, that we'll be having a 55-minute talk. So overall, it's 45 minutes of talk, and then we'll have around 10 minutes for discussion. The dais is now over to you. So,
yeah. Hello. Good morning to all. So,
good morning.
Yeah. So first, let me share my screen. So are you able to see my screen?
not yet. Yep.
It has come? Yes.
Yes, yes.
Okay. Thank you, Chair, for the nice introduction. And it is my privilege, and I thank organizers, especially Professor Manoj, for the invitation. I will start my presentation that Professor Selvam and Professor G.D. Yadav and other eminent professors are already set the platform for this particular conference, and they have talked all about the sustainable chemistry and especially the heterogeneous catalysis. So in today, I am going to talk on designing the sustainable heterogeneous catalyst by introducing the porosity and implanting the active site. So this is the talk title I kept it, and then I will move forward. Maybe I can put the full screen if it is. Yeah, it's fine now.
Yes, we can.
Yeah. So actually, I will start with the our atmosphere. So we have troposphere, in which we have large amount of reactive and non-reactive gases, and these gases, and actually you can see your lithosphere and biosphere is actually made up of these gases. So these because of the natural process, these gases have converted and formed the lithospheres and the biospheres. And a lot of enzymatic process is known to convert these reactive and non-reactive gases, and that is why we have here fossil fuel and biomass. They are the source of energy, foods, and so on. And we are also having a large amount of minerals and metals present on the earth. So you know that whenever you are trying to convert a non-reactive or reactive gases to a chemical or fuel, you require an energy. So the energy, and you required a catalyst. So the energy and catalyst is very much important in this particular aspect. So the energy, because you know that any chemical reaction is required a making our bond or breaking our bond, you require energy. And what the role of the catalyst is to bring down that energy barrier. But you require certain energy, and that energy can be given through different form. Either you can give the thermal energy, or you can give energy in the form of solar energy, and you can also give in terms of the electrical energy. So all these processes can be accomplished using a different kind of source of energy, and that is why heterogeneous catalysts can be classified in traditional catalyst, that is conventional catalyst, photocatalysis, and electrocatalyst. And in all the cases, you need a special kind of designing a catalyst, because you need a catalyst, you need the active phase to catalyze this reaction. In case of conventional catalyst, you have redox reaction, you can have acid-base reaction, so accordingly you need to design the catalyst. In case of photocatalyst, you need to have additional advantages, that you should have the light absorption capacity, otherwise it cannot work under the solar radiation. And in the case of electrocatalysis, you need conductivity, then the electron transfer can take place. And in all these processes, you required a suitable kind of a catalyst. And the catalyst designing is a very important aspect, as Professor Selvam kept on emphasizing on it, that designing a catalyst, especially the porous catalyst, is very, very important. So when we think about the development of any industrial catalyst, there are certain important aspects one need to look into it. That it should be easily synthesized, and it should be easily scalable and reproducible, because you need a catalyst in the large scale. And if it is not reproducible to the same textural property and chemical property, you will not going to achieve the similar activity over a period of different scale and different time. You also need to have economical precursor. So one has to think about, rather than taking platinum and palladium as a catalyst, you need to think about very small precursor, simple precursor, and economical precursor. Tricer metal-based catalyst is important. And it's very important that when you have developed a catalyst, it should not exhibit any deactivation phenomena, but definitely we all know that all the catalysts exhibit deactivation phenomena. What our aim is to reduce it and minimize it as much as we minimize it. And in that process, again, porous catalyst plays a very important role, as Professor Selvam already illustrated in the first talk. And then these heterogeneous catalysts should be recoverable and recyclable. Most often we say that it is recoverable and recyclable, but in some case what happened, it requires regeneration also. So it should be easily recoverable, recyclable, and regeneration in the case it is required. And very important thing that what we work on the lab scale, where we work on the small scale synthesis, where we directly use catalyst in the powder form. But when it goes to the industrial scale, one has to prepare the pellet form, or the form is required. And during that process, or it has to go through the stream of the fluid as well as the gas stream. It has to be retain its porosity, retain its activity. That process. So once you make a catalyst porous and make it pellet, after making the pellet, its activity and reactivity and the porosity should not change much. That's what is a challenge in the development of the industrial catalyst. And when we think about the catalyst, when we talk about the redox reaction, one should have the metal oxide and or supported catalyst. That redox activity can be inculcated by the ion exchange process. So if your material is having the ion exchange capability like zeolites or clay, one can incorporate the implant the metal ion of the required types. You can do impregnation. There are several methods of impregnations are there. You need to think about that which kind of impregnation method is best suited for my application, because it depends upon the porosity. It depends upon you want your metal should be on the surface or it should go inside the pore. All these things is defined by the method of impregnation, so play a very important role. Sometimes we required that our metal complex should be functionalized. Okay, so you can do different kind of functionalization. Either you can anchor it, or you can tether it, or you can graft it. So it depends on the requirement. You have to choose a suitable kind of functionalization method. And in some cases, your metal complex get agglomerate. That is why activity is less. But once if it is caged in a porous matrix, then activity can be enhanced. And of course, the leaching behavior, everything can be reduced. So what happened in that process, sip in bottle synthesis is very, very important. So these are our very various methods by which one can prepare the catalyst. Now, as I said in my talk, that porosity plays a very important role. So for a student, you can think that when you have a flat support, you don't have any porosity in that. Then you have some sort of surface area. But when you have porosity, then you have additional external surface area present in the material. So that will give better surface area. And moreover, you have its selectivity because of the pores. So you can introduce your active site inside the pore, and you can do the catalysis inside the pore. So that is what one has to think about, how to design the catalyst and how to inculcate the active sites inside the pore. So we can have different type of shape selective catalysis, which can be based on either reactant selectivity or product selectivity or the transition state selectivity. So these are the various selectivity can be achieved once you are working with porous material, especially the zeolites. So in today's talk, I'm going to discuss on 4 different kind of material: metal oxide, zeolites, MOF, and carbon nitrides. All these are very fantastic material, and they can be used for conventional catalysis, electrocatalysis, and photocatalysis. So I am going to discuss on all these 4 materials. But as I said, that porosity need to be introduced. But how to introduce the porosity? So in case of zeolite, since it is the microporous in nature, you require a small template. So that is why small cationic template or amine-based templates are used for the synthesis of the zeolite. But once you think about the mesopores generation, so in the case of mesopore generation, you require the bulky structure dating agent. So long chain structure dating agents are highly successful in this case. So we have 3 different variety of structure dating agent. They are cationic, anionic, and non-ionic. And they form these porous material by electrostatic force of attraction or by the hydrogen bonding. So that is what, these are some of the examples, some of the very, very illustrated example I have just put it here, which is widely known for this generation of the mesopores materials. And what happened when you put these mesopores, this material, long chain material, what happened when you put into the synthesis domain, then they form the micelle structure. So they can form different micelle structure. And these micelle structure can further aggregate to a liquid crystals. So liquid crystals are those crystals, it depends upon the critical micellar concentration. It also depending upon the packing parameter. So what happened when you have large excess of this your structure dating agent, long chain structure dating agent, they assembles and they try to generate a different kind of structure, mesophase within the crystal domain. They act as a template. That is why it is called as the liquid template. So these are, for example, MCM41, which is the mesoporous silica 41, which was synthesized in 1992, was actually based on this liquid crystal template mechanism. So we also have and we can tune this different mesophase depending upon the packing parameter, and you can change the packing parameter. What you can see here, that packing parameter can be easily changed by changing the volume and by changing the head group area of the surfactant. So that's what you can tune the packing parameter, and you can change from one mesophase to other phase depending upon the evolution of the structure during the synthesis. So as I said, that actually the mesoporous material was started using the development of these kind of structure dating agent, and they started prepare different kind of mesoporous silica because in the petrochemical industry they required a mesoporous material, and that is what that has given the momentum to the birth of these kind of different materials. For example, MCM family material, which is based on cationic structure dating agent, SBA15 material is based on non-ionic structure dating agent, which is based on actually the hydrogen bonding based mechanism for the synthesis of mesoporous silica. And FSM60, actually you have the your clay, which you can delaminate and then you assemble in the presence of structure dating agent to get the FSM60 like material. KID6 is another interesting material in which your mesophase is changing from one structure to other structure in the presence of co-solvent. That is what your butanol, and that's what you get a different cubic architecture. So so that is what you can design a porous material of different type, different crystallographical structure, and all those things one can design. But it is very important, and it is very difficult to leave the zeolites, because the success of zeolite I have presented in the different form. You can see that the initial applications of the zeolite was actually limited to the petrochemical industry, but they are extending to all domain. So it is used for the gas separation and purification. It is used in bioimplant. It used in the water purification, used in medicine. It used in several sectors. Whatever the sector you think of, these zeolites can play a very important role. And that is the region you can see that more than 200 zeolite framework structure is synthesized and more than 40 are naturally occurring. So that itself shows the success story of zeolite. So we have done a lot work on the zeolite, but today I'm not going to much discuss on the zeolite because my aim is to show how the activity can be tuned in the different class of materials. So, but in case of the catalysis, mostly in the petrochemical and fine chemical industry, GSM-5 and beta rule the industrial market. So as Professor Selvam also said that we have also started working on the mesoporous zeolite, hierarchical zeolite, nanocrystalline zeolite, all these zeolites we have started working on. And we, for every synthesis, especially for the mesopore director, you need a different kind of a structure directing agent. And they are actually made from the fossil fuel. Because all these mesopore director is a carbon-based material, you require, they are actually sourced from the fossil fuel. So the sustainable synthesis strategy is very, very important. So how to make the sustainable synthesis? The one which approach that don't use template, but when you don't use template, definitely you are not going to get always the ordered material, especially when we think about the porosity, especially what the zeolite is lacking, it has microporous, very well defined microporous, but it doesn't have the mesopores. So that is why from 2000 onward, people started making of microporous, mesoporous hierarchical or nanocrystalline zeolites by using different kind of structure directing agent. But it is very important if you have the tri-level porosity. Tri-level porosity means if you have micro, meso, and macro. And macro should not be very large. It should be in the range of 50 to 200 nanometer. So that will further enhance the diffusion. And when you think about making this kind of material, so you would always think that I will use a polymer. So polymer as a macropore directing agent. People have done a lot to synthesize macroporous material using the polymer as a structure directing agent. So what we thought that we worked on the biomass, especially even we worked on the pollen grains to synthesize zeolites. But here I am just presenting that how we use the starch and the cellulose as a source of the template for the synthesis of zeolite. What we did, we first make the silica particle and then we coated starch onto it. And then when the starch coated silica was used into the synthesis domain of zeolite, then what happened? It requires 21 days for the synthesis. Very large time was there without starch. But when we added starch, the synthesis took place in just 6 days. And when we add propyl triethoxysilane into the reaction medium, which retard the growth of the zeolite. So we have, you can see that we have both micropore, mesopore, and macropore. And macropore is in the range of 50 to 200 nanometer, 150 nanometer or so. So we have the material having the tri-level porosity, micro, meso, and macro, and which exhibit very good activity. And we are now working on more towards the synthesis of the zeolites in the sustainable methods. Now, that is the story of the zeolite. You know all that zeolites are mostly, if you think about zeolite, always it's all aluminosilicates. So in order to introduce a active sites in the zeolites, one has to think that you are using silica and alumina. Their hydrolysis rates are very much matching with each other, and that is why they are forming the silica alumino framework structure. But once you add any metal other than silica and alumina, any other metal source, they are different. Their hydrolysis rate has to match with the silica hydrolysis rate, otherwise they will not participate into the framework formation. So we use propyl triethoxysilane as a structure, as a nanocrystalline agent, because it's reduced the growth of the zeolite, and we prepare the titanosilicate and zirconosilicate. That's what we prepared the nanocrystalline. Even we use the hierarchical structure directing agent to prepare the hierarchical zeolite. What is important of this work is that people have said that titanium zeolite is very good for aminolysis reactions. So their activity was very good. But what we have found that after incorporation of the zirconium, the activity has increased multifold. And that is actually because of the epoxide can be more polarized through the zirconium when compared to the titanium because of the electropositive difference. And you can have the selective product depending upon the amines and the adsorption of the epoxide on the surface. So we have done the competitive adsorption, we have done the adsorption of the amine and epoxide separately, and show that how you can get a selective product under a particular condition. So that was the important of this particular work. So in this work, I just wanted to say that we have porosity as well as the active sites in planting. That's both are important factors. And then generally people think that zeolite cannot be used in the electrocatalysis, but we have shown in a number of occasions that zeolites are very good material in terms of electrocatalysis as well. So of course it doesn't have that conductivity as the carbon-based material has, but our aim was to use this zeolite in the methanol oxidation. What is how you can do methanol oxidation, especially in the alkaline medium? So what is the role of zeolite? What is the role of cerium oxide? So cerium oxide can make cerium oxide, cerium hydroxide species. And that, what is the role of zeolite? Because zeolite can provide large surface area. When you heat with cerium oxide, it make a very strong connection between the zeolite as well as the cerium. And then since the zeolites have the Bronsted acidity, so it will absorb the methanol. So now you have the adsorbed species methanol onto the surface, you have the cerium hydroxide, and that helps the dehydrogenation process, and you get very good activity for the methanol oxidation. So that is used in the methanol fuel cell. And in fact, we improved our activity by tailoring, by making the zeolites also active. So first what we did, we take the ZSM5 mesoporous nanocrystalline ZSM5, and what we did, we ion exchange that zeolite by the nickel and copper, and we optimize under which condition we get the best activity. So now we made our support also active, and then we incorporated the active phase in the form of spinel, and that spinel, you can see that it's retained its activity after 1000 cycle, 99% activity. And under the similar condition, the commercial catalyst, that is the platinum carbon catalyst, exhibit retardation activity up to 25.3%. So that is what the achievement which we get in this case. And we have worked a lot on the methanol oxidation. We kept on understanding how and what kind of metal oxide should be suitable for this particular reaction. So that's, I just wanted to show the importance of the zeolite in electrocatalysis. And as Professor Selvam also says that one can prepare the mesoporous metal oxide, because metal oxide preparation using the soft template is not so easy. Always it goes through different transition state, and generally structure collapse once you calcine it. So hard template strategy is always better. So hard template strategy is that rather than taking soft template, which are much more tunable in nature, you have to take a fixed template that for which the structure is already fixed. So what you can do, you can infiltrate your metal precursor so that it can go inside the pores, and then you carbonize it, and then you etch out the silica by the sodium hydroxide or HF, and you will get the metal oxide. And one can get a wide range of metal oxide of the same geometry, same structure as you have started with the mesoporous silica. So that's possible. So, but the limitation of this strategy is, number one, that you have to synthesize in the low scale, because you are taking, let's say, 1 gram of zeolite and 1 gram of Sp15, and it's you can only put some amount of 0.1 ml of your solvent into that, because the mesopores are like that only. So that is why you will be preparing very low amount of the material. So that will be very good for lab scale catalysis, but not be very for industrial scale catalysis. So what we develop a 1 scale direct synthesis strategy in which we prepare the similar kind of mesophase by putting the organizing the structure in the form of polymer. So what we did, we took the fluoroglycerol, we added the formaldehyde, and then metal precursor in the presence of F127. So they form a polymeric structure. You can say that it forms a resin-like structure, in that the metal is entrapped into it. We carbonize it and then calcine it. And we got a very similar porosity. For example, for cerium oxide, we got around 150, zirconium 150, aluminum oxide, yttrium oxide, many different oxide we have prepared by this strategy, and one can prepare in large scale. So this is the advantage of this 1-step direct synthesis strategy. So now I have shown how you can make the material by soft template as well as the hard template. Now I am coming, someone has asked in the previous talk, is that what is the role of zeolite in terms of gas absorption? Yes, zeolite has, definitely they can be used as a gas separation, but its sites are having limited, because you don't have any chemical interaction. You have only silica and alumina. So any gas having this kind of chemical interaction only can be used for the zeolite, but not all. So that is why the initially metal organic framework have been developed, because metal organic framework, you have an organic building framework unit and you have a metal. You can tune your metal and you can prepare a large number of metal organic framework. And that is why these materials are very good for the gas adsorption. So these materials are good for gas adsorption, but they are not very good in terms of catalysis, because they don't, because most of the metal sites are occupied or bonded with the organic linker. But still, one can introduce the active site by direct modification or by post-synthesis modification. So either you take the functional ligand and then react with metal, you can get the functionalized MOF in the direct modification method, or you prepare the MOF. Generally, MOFs are prepared in the solvent, because solvent are also entrapped into the MOF structure as the coordination site onto the metal. You can remove that particular sites, degas it, and then you can post-synthesis modify your functional site. And for some time, you also can functionalize your aromatic ring also by this process. So you can have versatility into the post-synthesis method. But it is very difficult to prepare mesoporous MOF. So what we tried to prepare the mesoporous MOF. We took the dicationic structure dieting agent, as you can see here, and we tried to prepare mesoporous MOF. And what we did, you can see here that this is the pore size distribution of this particular MOF, which is synthesized with dicationic structure dieting agent. And we also added the tetramethyl benzene as a pore expander. And but in all the cases, if you see that this is the isotherm without adding structure dieting agent, it is only microporous in nature. But once you added this structure dieting agent, mesopore director, you have this kind of a porosity generation, which you can see from the pore size distribution. And it was found that the CO2 adsorption was better when you have this mesoporous development. And moreover, these were found good in catalysis, especially if you see that for the large molecular synthesis, large molecular oxidation, this copper BTC MOF was less active as compared to this. And this activity difference you can observe much more in detail when you do the recycling. So recycling, this formed the deactivation behavior, but this doesn't deactivate much. So that is what retention in activity is observed. This is because of the mesoporous generation. So how is the mesopores form? Actually, you have the dicationic, they form the lamellar surfactant phase, and then you have the coordination polymer formed by the BTC and copper BTC. They form the electrostatic interaction between these two layers. By this, you can see that these are the very weak electrostatic interaction, and one can remove this structure dieting agent just by treating with ethanol after the synthesis. So one can remove it. But again, I would like to mention that it's not as stable as zeolite. MOF was very good material, but it's not as stable as zeolite. But how to improve the stability? So what we did, we tried to grow MOF onto the surface of the zeolite by chemical. First we functionalize some ligand, and then we try that MOF should grow on that. We prepared zirconium containing MOF, and we found them is very good for biomass conversion. I'm not going to discuss. I just want to hear in this particular slide, I just wanted to say that when you make the MOF zeolite composition, you get a very stable material. In fact, I can say that even amine functionalization plays very important role in terms of stability. So what we found that even the MOF, zirconium MOF synthesized on the surface of beta was leaching or framework collapse is observed in case of biomass conversion, but when we have the amine containing group, it was not found. So depending upon the kind of group present into the MOF structure, stability also improves. So that we have done through NanoMaterials from this one. So what is that in this particular work? What I just want to say that beta is a very good material, especially for fine chemical synthesis. So, but in chemical industry, when the beta is used, they need to remove this extra framework aluminum. So you are losing the extra framework aluminum. I thought that why can't we use that extra framework aluminum to grow MOF? So what we did, we take the beta, we added the MOF source, and we grown the MOF onto the structure of on the surface of beta, and we so that by solid state NMR that your de-elimination has taken place and the MOF has grown onto the surface from the solid state NMR. And even ammonia TPD provide such indirect evidence for this growth. So as I said, that MOF is very important and very good, especially in the gas, but its application is limited because of its instability to the reaction medium when we do the Hartz catalysis. But MOF-derived materials can be very unique. That is why MOF-derived materials are now playing very important role in catalysis, especially in electrocatalysis and photocatalysis, because there you don't need a large amount of material as you can add in case of conventional catalysis. So because what happened when you synthesize MOF and then you carbonize them, then you have a highly porous metal oxide, and such activity will be very good. Such kind of a porous metal oxide having large surface area, you will not be achieving by any other method. And we also have a kind of a support with the carbon. So that kind of a materials provide very unique activity. In fact, you can achieve the activity which you can get with platinum, palladium and platinum. So what we did, we prepared the MOF and then we carbonize and in the nitrogen atmosphere and in the nitrogen oxygen atmosphere, and we got the copper oxide, CuCu2O. And then in other case, when we did some amount of oxygen, we got the selectively CuO based material. So now, and they were used in the Sonogosera reaction. Generally, they are generally used in the palladium-based coupling reaction. But we have shown here that how the copper-based catalyst is used in the catalysis, especially the palladium-based catalyst. So here, both phase playing very important role. For example, if you see that copper nanoparticle is less active, copper BTC itself is less active, means parent MOF is not at all active, but Cu2O is very good, means it's good active, copper oxide is not at all active. So what we have the mixture of Cu and Cu2O. When we prepared Cu-Cu2 mixture, its activity was enhanced, but when we prepared this onto through the MOF, it has the carbon. So you can see the previous case, you can see that this is a structure of the MOF. You can see that it has the porous structure and it is the metal oxide actually. So you have the carbon, inside the carbon you have the porous carbon Cu-Cu2 phase, and that is what you get the better surface area and the better activity. Not only for this, it can be generalized for coupling reaction. For example, Ullmann amination, you can also do for A3 coupling reaction. This is for Cu-Cu2O. In all the cases, you can see that it exhibited the better activity as compared to the starting Cu-Cu2. But for the copper oxide CuO, what we have shown in terms of oxidation of this benzylic compound, dibenzyl, that diphenyl, and you can see that diphenyl methane oxidation takes place in presence of oxygen, where NH pi is the just radical initiator, and that has been used, and you can get very good activity. Even if you see the copper oxide is less active and copper CuCu2O is almost more than double active in this case. So that is what we have demonstrated, that how when you prepare the MOF derive this metal oxide, they are, and if you go through the literature, many people are working on MOF derived material, especially in the electrocatalysis, because you required less material there, and there they are using for the electrocatalytic application. So another, motivated by the previous work, because what we have shown is that copper plays a very important role. So can we do the selective catalysis? So again, implanting a suitable active site is becoming very important. And you know that hydrogen production, hydrogen and carbon monoxide, both are actually generated from the, you can see that steam reforming and the process. Okay, so the production of hydrogen leading a lot of CO2 gas into the atmosphere. So can we use certain biomass derived reducing agent? So formic acid can be derived from the biomass, and that can be used as a reducing as well as formulating agent. So that's what our aim was. So use as a formic acid as a reducing agent as well as the formalizing agent. So what we prepare carbon nitride containing material, in which actually what we have done, we take the colloidal silica, in which and then we have grown the nitrogen containing carbon by the polymerization of the orthopolyene having the melamine in it, and then we use the cobalt and then carbonize into the inert atmosphere, and then we get the cobalt. So cobalt is entrapped. It is actually present in the zero oxidation state. It mostly in the zero oxidation state, which we confirm from the XPS. And you also have some amount of cobalt nitrogen, cobalt oxygen bond you can see from the XPS. So that shows that cobalt is highly stable and is stable. Otherwise, cobalt generally leach out if you put into the normal activated carbon or anything. And what we shown that under a particular condition, especially in the water medium, you can get selective hydrogenation of this quinoline, especially this quinoline ring. So only you can get the hydrogenation under the water condition. If you see the catalyst, we have seen a large amount of catalyst. Only the cobalt containing catalyst was good, especially when you carbonize, or when you heat the material in atmosphere, nitrogen atmosphere at 800 degrees centigrade. Okay, then only it's very good, because otherwise your surface area is low, it has graphitic nature, we have all proved all those things, and that exhibit very good activity and selectivity. But please note that this is underwater condition. So what happened underwater condition, you get decarboxylation taking place. That is why you get the H2 and CO2 from the formic acid. And this support plays very important role, because it's basic in nature. So what happened, this support absorbs the quinoline, and it also absorbs the formic acid, because formic acid is acidic and support is basic. So it's absorbed both formic acid in presence of water, it's selectively giving H2 plus CO2, and this H2 in dissociating to H and H, which is transfer hydrogenation taking place, which on the adsorb this quinoline molecule, and that is what this selectively THQ is obtained. And it's not only for THQ, a wide range of this compound we have investigated, and you can see that its aromatic ring is intact, but only those ring which is having the heterocyclic nitrogen content, they are selectively reduced. Now we can also do the formulation under the different condition using the same. So now here we have the generation of both H2 and CO. So what happened here, dehydration is also taking place in case of toluene. So you have, when you have dehydration, you also get the carbon monoxide. So you have both H2 and carbon monoxide. When it's present both in the reaction mixture, then you can get the reductive formulation product. So that is what we got in the reductive formulation product when you use the same catalyst in the toluene. So just by changing the reaction medium, you get the two different selective products. So that is the so it means that solvents, reaction mediums, type of catalyst is very important role. So that can be achieved, porosity, all these things plays very important role, and it can be versatile in nature. We have shown for a wide variety of substrate for this particular end formulation and reductive end formulation. So this is all about kind of material. Now I am coming to the third material, which is graphitic carbon nitride. And graphitic carbon nitride as such doesn't have very large surface area. And what happened, you need to take any kind of carbon and nitrogen source and heat it in presence of in the kind of a closed vessel, you get the carbon nitride. The advantage of this material is that this material has very good visible light absorption capacity. Moreover, it also, if you see that this particular figure, you have different kind of nitrogen containing sites. So these different kind of nitrogen containing sites plays very important role in case of, especially when you talk about certain molecule which are acidic in nature. Okay, so you can do the base catalyzed reaction using this. It also has the absorption capacity, light absorption, very good light absorption capacity, especially in the visible light. And which kind of nitrogen will be there, it depends upon how the growth is taking place. So if you have trimer, tetramer, actually may not be visible to you, but if you follow this of our recent article, you can see that just how the growth is taking place, the directional growth will lead into different kind of the nitrogen species present in the matrix, and that governs the catalytic activity. And you can make this material porous in nature by using the hard temperature strategy. One can make measy porous C3N4 also. In fact, what we tried when we started this C3N4 was we didn't have very good photocatalysis system with us. So we started with very simple. We tried to investigate and explore its activity in the conventional catalysis. So you know that it has the base, so it can activate the acidic molecules. So CO2 can be activated. So what we wanted to use the CO2 activation by this, but we have worked a lot on the CO2 activation, but the main important of this work was that how to activate the CO2 in absence of any co-catalyst. That was very important. And especially this, what we did, we treat this carbon nitride with a sulfuric acid. Under a certain sulfuric acid condition, we get a very good amount of SO3 functional group, and that's what that we confirm from this, what is that, your C3N pyridine IR, your XPS. And you can also confirm from the FTIR that SO3 group has been introduced. And ammonia TPD and the CO2 TPD has shown that it has the better active material and the better acidic material. So when we did this reaction for the CO2 activation, especially for cyclic carbonate synthesis. So the accomplishment of this particular study was that we did the reaction in the neat condition. Generally, you required a solvent, a mild condition, and most importantly, large scale synthesis. So we generally did this reaction in the large scale and solventless condition and without any co-catalyst. So this is actually possible because we have the SO3H and H2 group. NH2 group can activate the carbon dioxide, and epoxide can activate simultaneously the SO3H can activate the epoxide, and simultaneous activation of these two leads to the higher activity of this particular catalyst. Okay. Now, as I said that when we started this work, we had very limited resources of the photocatalysis. So we started with 250 watt mercury lamp, and we did the initial investigation on the photocatalysis. We started with very simple reaction, that is benzyl alcohol oxidation and amine oxidation. But the aim was to understand how this is actually happening. What is the reaction mechanism? So what we made the heterojunction material, because CCN4 has very good activity very efficient in terms of visible light absorption, but is not active because hole and charge recombination takes place here. So unlike you require another criteria that hole and electron which is getting separated, it should not be recombined very fast. So in order to minimize this recombination behavior, one has to make the heterojunction with a suitable metal oxide. So we made the BiBO4, and then you can see that photocurrent was improved. It means the charge separation has been improved. This is also from the photoluminescence. We saw that this is the parent CCN4. It has more electron and hole recombination, but when we have made the heterojunction, the electron hole recombination was minimized. It has better charge transfer mechanism happening here, there. And the main important thing that we showed how the three different pathway of the mechanism. So what we say that there can be OH cleavage pathway, CH cleavage pathway, and whatever the H2O2 is generated during the reaction, that itself can catalyze this oxidation reaction. So all these three we have developed, we have done a lot of scavenger study, for example, electron scavenging, hole scavenging, superoxide scavenging, and the OH dot scavenging. All this scavenging study led us to give this kind of a mechanistic study. So mechanistic investigation we have done, that was the main importance of this work. And then we know that this hydroxylation can be very easily done by Fenton reagent. So iron-based catalyst is very good. Similarly, we can also do with vanadium-based catalyst. So what we wanted to make a comparison between the thermal catalysis versus photocatalysis. So that is what our aim. So we prepare iron vanadate. Why we chose an iron vanadate? Because it has the active sites, can do hydroxylation reaction. Why we made the composition with CCN4? Because it has very good light absorption capacity. So when we made the heterojunction and we investigated these reactions under conventional light, and I will just skip this slide. In this slide, we can just show that when we have made the heterojunction, it's got very good electron holes already separated, and you can see that the visible light absorption capacity of this particular material. And photocurrent measurement shows that it has the 330 and to 70% composition has the better photocurrent measurement. And what we observe that the OH dot radical generation. So that we have monitored in situ by fluorescence, and what we obtain that OH dot radical is generating with time, and it gets saturated after 4 hours and so on. And if you see that in the dark, you do not have OH dot generation. In thermal catalysis, you get some amount of OH dot generation, but in case of photocatalysis, we have more OH dot generation. And that is the reason we get the more activity in the photocatalysis. If you see here, benzene to phenol, very important reaction. You can see that in normal catalyst, iron vanadate is 25.6, but this Fe3A7 is 30. So improvement in activity, you get phenol in higher selectivity. You get some amount of benzoquinone in case of thermal catalysis, but in case of visible light, you get more of benzoquinone. And that shows that hydrogen oxide efficiency, H2O2 efficiency is more in case of visible light. Similarly, when we did from phenol, you get the benzoquinone. From this, we both give phenol and catechol. Every case we get directly benzoquinone. In all the cases, in comparison to thermal catalysis, photocatalysis gave the better H2O2 efficiency. Not only this, we also did for naphthalene and anthracene, and all those cases we get very good activity under the thermal condition. So this is how we have the generation of this species, peroxide species, from the UV visual spectra, and then a species is converting to MO dot, that is taking away the hydrogen proton from this aromatic ring, and then you get the phenol. And that is what you can do the hydroxylation reaction. But this catalyst was also very good for the alkyl oxidation, CH activation. You can see that for toluene, generally toluene activation is not easy. So if you see that thermal catalysis, you got maximum 10% benzaldehyde only.
So you asked the last 5 minutes.
Okay, fine. So in case of you can get 37%. So that is what one can achieve, the better catalytic activity in terms of photocatalysis. So I think I will not discuss this particular part. I will just go on to the biomass conversion, because that is very important to discuss on this platform. But what we also did, because if you remember that I have shown that how in the methanol oxidation we have generated the CO2. So the CO2 can be converted to methanol back by photocatalysis using CTN4. So I'm not going to discuss much. I am just leaving. If someone is interested, they can go through this recent generation. We just made little alteration into the catalyst. We introduced carbon, extra carbon and oxygen into the this thing. That was very good for the CO2 to methanol conversion. And we also did using the same catalyst H2O2 production. So H2, so you can we use electron and hole very efficiently to oxidize water, and we get the H2O2. And that is also very important in terms of the industrial process, generation of H2O2. Now, since only 5 minutes is left for me, so I will take this 5 minutes into the biomass conversion. So biomass conversion, Professor, many other forum, everybody has told, but biomass conversion is required a very suitable catalyst. If you don't develop a suitable catalyst, because there are large number of functional groups are there, and you required one kind of functional group transformation very selectively. So it required an optimum acidity, optimum basicity, optimum activity, and that can be achieved by modulating the surface, by modulating the activity. So here what just I wanted to show that this particular, I will not go into detail due to the time limitation. What I can say that glucose to fructose isomerization takes place using the beta and tin base catalyst. It is also known to catalyze by base. So what we developed the magnesium containing the MTW, gerasone 12 catalyst, and that is having both acidity and basicity. We have demonstrated by the FTIR and ammonia TPD. Under one condition, we got very good yield for the glucose. You can see that we got the glucose 35% conversion. It's not less. Generally, people have report from 20 to 30. It's very good. It has both added advantages of acidity and basicity. Moreover, under the higher condition, higher activity, we got the methyl lactate. So lower temperature, we got selectively the higher temperature, we got the methyl lactate. Of course, we get large amount of other side product, which we monitored by HPLC, but we got more of methyl lactate. And selectively, one more interesting thing is that we took isopropanol as a reactant to generate in situ acetone, and that reacted with the furfural to give you FAC as a selective product. If you take directly acetone, it can lead you to directly Fa2C. So that is what we used both acid-base functionality in the material that give the transfer hydrogenation, and that transfer hydrogenation is leading to the FOL in one case, and that FOL is important. So in one condition, in another condition, it gives the aldol condensation product to give the FAC in the selective. So that's how you can get the selective catalysis with that. Another important thing what we did, generally for FAL to FOL means reduction, you require a kind of a palladium copper chromide catalyst. This is widely known. But what we use a very simple zirconium phosphate, especially amorphous zirconium phosphate. When we did the crystalline, has more acidity, but it's not found good active. But amorphous, having moderate acidity plays very important tool to get a very good selectivity for this HMF and DFF to the selective FOL. Means selective, you are doing carbonyl to CH2OH group. And another, I will not go in detail because of time limitation. I will just say that how the support plays very important role. See, what we have developed, we wanted to select, because if you take furfuryl alcohol, you can get large number of reduced product. So how can we get selectively a reduced product? For example, in this case, how can we can selectively reduce the CO to CH2OH, and how can you selectively reduce both CO as well as this aromatic? So we can achieve these two things under different reaction condition. Again, you can see that solvent plays very important role, and support also plays very important role. So of palladium supported on CuF4, we got selectively FOL. But in case of nickel, because nickel can absorb furanic ring through nickel, and that is why we got that selectively this connection. So that is what we get the selective products. And the last last 1 or 2 minutes, so I have shown the importance of the furanic compound, which is developed from which is derived from the cellulosic part, but we also have the lignin part. So the lignin part can be converted to aromatic kind of compound, aromatic fuel. So that can be achieved by the hydrogenalysis reaction, because you have benzyl phenyl ether, you have diphenyl ether, you have very, very different kind of these linkages present in the lignin compound. We have taken the model compound, but the activity is very difficult to cleave this bond because they have different energy and very difficult to cleave this bond, especially when you have the palladium into the zero state, and it should strongly absorb, optimally absorb onto support. And what we obtain, what we observe, in not only with the our catalytic activity data, but also to the computational study data, that how the benzene phenyl ether is selectively absorbed with having a high adsorption energy on the MOF surface when compared to the parent cerium oxide. And that is how it is the reactant is absorbing modulate strongly, whereas the phenol, which is product, which is traveling more strongly on the cerium oxide surface, that's we have done from the computational study. And that is what the product was low in case of palladium supported on cerium oxide when compared to palladium supported on cerium MOF. So with this, I just want to conclude by saying that key template is very much required to introduce a well-defined porosity. And in order to catalyze a particular kind of reaction, you require a suitable active sites. You need to think about, you need to design a catalyst, what kind of reaction you are interested in. So accordingly, you need to design a catalyst, and you should also have a suitable porosity so that it can achieve required activity, whatever you want to achieve. And if you want to work on the visible light absorption capacity, one should have the additional feature in the catalytic material that it should have the visual light absorption capacity. If you are working on the electrocatalysis, one should have the one should have the good electronic conductivity. And all these things has to be designed depending upon the pointed application. So one has to think about that, what Professor Selvam kept on saying, that organic chemist plays a very important role, and they just think that heterogeneous catalysis people don't just they take material, do they some organic transformation. It's not like that. One has to properly think, and one has to properly think about the reaction. We have 3 roles to place in case of conventional organic chemists. What they do the chemical reaction, they get the product, and then they try to, based on the identifying of the intermediate and product, they try to propose the mechanism. But what our case is that how the activity is retained, how the activity is really imparting to the particular reaction. So we need to have very strong structure activity relationship in place. So that's case become very, very crucial for all of us. So that is why designing the catalyst, studying the structure activity relationship, and then proposing the mechanism based on the structure activity relationship is the key parameters in completing the whole job. And that's all is very important. And all these catalysts can be scalable and can be industrially viable if it is not deactivating.
Can you please conclude?
Yes. So thank you very much. So this is my group. My old student and the present student, these are the funding agency. I thank all of them, and this whatever the work I have presented is all because of them. And this is just I just tell them, and they did a very excellent job, and I thank all of them, and I thank all the funding agency. And I thank you all for your kind patience. Thank you very much.
Thank you very much, Professor Srivastava. It was a very elaborate and well-described talk about how heterogeneous catalysis again can play a role. I agree with you when you're suggesting that you need to understand, as maybe organometallic chemists, organic chemists, or whoever is to appreciate the fact that heterogeneous catalysis requires a lot of understanding of the surface, the type of functionalities which are involved in catalysis. And that's why development of these materials is not that easy. Even the characterization is very, very different. So thank you very much for giving a lot of insight into not just your research, but even generally heterogeneous catalysis. I think we have a few minutes to take some questions. Harsha Kastwal has one question. I'll just read it. So zeolites like Z5H beta and mesoporous materials are being extensively studied for catalytic pyrolysis, but they are too expensive in terms of industrial scale operation. Is synthesis through starch-coated silica cost-effective or scalable?
Yes. So yes, when we think about the cost factor in terms of, first I will take up the question that what she said, that the zeolites are not cost effective. Please think that we are investing a money just to synthesize zeolite at the first stage. So you use a structured dielectric agent, you are using a silica precursor which are very cheap, alumina precursor which are very cheap. You are definitely using certain amount of the structured dielectric agent, which is the micropore. They have certain cost. So overall, if you think about the reagent chemistry and the ZSM5 and beta catalyst, maybe the initial cost may be little higher. Maybe in case of reagent, maybe let's say 100 rupees, and in case of zeolite, maybe 200 rupees. Let's assume. But reagents producing large amount of the waste, and you are not recyclable. Once you have the zeolite, you can do this catalysis. Having zeolite once in place, you can use this zeolite for 1,000 times. So you can have this activity. So the cost, initial investment is required more, but later on you are sustaining and you are keep on working with the same. That is the first answer. The second answer is that yes, when we compare our biomass starch-based, silica-based material and when we use them for tri-level porous zeolite material, yes, they are cost-effective because we are using starch and the cellulose. They are much cheaper and they are easily available when compared to the tailor-made, specially designed organic structured dielectric agent for the generation of the mesopores and the macropores. So in that aspect, definitely our approach is very sustainable and very cost-effective. Yes.
Thank you, Professor Srivastava. I think the time factor. I would like to request, if there are any more questions, we can take one more question if there is anyone who wants to ask a question. Given the time factor, I think we can. Okay. Yes, there's one question from Ranjita Das for cerium oxide geometry optimization. Which software was used by your group?
Yeah, so actually we have not done that work. This work was done by our collaborator in our department. I think we have used DMOL 3 software.
Okay. Thank you. Thank you very much. I think we would now like to conclude this talk, and I would like to again thank Professor Srivastava for giving a wonderful talk on behalf of myself personally as well as the organizer. I would like to thank him for taking time out of his busy schedule and giving us a very good insight into the heterogeneous catalysis in his group. Thank you very much.
Thank you. Thank you very much. Thank you, Manoj, and thank you, Anand, for your nice gesture. Thank you.
Now we are moving on. The next speaker for the afternoon session, so the second session which was going on, this next speaker is none other than Professor Radha V. Jairam. She is a head and professor in Department of Chemistry at the Institute of Chemical Technology, Mumbai. Her research focuses on the heterogeneous catalysis in organic synthesis, application of green chemistry principles for process intensification, waste minimization and waste treatment, adsorption techniques for removal of water pollutants, photocatalysis and photodegradation of pollutants, synthesis and application of novel materials, surface and interfacial chemistry. Till now, Professor Jairam has extensively published in the area of physical chemistry as well as surface catalysis and has more than 122 peer-reviewed publications in reputed journals. She has supervised to date several doctoral and master students in chemical science as well as technology. Professor Jairam also received the 2015 ACT Best Woman Chemistry Teacher Award from Association of Chemistry Teachers. Today, her title is the title of the talk, what she's going to give today, is Catalysis, a Green Chemistry Approach. Professor Jairam, the stage is yours. We are starting at 12:15, so we will complete by around 1 o'clock, and then we'll have a 10-minute session.
Okay, thank you, Anand. Can you hear me?
Yes, yes.
Good afternoon, everyone. Can you hear?
Yes, madam. Madam, you can go ahead.
Okay, I just don't want the video. Now that you have seen me, it's okay. How do I?
There is a button.
Yeah, one minute. Yeah. Okay. Good afternoon, everyone. First of all, I thank the organizers. Can you see the screen?
Yes, Professor Jairam, yes, you can see. You can click on the slideshow so that it is complete.
Me to this.
Hello.
So my topic today is green chemistry approach to chemical reactions. I will start first with an introduction to catalysis, then what is green chemistry all about, and how catalysis can address various green chemistry issues with some suitable examples. So this would be the content of my talk. First, I would be giving an overview of catalysis. Though people know it, there may be students, because it's a mixed audience, I thought I would have to start with a brief introduction and what is meant by green chemistry and what is the need for green chemistry, what is the role of catalysis in green chemistry, and how catalysis can be carried out in an evergreen green solvent, which we all know that it is none other than water. This slide may look very primitive because it's a basic definition of catalysis. In spite of that, I know that many undergraduate, postgraduate, even PhD students would definitely make at least one mistake in this definition. This is a definition of Oswald given maybe a century back. Catalyst is a substance that increases the rate at which a chemical system approaches equilibrium without being substantially consumed in the process. This definition is fully correct. But today, if we define a catalyst and the process of catalysis by this definition, I think we would be definitely insulting catalysis and catalytic substances, because a catalyst can do many more things other than simply improving the rate of a chemical reaction. So we have to give the due credit to the concept of catalysis, the reach of catalyst in chemical reactions other than improving reaction rates. So if you look at this, rate enhancement is one aspect of catalysis, but with a proper choice of a catalyst, I can also harvest different forms of energy, can be sustainable energy, clean energy. I can use alternate feedstocks. I can use alternate solvents. Above all, I can impose selectivity in a chemical reaction. All of us know that in case of chemical reactions, especially in the production of pharmaceutical products, how important selectivity is. Sometimes one may have to compromise in activity to make a reaction better selective. I would just give you a few examples of catalytic reactions which made a global impact. The first one is hydrogenation reactions. Sebastia's work on hydrogenation reaction, again, more than 120 years back. Today, we talk about several types of hydrogenation: asymmetric hydrogenation, transfer hydrogenation, hydrogenation to produce chiral products. So hydrogenation encompasses various branches of chemical production and production of high octane gasoline. And in fact, this high octane gasoline production secured the victory of Royal Air Force in the Battle of Britain in the World War. And again, Ziegler-Natta, chemistry and technology of polymers, nylon and polymer derivatives. Knowles and Sharpless work, we know that is, bringing chirality in chemical synthesis and developing a method to produce L-DOPA in large scale. Again, Thomas Chick work on catalytic activity of ribozymes. We all know the impact of viruses and what is the role of catalytic activity of ribozymes, at least at this juncture. And this one reaction, it actually changed the fate of Germany after the World War. Simple reaction, fixation of nitrogen from air into fertilizers. Till then, people were using only natural fertilizers, and with the growing demand of world population and food need, and this could not be met with. People tried several methods, and it was an Herculean task. Just fixing nitrogen, which is present to an extent of about 74% in air, and then making into a fertilizer was very, very difficult. Bugs could do it, enzymes could do it, but we couldn't do it. But fortunately, in industrial chemist Fritz Haber and coupled with the help of a chemical engineer called Bosch, they designed the Haber-Bosch process to convert nitrogen in the air to ammonia. Till today, very little changes have been made in the plant design of this reaction that talks about the authenticity of the system they developed. On paper, this reaction looks very, very simple. Of a molecule of nitrogen, 3.5 molecules of hydrogen, or 1 molecule of nitrogen and 3 molecules of hydrogen producing 2 moles of ammonia. It's an exothermic reaction, and it has to be carried out at moderately low temperatures and high pressures. But then it took more than a century to arrive at the mechanism of the reaction. Gerhard Hertel, a very famous surface chemist from the Fritz Haber Institute of Max Planck Society, Berlin, he proposed a detailed mechanism for this reaction. And of course, in 2007, everybody would recognize this platform because ultimately this is the destination where every scientist would like to reach. He received the prize, the Nobel Prize in 2007. If you look at the history of catalysis, right from 1909, Nobel Prizes were awarded to various equilibrium rates of reactions, and also catalytic reactions. Then it went on to hydrogenation of organic compounds, carbocation chemistry, polymerase chain reaction, and 2010 was the last year when Heck, Negishi, and Suzuki, they got the Nobel Prize for palladium catalyzed cross-coupling reactions. So it is more than a decade now. I think it is high time that a Nobel Prize in catalysis is awarded next year, or maybe this year itself. So as I told you in one of my earlier slides, the catalyst can do wonderful things apart from simply increasing the rate of a reaction. You can think of new processes, you can think of new products, you can think of energy economy in a chemical reaction, and you can also use a catalyst for environmental issues. And above all, by doing all this, definitely you will reduce the cost of production. After all, nobody comes into industry to do charity. If you tell that a catalyst will do this and that, but your cost will not be reduced, and nobody will look for this. And apart from that, catalysis is also an interfacial science. Not only heterogeneous catalysis is a surface phenomenon, the concept of catalysis itself is an interface between chemistry, physics, biology, chemical engineering, material science, you name any branch of science and technology, a catalyst and catalytic concepts are used somewhere or the other. And today, if you see, more than 80% of the process in the chemical industry, they use a catalyst at some stage or the other. It is a huge industry involving about 1,500 billion euros annually. So how does a catalyst help in a reaction? As I told you, I can use raw materials efficiently. I can use. Now people are talking about biomass. At one time, no one talked about. Maybe a couple of centuries ago, biomass was never considered as think about how to design a reaction so that either you produce no waste, and if you produce waste, it is your responsibility. And one has to think of new fossil fuels are exponentially, the resource is declining, so you have to harvest solar energy or any other form of bio energy and any other form of energy to compensate for the energy sources that are available today. So I given a simple example. Today, no one looks at a reaction where you are using either a mineral acid or a or a stoichiometric reagent in chemical reactions. Maybe in a classroom, maybe in a laboratory, but in an industrial scale, I think people are moving towards solid acids, solid. Diagram below, it's an acid bottle. You can see that it is fuming, fretting, and the label itself is spoiled. If one can think of a solid catalyst which is as acidic as 100% sulfuric acid, of course this was a catalyst developed by Ola. There are acids which are known as super acids, which are stronger than even 100% sulfuric acid. You can simply handle them, you can use them, reuse them. They are solids which are no problems. So industry and academic research has shifted now towards producing catalytic materials which are easy to handle, hazard-free, and are reusable. So when we talk about a catalyst, there has to be certain performance parameters. So there are basically 3 performance parameters. One is activity of the catalyst, selectivity of the catalyst, and stability means how it deactivates. Because if you remember, in the first definition we told a catalyst is not consumed in a reaction. If it is not consumed in a reaction, why a catalyst cannot be used eternally? It's something like a perpetual material. That is not possible because a catalyst can be physically present to the same extent to which you had taken at the beginning of the reaction, but its quality could have been considerably reduced during the course of the reaction. Because in the catalytic cycle, the catalyst is reproduced, but there may be certain other side reaction, there may be certain other effects, so that the activity is slowly getting reduced in the course of a reaction. So if you have to talk about catalytic activity, there are various parameters. I deliberately put this slide because even now students have a tendency to compare catalytic performance on the basis of certain parameters which are not totally acceptable. For example, people talk about length of reaction time. There is nothing called length of reaction time because time varies for a particular level of conversion with the quantity of the reagents you have taken. So the better parameter would be reaction rate, or you can use the temperature at which a particular level of conversion can be achieved because this is directly related to energy input, or you can talk about turnover frequency, how quickly you can get the desired yield, or turnover number, how many times you can turn over the catalyst till it is completely deactivated. And by doing all this, you can also find out the lifetime of a catalyst. I'll give an example, this the syngas, hydrogen and carbon monoxide, depending upon the choice of a catalyst, I can form methane, I can form methanol, I can carry out pressure drop synthesis, I can make higher alcohols. So the choice of a catalyst actually decides not only the activity, but selectivity towards a particular product. So these are the various types of selectivities in a chemical reaction: chemoselectivity, regioselectivity, diastereoselectivity, and also enantioselectivity. All these selectivities you can achieve with the proper choice of the reaction. We all know that enantioselectivity is extremely important in case of pharmaceutical products. We know certain catastrophes which happened because where the product was not 100% chiral pure, and it led to severe problems. And again, the next important issue is catalyst stability. Especially when you're working with very expensive catalysts and catalysts which are very difficult to design, then the stability becomes very, very important. Catalyst stability is nothing but catalyst deactivation over the course of the reaction. The catalyst can be poisoned, or there can be some deposits on the catalyst surface which block the active sites, or there can be sintering, due to which the particle size reduces, active surface area reduces, or sometimes the catalyst can be lost by evaporation. For example, some metal carbonyls, they are highly volatile. So during deactivation, either the number of active sites decrease, or there will be a degradation in the accessibility of the active sites. Both lead to deactivation. So what you have to do is, first you have to find out the reason for catalyst deactivation. That can be done by several ways. One, you can monitor the activity and selectivity over various cycles, or you can do a surface characterization. Once you know the deactivation mechanism, I can think of reactivation. Again, it can be at various levels. It can be the catalyst source, or it can be, the reactivation can be done by changing the reactor design, or it can be done by changing the operating conditions. For example, if it's sintering, I can try to do the reaction at a lower temperature. But then, irrespective of all this, if you cannot reactivate a catalyst, you have no option but to discard the catalyst. Again, you cannot discard as you want. You have to recover all heavy metals from the catalyst. You must see to it that when the catalyst is returned to the environment, it is not going to cause any environmental hazard. So what is the relevance of catalysis to green chemistry? See, this is something, in the last 100 years, everybody is talking about pollution as though pollution is a new phenomenon. The pollution had been, in vogue for several centuries. Okay, even in the Stone Age, when somebody was cutting the stone, there was particulate pollution. Okay, but what happened in the last several centuries is the level of pollution has gone out of control. We polluted everything. We polluted air, we polluted water, we polluted soil. Only fire, of the 5 elements, fire we couldn't pollute, we polluted everything. But there are several reasons for this pollution, and this pollution is not only due to chemicals or chemical industry. We have to understand that though we have taken the responsibility fully, environmental pollution is due to many things. It can be due to deforestation. It can be reckless discharge of domestic waste and municipal waste, agrochemicals. But unfortunately, the blame came completely on chemicals. Because of that, there was a negative perception of the public, and there was strong opposition to new chemical plants, and a decline in government assistance in R&D projects. And people thought that chemists are there only to pollute the environment. All chemical laboratories are producing stinking substances. So there was a very, very negative public impact. So what happened was, maybe in the turn of the century, several people came together, for example, Constable, Paul and Estes, and Sheldon, many more. They all came together, and then they decided that chemistry has to be practiced in a different way, which is now popularly known as green chemistry. Please understand that it is not a separate branch of chemistry. This is an approach to chemistry, but through a different pathway. So the green chemistry approach was, actually capsuled into 12 principles, which are the guiding principles to carry out chemical reaction. In principle, green chemistry works by reduction. It reduces energy input, it reduces waste, it reduces auxiliaries, it reduces hazard, and it reduces use of solvents. So many of these green chemistry goals can be achieved with one substance, that is a suitable catalyst. So anything which you cannot monitor, you cannot manage. So even in case of green chemistry, how far a reaction is green can be assessed by various factors. One is known as atom economy. How effectively you incorporate all the atoms in the reactant into the products. And the most important things which are repeatedly used in chemical reactions to monitor the greenness of a reaction are atom economy and E factor. So as I told you, catalysis opens the gates to a green world. How? Because with a catalyst, I can efficiently use raw materials, that too renewable raw materials. I can use clean and green sources of energy. I can develop new chemicals which are hazard-free. I can develop new processes. That is, I can the existing process I can do in a different way so that the process becomes hazard-free. For example, the Bhopal disaster. If that methyl isocyanate had been made in situ, I mean, it's by a simple, different way of looking at the chemistry, that disaster could have been avoided. So there are three different ways in which a catalyst can, help in achieving green chemistry processes. One, either you totally develop a new clean technology and replace the existing dirty technology, or existing process, you can improve the process by making certain changes. Or you can also build a system in such a way that the solvent is completely recycled and the waste that comes out of an industrial plant does not have any hazardous material in them. So how are we going to achieve these green chemistry goals? See, this is an ideal reaction system where the reaction should be 100% atom efficient. The reaction should be simple. That means it should happen in very few steps. It should be safe. Preferably, it should be one-pot synthesis, and there should be 100% yield. All material should be about to the next end of somewhere one has to make compromises. Obviously, you cannot make compromises in case of safety. You cannot make compromises in environmental acceptability. You cannot make compromises on waste generated. Maybe sometimes you may have to go for a higher cost. Maybe you may have to go for multi-step reactions, but certain parameters cannot be compromised. So what we did was, we chose a model reaction, which is a very well-known chemical reaction. And with that reaction, we used different type of catalytic systems and then addressed the green chemistry objectives. And we saw that how each system attributed to one or more of the green chemistry goals. This is a Navigational reaction, one of the oldest reactions in organic synthesis. But the challenges are, most of the time the reaction requires reaction conditions which are not very mild. Reaction rates are also low, and selectivity again could be a problem. Workup could be a problem. The catalyst could be non-reusable. I'm not saying that all disadvantages will be with one reaction scheme. If you look at the literature, each scheme would be having some disadvantage or the other. So ideally, one could think of a system where the conditions are mild, reaction rates are high, selectivity is high, and workup is simple. So what we did was, the same reaction we carried out with solid acids, solid bases, biphasic catalysis, wherein the catalyst separation becomes simple. And we also brought in the concept of interfacial chemistry in achieving green chemistry goals in this model reaction. So we carried out the reaction in a biphasic system. Here what happened is, the catalyst solubility can be regulated by monitoring by manipulating the temperature, so that once the reaction is over, the catalyst phase can be separated from the reactant or product phase, and hence it can be reused for further reactions. So this system we tested for the Navigational condensation reaction. We found the catalyst which developed to be reusable. Separation is very easy, and desired products yield was also quite considerable. We got more than 80% yield. The next, we thought of a solid acid catalyst. As I told you, the moment we say acid, what comes to people's mind is something very fuming, something very hazardous, something it's very difficult to handle. Solid acids had always been there in science, in chemistry. Maybe people did not classify then many metal oxides are solid acids, mixed metal oxides are solid acids. So one can actually design a catalytic reaction using a solid acid. What we did was we used zirconia doped ceria as a solid acid. This has got oxygen non-stoichiometry. In fact, doped ceria acts as an oxygen exchange catalyst because of this oxygen non-stoichiometry. It is something like 3.8, I think. I don't remember the exact value. So if this zirconia doped ceria is a very good redox catalyst. In fact, the thermal stability and redox behavior of ceria is immensely improved by incorporating zirconia, and it has been proved that ceria and zirconia form a substitutional solid solution. So this reaction again we carried out in various solvents, and we found that the conversion varied from about 50% to 95% depending upon the temperature and solvent which we used. And again, the green outcome of this method is the methodology is versatile. I didn't show because this can be extended to various substituted aldehydes. Reaction could be carried out in the liquid phase at atmospheric pressure and mild reaction temperatures. So we have developed a system where a solid acid can be used for Navier-Stokes condensation reaction under ambient conditions. Again, carbon materials have become, the choice of catalysts today. Various types of carbon materials, carbon nanotube. Advantage of carbon materials is they can be obtained from agricultural resources. So what we did was we produced activated carbon from agricultural resources like fruit peels, and then we try to functionalize them. See, unless you functionalize a carbon material, it doesn't become an efficient catalyst. You can do acid functionalization, you can do base functionalization. So we did amine functionalization using various amines of the activated carbon. And then we tried again the same Navier-Stokes condensation reaction. And then we found out the conversion to again vary from 20% to 98%. We can see that the activated carbon, when it is amine functionalized, the activity increases. Though the reaction rate does not change much, the conversion of benzaldehyde and final yield to the product that increase. So we have developed a solid reusable base from renewable resources. Again, two green chemistry objectives addressed. It is cost-effective and metal-free base catalyzed system. And there is ample scope for using this activated carbon in other base catalyzed reactions because we have used it only for a model reaction. It can be used for several reactions where a base catalyst is used for and maybe an important intermediate for a final product. The goal and the ultimate goal and the ultimate dream of everybody is to carry out a chemical reaction in a green solvent. We all know the green solvent is none other than water. Let us go back to our sustainability in chemical industry. I told you the green chemistry is waste prevention, atom economy, that is every atom of the reactant should be incorporated into the product. Synthesis should be less hazardous. There should be a design to produce safe chemicals, benign solvents, auxiliary should be benign and if possible can be avoided. Energy efficiency, renewable feedstock, use of derivatives should be considered. Then and many of these goals can be achieved using a catalyst. That is what I am going to show you from a different perspective. So if you look at a chemical reaction, about 56% of the total volume of a chemical reaction system is water. But the recovery efficiency is never more than 80%. The question is, are these solvents always benign? Are the methods used in the recovery benign? What is the fate of the volume of the solvent that is not recovered? So these are the questions that have to be addressed, which I think very conveniently we just pushed it under the blanket and we never bothered about it. Many of the solvents favored by organic chemists are on the blacklist. That the whole question of there is a solvent. This SmithKline Beecham company. They have made there is a complete report on solvent choice. So most of the solvents are actually blacklisted, and they use too much solvent, and they also use wrong. Be heat dissipated. So whether a solvent can be completely, avoided in a chemical reaction, that is questionable. But if one has to use a solvent, one has to use it prudently and with some kind of consciousness. That's what it means. This statement was made by Sheldon almost 30 years ago. So why water? That everybody knows that water is non-toxic, non-inflammable, abundantly available. It is not expensive. I won't say it is free because nothing is free of cost now. Water is no longer free. But the problem is there is a limited solubility of organic compounds in water. Is there a solution to make a solution in water? Yes, you can carry out a reaction by putting in high agitation. That is, it's something like emulsifying with mechanical energy. You can use a phase transfer catalyst, wherein a catalytic substance acts like a vehicle. It brings the reactant from one phase to the other. Once the reaction is over, the catalyst is taken back to the previous phase. That is one possibility. But again, are there problems? Yes, there are problems. There may be problems of toxicity, workup, and many things. So what we can do is, if I can produce an organic phase within an aqueous phase, will it not be a wonderful situation? How much time I have got, Anand? Hello?
Madam, you have time.
How much?
You have 15 minutes.
15 minutes, okay. So we can think of water as a reaction medium for catalytic reactions as well as non-catalytic reactions. How? Let us see. I can use a surfactant system to generate an organic phase within an aqueous phase. We all know what is a surfactant is. Surfactant is a unique molecule which has got a hydrophilic head and also a hydrophobic tail. Because of this unique nature, when you add a surfactant to water, the water molecules, of course, they have to adjust, breaking their hydrogen bonding to accommodate the tail part of the surfactant, though they very happily welcome the hydrophilic head. So definitely there would be a free energy disturbance, and this can be compensated if the surfactants adsorb at the water air surface, or if it's a system of two solvents, the surfactant can adsorb at the liquid-liquid interface. So surfactants, because of this unique structural assembly, can adsorb at the interface of liquid air, or liquid and solids, and incorporate several additional artifacts. They incorporate additional properties to the solvent system. One, they can drastically reduce the surface tension. They can also change the surface viscosity, and being present in the bulk phase also, they can do certain things which we will see later. So one important implication of a surfactant getting adsorbed at a liquid surface or a liquid-liquid interface or a liquid-solid interface is drastic reduction in surface free energy, and hence drastic reduction in surface tension. So this is, this is actually exploited in various industries like detergent industry, in wetting, in wetting, and then in coating. So various industries have utilized this ability of surfactants to adsorb at interfaces and surfaces. Surfaces and interfaces are one and the same. When one of the phases is a condensed phase, we use the term interface, otherwise we use the term surface. So depending upon the nature of the head group, surfactants can be classified as non-ionic, anionic, cationic, and zwitterionic. These are common, very, I would say, older definition of surfactants. But now we have surfactants like Gemini surfactants, we have surfactants like metallosurfactants, which the metallosurfactants will be one class of surfactants that I will be addressing today. And not only that, the surfactants have the ability to adsorb at the interface, they can also, within the aqueous phase, they can arrange themselves in such a way that the water hating part of the surfactant molecule is kept away from the water, and the water loving part, that is a polar head group, is facing the water surface. So they form some kind of aggregates which are known as micelles. The micelles can be of various shapes and various sizes, and that depends upon the nature of the surfactant, and it also depends upon the pH of the system. It also depends upon temperature. So the surfactant aggregates can be of various sizes, various shapes. You can have lamellar micelles, you can have cylindrical micelles, you can have spherical micelles. So everything is possible. So micellization is an alternate mechanism to adsorption to reduce the solution free energy. So what happens is, if I form surfactant aggregates within the aqueous phase, this newly formed surfactant phase itself acts like an organic phase. I can use this as a medium to solubilize some reactants. So that is the advantage of carrying out reactions in aqueous phase using surfactants. But if a reaction has to be carried out in the micelles, the concentration of micelle should be above a particular concentration known as critical micellar concentration. Only above this concentration there would be, a continuous micellar phase, and then the reaction or the solubilization can happen in the micellar system. So what we did was, we took again a very common reaction. You may ask, why are you using this reaction? After all, it is a, we only told that derivatization, de-derivatization should be avoided. But in case, if in a reaction, the derivatization and de-derivatization could not be avoided, at least let the reaction go in a green possible way. So what we did was, we did N-benzyl oxycarbonylation of amines in aqueous micellar system, and this could be done at room temperature. So this this protection is basically done to protect nucleophilic and basic properties of the molecule. And this reaction we carried out with surfactants at room temperature, and the reaction could be completed in just 10 minutes. So then the reaction was carried out. These are all conventional we did way back in 2008, one of the earlier reactions which we started with interfacial systems. Then encouraged by the results, we carried out nominal condensation also with the same surfactant system, and the reaction could go without even the intervention of a catalyst, and we could go above 90% yield with the surfactant system which we used, and these are all isolated yields. We used a cationic surfactant CETA. So the great advantages was, in this case, no catalyst was required. Water was used as a solvent. The reaction product yield was quite high. Temperature was low, and product isolation was also very simple. You have to simply break the micelles, and then you can use them again. Now, micelles can act as a reaction medium. But what if I have to use a catalyst? Then I have to think of a system wherein the catalyst as well as the reactants are within the micelles, or I have to think of a phase transfer catalyst. So is it possible to develop a surfactant system which not only solubilizes my reactant but also acts as a catalyst? The answer is yes. I can think of such a catalytic system, such a surfactant system, which acts not only as a solubilizing agent, but it also acts a catalyst because of the counter ion. If the counter ion is a catalytically active transition metal ion, then the surfactants can act as a reaction medium above, of course, a critical micellar concentration, and they can also act as catalysts. So such micelles or such surfactant aggregates are known as metallomicelles, and such surfactants are known as metallosurfactants. Depending upon the location of the transition metal ion, these metallosurfactants are classified as type 1, type 2, and type 3 metallosurfactants. So what we did was, first we thought of cobalt as a transition metal oxide because it has got variable valency, and cobalt oxide has been used as a catalyst for many reactions. So we made cobalt oxide metallosurfactants. We did some geometry optimization and tried to get the structure of the cobalt metallosurfactant, and we characterized it by various techniques. We recorded, I've given only an illustrative example of one cobalamin surfactant. We recorded the proton NMR spectrum, LCMS, and also we did elemental and ICP analysis to know the composition. And by all these characterization techniques, we confirmed that we have formed indeed a cobalt oxide metallosurfactant. And we also determined the CMC values and compare that with conventional surfactants. If you see the CMC values of the cobalt-based metallosurfactants are quite low. So that means I need a very less quantity of the surfactant to carry out the reaction. We also determine the size of this metallomicelles by dynamic light scattering method. And we try to see whether there is any, we wanted to study the oxidation of benzyl alcohol. So we determined the solubility of benzyl alcohol in the surfactant systems, of course, above CMC. We try to see whether there is any correlation between the solubilization and aggregation number, but unfortunately, we couldn't determine the aggregation number of a few surfactants. Then what we did was we took a mixture of this metallosurfactant and conventional surfactant, and we found out the transfer free energy value, and also we found that these systems are better than the individual system. There was some kind of a synergistic effect, and we carried out oxidation of benzyl alcohol to benzaldehyde using these systems. Conventional systems, conventional methods do have certain drawbacks like low selectivity, chlorinated byproducts, and toxic waste. And these we thought could be avoided by using the surfactant-based systems. And we found out the selectivity and the conversion for the benzyl alcohol oxidation with various conventional metallosurfactant and their mixtures. And these are the optimized reaction conditions. Encouraged by the results of the, hello?
Last 5 minutes.
5 minutes, okay. We moved on to copper-based metallosurfactants. Again, we characterize them by the regular techniques, determine the CMC values, and we tried two reactions with them. One, synthesis of phenols by oxidative hydroxylation of phenylboronic acid. And these are the effect of various parameters on the reaction. Various substituents in the phenol were also tested, and we found that these are the drawbacks of the reported methods, and these are the green advantages of the method which we have developed. Encouraged by this, we again we did a condensation reaction, synthesis of chalcones, and again these are the reported methods. These are the disadvantages. We try to see whether these advantages could be achieved, and we did indeed. And again, the reaction parameters were optimized by changing the reaction variables. And we found that both copper and cobalt metallosurfactants exhibited good catalytic activity for oxidation and coupling reactions respectively. And the most important green advantages, we could use water as a reaction medium. Then there is another class of surfactants known as ionic liquid surfactants. Ionic liquids, when they have a particular level of chain length, can be surface active. So we chose certain ionic liquid surfactants, and what we did was we tried to do oxidation of toluene using these surfactants. And these are the methods by which we optimize the reaction conditions. And we found that these ionic liquid surfactants exhibited synergistic effect with conventional surfactants. Toluene could be solubilized and also could be oxidized. I need just another 3-4 minutes. Anand, would you please spare?
Sure, madam.
Okay. The most important aspect of another type of interfacial catalysis, which is very, very interesting, is Pickering interfacial catalysis. See, when we try to stabilize an emulsion using a conventional surfactant, there are certain problems. Well, recovery could be tedious, and the surfactant stabilized emulsions could have some environmental issues. So what if I use a solid which can be present at the oil water interface, so that the droplets of the emulsion do not come together, they do not aggregate. So this concept was addressed by a person called Pickering. Pickering was a British chemist and he also an horticulturist. I think he has contributed enormously to an encyclopedia. And he found that solid particles which are adsorbed at oil-water interface form stable emulsions, and they are named after him. They are known as Pickering emulsions. We thought we will make emulsions using magnesium oxide as a Pickering agent. We precipitated magnesium oxide using 2 different precipitating agents, and we also calcined them at different temperatures, and we found that the method of precipitation and also the calcination temperature some effect on the physicochemical properties of the magnesium oxide, more than chemical, on physical properties like crystallite size, polydispersivity index, so many things could be affected. So we formed magnesium oxide Pickering emulsions. Then what having a Pickering emulsion, it only solubilizes something, If I can think of a reaction which can be catalyzed by magnesium oxide, it will be, hitting 2 birds with a single stone. So magnesium oxide, we all know it's an excellent solid base catalyst. That is because of the Mg2 plus vacancies and also due to the low concentration planes that are present on the surface. So what we did was, we tried to develop Pickering interfacial catalysis using magnesium oxide Pickering emulsion, and we again use the system for our favorite reaction, that is Navier-Stokes condensation reaction, and we found that the isolated yields varied with respect to the calcination temperature of the magnesium oxide prepared, and the catalyst could be reusable at least up to 5 cycles, and these are the advantages. About 80% of the condensation products could be isolated. Magnesium oxide suspended in the aqueous phase can be separated by simple centrifugation and can be reused. Water is used as a solvent, and the emulsifier itself acts as a catalyst. So these are the highlights of this protocol. So coming to the global challenges of challenges today, the challenges are alternate fuels, reducing harmful byproducts, cleaning up the environment, declining the causes of global warming. So most of the challenges could be met with using proper catalyst, and there are immense research opportunities for catalysis. There is enough to explore about catalytic reaction mechanism, which is not very easy. Studying surface reactions is very, very difficult. One can understand the chemistry of surfaces, apply quantum chemical methods to catalysis research. One can develop novel catalyst supports. New catalytic processes can be developed. Catalyst deactivation and reactivation can be better understood. Homogeneous catalysts can be heterogenized by using proper anchors, and of course, catalysis can be tried in green solvents. This is what Albin Miftash told, the person who was behind this Haber-Bosch process, who was an engineer behind this. He said chemistry without catalysis would be a sword without a handle, a light without brilliance, a bell without sound. These are the persons, these are my dear students. One is Dr. Manoj Gamande. I think he is a co-convener of this project, of this conference, and Dr. Janvi Shrikante, Dr. Anand Burange, and part of the work is, by Amber Sahani, Tushar Devre, Amit Sadgar, and Anuman Gaike. They are yet to submit their thesis. So whatever I presented today, it's a consolidated work. It's an emulsified, concentrate of all the efforts by these people. These are some of my research students. Some of them are missing. We met them a few years ago. All of us met at a common place. Manoj is not there. At that time, he was not in India. So thanks a lot, my dear students. Because of them, I could come up with these results. And I also thank the audience for their patience. I thank Anand for his nice introduction and managing the session very efficiently. And finally, I thank the organizers for giving me this platform to bring about the reach of catalysis and a new dimension of catalysis, which is, using surfactants, interfacial science in achieving green chemistry goals using catalysis. Thank you all.
Thank you very much, Professor Jairam, for a very informative talk. I think it started from the basics, tried to understand exactly how green chemistry plays a very important role, and how heterogeneous catalysis, which is a theme of this conference, somewhere it could play a very important role in developing efficient processes. And this was very nicely divided into various parts by Professor Jairam. including even her research perfectly to show us exactly how it could be done. We could take few questions if anyone wants to go ahead and ask the question. I don't see any. Is there anyone? Or if I could ask a question, maybe. Oh, madam, yeah.
Yes, Anand.
So, Lely, if you want to go ahead
I don't have a question. I just have a comment for Radha.
Yes,
That
ma'am.
Dr. Manoj is her student. So it is said in Sanskrit that Shishya Tichet Parajam. She must be feeling very proud to see her student growing so well and organizing such a great international event. And
Yes.
Yes,
very
ma'am.
nice talk, Dr. Radha, as usual. You are a fantastic teacher.
Thank you, ma'am. Anand, you wanted to ask something?
Yes, madam. Now you have done a lot of heterogeneous catalysis, and
Yes.
from morning session as well, we have seen what Professor Selvam talked about, or Professor Srivastav talked about, that homogeneous catalysis or general synthesis, the realization of the importance of heterogeneous catalysis may not occur to many people, and something which personally I thought was one of the reasons would have been that if there is a specific example where homogeneous and heterogeneous could be, if there are several papers or several examples where a reaction where homogeneous reactions or homogeneous catalyst has been used extensively, but then either it has been heterogenized or certain alternative heterogeneous catalysts could have been compared. Maybe then naturally the realization will also be much more. Would you like to shed some light on this part?
See, going abruptly from an homogeneous catalyst to heterogeneous catalyst is not a solution. The fact that people have chosen homogeneous catalyst is there are certain advantages. One is reaction conditions are mild. See, the one super advantage of heterogeneous catalysis is separation. Heterogeneous catalysts are highly susceptible to poisoning. They need drastic conditions, and then understanding the surface chemistry is very difficult. But in spite of that, they enjoy the kind of place they've got in catalysis is the separation. So if there are several papers where homogeneous catalyst can be anchored on a platform, heterogeneous homogeneous catalyst, you can use a polymer anchor, you can use liquid biphasic catalysis. What do you call? You can take a catalyst on a homogeneous, a homogeneous catalyst or a solvent supported on a heterogeneous catalyst. Okay, so there are various ways in which a homogeneous catalyst can be heterogeneous. Again, here the major problem is leaching. So to think of a stable, heterogeneous, homogeneous catalyst is a challenge, and if people start working towards that line, I think both the advantages of these two extreme situations of catalytic chemistry can be coupled.
Thank you, madam. We can take one more question. So this is being put up by Rajiv Kumar Shandilya. He's saying, madam, you have discussed quantum chemical methods for green catalysis. Can you shed some light on this part?
No, I had told these are the research opportunities. You remember in the previous talk, somebody talked about, so understanding the active sites, metal clusters. These computational chemistry, especially in case of metal catalysts, so far computational chemistry has not been completely, exploited in catalytic science. So there is a lot of opportunity to go for that. That's what I meant. Not for green chemistry, understanding catalytic activity and catalyst surfaces and understanding the phenomena of catalyst deactivation.
Thank you. I can take one more question if anyone wants to. Manoj, you want to ask anything?
No.
If there are no more questions, again, I would like to thank Professor Jairam for giving a beautifully concepted talk on basics, applications, including research, and how heterogeneous catalysis can be really a very important area for many of us. The young generation should really look at it as a very important area, because you can also see that companies are coming forward for collaborations with the academia, and they want solutions henceforth so that India becomes so-called Atmanirbhar. So these are the solutions we should really look at. And whatever we have heard till now, I can really summarize from my own perspective that the way forward about either heterogeneous, homogeneous, but a catalyst which has a lot of application and something which can go commercial at the end of the day. So with this, I would like to thank even the organization for giving me this opportunity to be the chairperson. Professor Gavande, Professor Lele, who has always been very supportive of all of us, and even the support she has extended towards this conference. So thank you. And I would like to call this session completed. And I would like to now hand over the mic to Professor Gavande. He can take over the proceedings.
Yes, yes. Thank you, Dr. Kapadi, for chairing this session. I think you have organized very well, and it's finished within time, I guess, just 5 minutes over. I would like to thank first speaker, Dr. Rajendra, for shedding a light on various designing of heterogeneous catalysis, especially focusing on porosity and implanting various kinds of active sites. I think you have explained very well about the various geolites and how they are important in various fields, including biofuels, bioimplant, petrochemicals, and gas separations. So thank you so much once again for this informative talk. Thank you, Jairam ma'am, for a very informative, basic, yet important talk on catalysis, which is really important for sustainability as well as green chemistry approach. I think you have explained very well about how these sustainable processes are important for clean technology, how this solvent can be purified from industrial waste as well as various heterogeneous, that is a solid supportive reactions as well as various micellar reactions. I am glad to see that some of my results there, which I did during my PhD, for example, this non-anical reactions as well as this CBZ protection, it was really nice memory. I think that this is the perfect talk for this NANO-SA 2020 conference, which really aims for sustainable applications via catalysis. Thank you so much, man, once again. Thank you so much. So now we have a 1 hour break, and we will meet 2 o'clock for the last session of this conference. Thank you so much, everyone.
Thank you. Thank you all.
Adinesh.
Hello, Professor Manoj. Am I audible?
I can hear you.
Okay, and video is fine?
Yes, yes.
Okay, thank you very much. Just wanted to
It is
check.
fine. Yeah, thank you.
Thank you.
Hello.
So welcome back, ladies and gentlemen. We now begin with the last but one session 5. It is our privilege to have with us Professor Dinesh Sawant, scientist from NCL Pune, to formally begin and chair the session 5. So Dr. Dinesh Sawant, prior to working in NCL Pune as a scientist, he worked as an assistant professor, DST Inspired faculty at the Department of Applied Chemistry at IIT ISM Dhanbad. He has been recently appointed as DAD Germany Research Ambassador for India, which is a very honorary position from 2018 to 2022. He received his PhD degree with the Best PhD Thesis Award from ICT Mumbai under the guidance of Professor Bhange. He has many postdoctoral research experience from Saudi Arabia, Japan, and Germany. And one of the notable postdoc research was under the Nobel laureate Professor Ryoji Noyori at Nagoya University, Japan. So Dr. Sawant has published 25 international publications which are cited more than 550 times with an H index of nearly 14. In year 2011, he was awarded with Young Scientist Award by Indian Chemical Society at International Conference in the University of Allahabad, India. Department of Science and Technology has recognized him by awarding Young Scientist Award SERB Startup Grant in 2015, as well as INSA has recognized him by awarding DST Inspired Faculty Award in the year 2017. Dr. Sawant is also the founder of NGO, Sawant Innovative Foundation, which works for promoting scientific education among rural students. So may I now invite Professor Sawant to carry forward this session 5. So ladies and gentlemen, please put your hands together for Professor Sawant. Over to you, sir. Thank you.
Thank you very much, madam, for such a nice introduction. And I would like to welcome you all in the last session of this excellent conference on nanomaterial and sustainable applications. And as an alumni of ICT, it's an honor for me to chair this session. So without taking much time, here I would like to introduce speaker for this session. So first speaker will be Professor Balraman from ISER Tirupati. And the next speaker for this session will be Professor Bhange, who was my PhD guide from ICT Mumbai. So let me introduce first speaker for this session, Professor Balraman. He is currently working as a faculty in Department of Chemistry at Indian Institute of Science and Education Research, Tirupati. And today he will deliver a talk on sustainable catalysis by earth abundant metals, back to the future. So to briefly introduce the speaker, he has done Masters in Chemistry from RKM Vivekananda College, Chennai in year 2002 and PhD from Central University of Hyderabad in 2008. Subsequently, he has joined as a FGS postdoctoral fellow at the well-known institute, Weizmann Institute of Science, Israel, from 2008 to 2012. Thereafter, from July 2013, he started his independent career as a scientist at CSR National Chemical Laboratory, Pune. And thereafter, from December onwards, he is currently working as a professor at ISER Tirupati as a faculty member. And his research interests are focused on catalyst development for sustainable catalysis, particularly, and for C1 chemistry. He's a recipient of many prestigious awards. I would like to mention few of them, like bronze medal for his contribution in chemical research from CRSI in 2020. Then in 2019, he was awarded with Asian and Oceanian Photochemistry Association Prize for Young Scientist, and also A.V. Ramarao Young Scientist Award. He is an elected member of many prestigious organizations. He is a fellow of Royal Society of Chemistry, FRSC. He is a member of Indian National Young Academy of Sciences, also member of INSA, Indian National Science Academy, and affiliated member of IUPAC, that is nothing but International Union of Pure and Applied Chemistry. With this brief introduction, I would like to invite Professor Balraman for his talk. Welcome, Professor.
Yes, Dinesh, thank you. May I audible, first of all?
Yes.
Yeah, good. So, very good afternoon to one and all. And thank you, Dr. Dinesh, for your introductory remarks. And let me share my slide first. Is my slides are visible?
Yes.
Good. Thank you. Fine?
Yeah, now it's full screen. Thank you.
And maybe with the permission, maybe I keep my video to disable so that it will be easy. Okay.
So just like to mention, talk will be around for 45 minutes and then 10 minutes discussion. Thank you.
Sure. Stop. Anyway, fine. Yes. It is. Yes. So good afternoon and welcome back. And really, it's very hard time for me and to catalyze you people after your lunch. And also, like, I keep my talk as bar as result to the undergrad and research scholars. Okay, so today I'll be talking on the sustainable catalysis, particularly based on well-defined earth-abundant metal catalyst. And we all know that why I kept the title Back to the Future. And after the talk, you will understand what you mean by that. Yes, and at the outset, I would like to thank Professor Lille as well as Professor Govande for their kind invitation. And indeed, it's a great pleasure for me to be a part of this wonderful virtual seminar. Okay, yeah, today maybe 30 to 40 minutes I'll be talking on mostly catalyst development and for their application in sustainable catalysis. I don't want to go into detail how do you design the catalyst like they have discussed. So I'm going to give you a kind of overview like what we have been doing for the last 5 to 6 years. Okay, yeah, so the catalysis is a fundamental phenomenon which plays very critical role in both chemistry as well as biology, and it has been immensely contributing to the benefit of the mankind, and also has been contributed to the various other fields such as food, health, material and environment, water and energy, and these are what to mention, and their application of catalysis on this particular field are manifold. We all know that most of the industrial processes are basically based on catalytic process, and you can see so over 90% of chemical processes are mainly based on catalytic reaction. Only the 10% is belongs to stoichiometric reaction. This shows how the catalysis or catalyst development plays a critical role in not only in the day-to-day life as well as in chemical and pharmaceutical industries. And if you look at it carefully, and most of these metal complexes or most of the catalytic reactions are metal centric. What do you mean by metal centric? So we just take a typical cross coupling reaction. So because this is received a Nobel Prize, and 3 gentlemen received a Nobel Prize for palladium catalyzed cross coupling reaction, and also so many of the research scholars well aware about it. So with that, I will start this. And this is mostly applicable for precious metal, particularly iridium, rhodium, ruthenium, and palladium. Okay, and what do you mean by metal center catalysis? So, for example, I have a metal complex. So, particularly, you have a well-defined homogeneous catalyst. First, this substrate, you are going to activate the substrate. First, this substrate activated by this metal complex via oxidative addition. So you can see this during this process, only the metal center is the only active center, and ligand does not have any role. It means it gives you a kind of a pocket to the good environment to the metal center, both steric as well as the electronic factors. It gives you the metal center, but it will not take part in the during the bond activation process. That's mean by metal center catalysis. So also during this process, the oxidation state of the metal is increased from N to N+2, and it follows other elementary steps. We all know the transmetallation on other reactions, and finally via reductive elimination, this leads to the product formation and completes the catalytic loop. Okay, and even during the product formation also, the oxidation state of the metal is decreased from N+2 to N. Okay, this is called reductive elimination process. This oxidative addition and reductive elimination, these are complementary and microscopic reversible reaction. We all know about this system. Yes, and this is what we say as a metal center catalysis. Okay, but in view of global concern regarding energy, environment, and sustainability, that there is a strong and urgent need of discovery of new catalytic system rather than already existing one. So there is a paradigm shift from precious metal catalysis to a non-precious metal catalysis. So why that I will explain briefly. So you need to have a good robust system for designing a molecular catalysis, basically based on this first row transition element. These are earth abundant, very cheap metals. And if you ask me why you want to work on the first row transition element, that is 3D transition element, obvious answer is, first of all, if you look for industrial application, one can think of the cost, okay, and also global resources. This is the first point if you ask any undergrad student, okay. And if you look at the cost of the first row transition element, these are much cheaper than their parent element. For example, that cost of iron is much cheaper than the corresponding or homologous series, for example, ruthenium. And similarly, nickel also is much cheaper than the palladium as well as platinum. Okay, so not only the cost, you look at the sustainability or global resources. So these global resources for the non-precious metal, particularly manganese, iron, and cobalt, are several manifold than the precious metal catalysis. So after a few years, we want to develop a catalytic system. You must work on the first row transition element because of the scarcity of non-precious metal catalysis. Okay, so I'm not against the people who are working on precious metal catalysis. Just we want to define, or we want to elaborate, or we want to give a good insight about the first row transition element. In that context, I'm talking about. This is my own perspective. Okay, and also you look at the cost of the precious metal. For example, rhodium. This is the for the last from 2012 till 2012, you look at the cost of rhodium, it's highly fluctuating, right? You can see this highly fluctuating. It's very difficult to put the price also. So this is the cost and global resource metal catalysis. Okay, may I audible? Yes, hello.
Yeah, there was small interruption, but now it's okay.
But okay, fine, thank you. Yes, and it's not only the cost as well as the global resources, and also the chemistry wise, the first row transition elements are very challenging. Why? So we can see. So as I said in the beginning, this precious metal catalysis typically follow, that is metal center catalysis, typically follow two electron processes, right? So oxidative addition and reductive elimination. Okay, it follows the two electron manifold. But whenever you work on the molecular catalysis on the 3D transition element, that is first row, iron, cobalt, manganese, and nickel, and they may not follow the same trend, okay, because there are several challenges with respect to the reactivity or with respect to the chemistry. So we are aware about it, because if you look at the typical textbook chemistry, you can see this first row transition element mostly adopts a single electron manifold. Single electron manifold means it's a kind of radical thing. So controlling the reactivity is highly challenging, it's very difficult. And also variable oxidation state. For example, you just take a manganese, and the oxidation state of the manganese is varies from 0 to +7. So whenever you design a catalytic system with respect to this type of metals, and we never know that what kind of catalytic this is being involved in your catalytic loop. Okay, it's a very challenging thing. And also there is an interconversion between the oxidation state. So you know this d orbital, the energy for the d orbital is very low and very narrow, and there will be always switch from +2 to +3 with respect to particularly the iron. And similarly, it is also applicable for other metals like cobalt, manganese, and even nickel also. And also finally, these metal complexes are paramagnetic in nature. So why paramagnetic nature? Why you have to worry about the paramagnetic feature? So if the molecule or if the complex is paramagnetic in nature, then it's very difficult to prove the reaction mechanism. If the complex or diamagnetics, we can study the reaction mechanism in NMR, but it's a paramagnetic only you must depend on the EPR tool. But it will not give a good insight. It shows only what is the spin state of the metal and all the things, except that you will not have any information. And also, since these complexes are paramagnetic, mostly they are level in nature. Level in the sense, so you have a ligand and metal. So when you perform the reaction, the ligand will come out from your metal core. So you may not have a molecular catalyst in your system. So you will have a different catalytic system. It may perform slightly better than what you expect, or it may not perform any. It will not show any reactivity also. Okay, and so then how can you overcome these issues? So if you are going to work on molecularly defined phosphor transition elements, or we are going to tackle these issues? Okay, this is anyone can ask this kind of question in your mind. So first, what you need to do that you must have a robust and innovative catalytic system for a successful design of phosphor transition metal catalysis. So why? So as I said, these are the challenges we have to overcome. Okay, so how can you overcome these issues? As I said, these are variable oxidation state. So what you need to do, you have to maintain the oxidation state throughout the catalytic cycle. Then you don't need to worry about what is the catalytic active species. So if you are taking a +1, it must be the +1 through the catalytic cycle. Okay, so you need to fix the oxidation state of the metal through the catalytic cycle. How this is possible? So not only the metal center and ligand also to take part in the bond activation, then only such kind of thing is possible. So you must have a ligand that's known as a cooperative or non-innocent or bifunctional system. So ligand also to take part in the reaction system. So it means that the metal center is not the only active center, and ligand also plays a very critical role during the bond activation. And again, there will be a structural change, and that structural changes on the ligand should be reversible. Then you can have a very wonderful or beautiful catalytic system based on the phosphor transition element. You see a typical example, a schematic diagram I have shown here. You just take, this is the complex, we call it as a cooperative complex. This metal is particularly phosphor transition element. Since we are working on manganese 1 and iron 2 and nickel, another thing, just I've given only these two complexes. And suppose you are going to activate this, and you can see this. So it undergoes a hydrolytic cleavage, and more negative part goes to the metal center, and more protic part goes to the ligand side. So here ligand also takes part in the bond activation and maintain the oxidation state of the metal N to N only. There is no change in the oxidation state. Such modes of bond breaking and bond making will enable an efficient catalytic system for a sustainable synthesis of chemical without following a traditional 2-electron manifold. Okay, and this is always, you know, whenever you design a new catalytic system, Mother Nature is inspired to all of us. Okay, and yesterday we we heard a very wonderful talk by Professor Day, where he discussed about how to activate the small molecule and other things. So and he is also working on bio-inspired catalysis, and you can see this cooperative catalysis basically is bio-inspired one. So for example, you have an enzyme called urease. This is responsible for urinary tract infection, and this is responsible urinary tract. How? Because you have uric acid or urea, and that undergoes hydrolysis. In the presence of this particular enzyme, you start getting ammonia. So this is responsible for the thing. Okay, how this reaction takes place? If you take urea and put it in a water, you will not have ammonia. So maybe it takes more time to liberate the ammonia, more days to liberate the ammonia. But this enzymes does this reaction beautifully. First, it is a bimetallic complex. First, we have a nickel center where this water is coordinated to the nickel center, and another metal center, that is nickel, and then this urea, the carbonyl group, coordinates to the other nickel center. And then histidine moiety, this is a part of or integral part of this enzyme, which is close proximity with this system. This picks up a proton from this water molecule. Then you will have more nucleophilic reagent, OH minus, that attacks the carbonyl compound. Because you have activated the carbonyl compound of urea, then the reaction happens instantly. So such kind of system, like ligand also takes part in the bond activation. If the histidine moiety is not present in your system, the reaction won't go. Okay, so this is a cooperative catalysis known in the system. This is only one example I give. This is several hundreds of examples you can look at it, like hydrogenase enzyme, alcohol dehydrogenase enzyme, and carbonic anhydrase. All this is plays a very important role in day-to-day life, which follows the cooperative mechanism. Okay, and whether this kind of system is known in the man-made complexes. The Dinesh is worked with Professor Nayori. He is well aware about this system, and you have just for the simplicity, I did not give a complete system of Nayori, and you just see this is basically is a bidentate system, and you have this is imide, this is N minus, this is minus, this is a X type ligand. So this is H, and you have a ruthenium plus 2. So this complex is a very good complex for activating a hydrogen molecule and followed by prochiral hydrogenation of carbonyl compound. So you can see how the reaction sequence follows. First, this H2 molecule code into the metal center, we have sigma complex, and followed by this 4-member cyclic transition state, and there will be heterolytic cleavage of hydrogen, and you can have a dihydride. You can look at this carefully. This is red dotted H2. So one H has gone to the metal center, another H has gone to the ligand side. This is the ligand side. So this is the way we can split the hydrogen by using this Nayori's catalyst, and again followed by outer sphere mechanism, we can have the reactivity. The basic thing what I want to emphasize here is the metal center is not the only active center for the activation of H2, and ligand also plays very important role. So here, what is the driving force? Hemide to humming. This tautomerism is responsible for the bond activation, that is H2 bond activation. You all know this is breaking of H2, you require a amount of energy, but this complex does the reaction very beautifully, precisely. And this system is known for the bidentate system. And Professor David Milson is an Israeli chemist, and he worked on a similar kind of catalysis for the activation of small molecule, both dehydrogenation and hydrogenation chemistry, where he has shown not this imide to amine concept. He used another concept called de-aromatic to aromatic compound. So which is responsible for the bond activation. So we can have this de-aromatic complex, these tridentate complexes which are in the same plane, so that you can stabilize this. Even though it's a de-aromatic compound, it is slightly stable because of all the 3 ligands. This is nitrogen and L prime will be in the same plane. So the stability will not be the problem. So if you are going to activate any HX bond, it's not only the HX bond, maybe other small molecule also, then this is responsible for the MLC, that is metal ligand cooperation. So you can see this, the de-aromatic compound becomes an aromatic compound, and wherein this H has gone to the metal center and X has gone to the metal center and H has gone to the ligand side. See here, the de-aromatic to aromatic is responsible for metal ligand cooperation. So this is basically is for the tridentate system, and Professor Nayori system is for the bidentate system, where in both the cases ruthenium people have used it. Okay, and we have been working on catalyst development based on phosphor transitional element. This is one of the complexes which we have prepared in our laboratory, which is a tridentate phenanthroline based system, where the manganese is in +1 oxidation state. You can see this is the N- imide ligand, and this activates alcohol at room temperature. So you can see this. So this H has gone to the metal ligand center, and this alkoxide ligand has coordinated to a metal center, that is manganese thing. And slightly at an elevated temperature, this molecule undergoes beta hydride elimination, call it as a dehydrogenation, and you can get back your complex with the formation of very valuable product, that is aldehyde, and H2 as a co-product. So you can see this reaction is very facile, and you can take alcohol and that converted into aldehyde with the formation of H2. Here it follows the typically a mainstream catalysis, that is de-aromatic to aromatic system, de-aromatic to aromatic, which is responsible for this activation of alcohol. And in contradictory to that, which is same complex which activates hydrogen at room temperature under excess of hydrogen, and you can see this, the ring is get hydrogenated. You can see kind of a completely hydrogenated ring. And this can be used as a complex for hydrogenation of carbonyl compound as similar to as an IOD system. So here, humming to imide is responsible for a bond activate for hydrogenation reaction. So in one system, you can have two different modes of reactivity, that is dual modes of reactivity. And so this is so totally unprecedented. This based on this complex, we have been performing several reactions like dehydrogenation and hydrogenation reaction. And particularly for this complex, and we have done some data calculation. This shows that this hydrogenation reaction follows the concentrated mechanism, and also the hydrogenation reaction is an outer sphere mechanism, and amine to imide is responsible for the bond activation. And so just for to show the utility, synthetic utility of this complex, and this is a very wonderful reaction. You can see that we have been working on CO chemistry, and just take the epoxide and then the presence of CO2 using this catalyst, one can have a polycarbonate diol where you have a terminal OH group. Okay, and someone can ask me, like, this reaction is well established, why you are going to work on this system, or what is the utility of this system? You see, it's only there are two companies. One is the Econic Catalyst by Novomer, and covers. So these are the processes are known for the synthesis of this polycarbonate diol. Particularly, you must have a dihydroxy group, terminal dioxy group. The moment you have a terminal dioxy group, this can be used as a monomer for the polyurethane industry. Okay, and it's not only used as a chemical, as a plastic, it also can be used as a monomer for synthesis of a polyurethane. You know the importance of the polyurethane. I don't want to go into detail, and these are the few benchmarks we have achieved. And presently, we are taken up this reaction for the next level with the help of GAIL. So GAIL is supporting this project, and we are working on this system using the catalyst which I have mentioned. Okay, and okay, fine. So what we have been doing? So we have been working on organometallic and synthetic catalysis. Our main aim is to synthesize here non-noble metal catalysts, particularly for dehydrogenation and boron hydrogenation reactions, and also C1 chemistry. We do have a significant result. So what I showed is really in the point of industrial point of view, and also we do have a significant decent contribution as a fundamental contribution, and we can see a few decent publication, and also we do work on a bond activation. And today I'll be talking on a molecular-based catalysis for dehydrogenation and relevant reactions. Okay, so why we are going to work, why our group is working on a dehydrogenation reaction, particularly alcohol activation. Okay, and just for that, just let me throw some few things. First, in year 2011, I started my independent career during that time, 2013, and that time there are ACS and Green Chemistry Institute. They had a brainstorming section, and several well-known companies. I can list out several well-known companies like GSK, Merck, Pfizer, Eli Lilly, and AstraZeneca. The several top people of this company, they participated, and they discussed the reactions that are frequently used in the reactions. Okay, and based on the waste management assessment and process assessment measurement, and they have come up with a solution. So just for the checking, may I audible, guys, because I'm looking at only my slide. I can't. Clear, yes. Right? Yes. Okay, thank you. Yes, and these are based on the company codes. So you can see this amide bond formation received a 6 out of 6 votes. The 6 companies participated. All of them, they voted. All the 6 companies voted. They wanted to have a better solution for the amide bond formation. The reaction that are frequently used in the industry. And also you can see that out of 6, 5 votes is received for alcohol activation, particularly for a nucleophilic substitution reaction. For example, amination reaction, that is CN bond forming reaction, as well as the CC bond forming reaction. They strongly prefer this GCS, this Green Chemistry Institute, and ACA. They strongly prefer a better alternative solution for this, for alcohol activation particularly. Okay, and this slide is purely for benefit of the students, and how we are going to activate the alcohol, how you can use the alcohol as an alkylating agent. So first, the alcohol need to be converted into, because this OH is not a good living group, must be converted into a good living group like a tosylate or chloride, or even in the presence of acid, and followed by a nucleophile, say for example amine, then you will have a aminated product. Okay, this is the way you can have an alkylation reaction of amine. Okay, so what are the problems associated with this reaction? Okay, so the problem are you produce a copious acid waste, and also the whatever the amine is formed, this has more nucleophilic in nature than the parent amine. So this whatever amine is formed, this further attacks this compound, and you will have a multi-alkylated product that we call it as over alkylation. Okay, and this also is not a single step process, it's a two-step or multi-step synthesis. These are the problem for using alcohol as a alkylating agent. So what are the desirable approach, what the Green Chemistry Institute wants it? So the reaction must be step and atom economical in nature, and also should operate under environmentally benign condition without producing a copious waste. And if it is a catalytic protocol, this is more advantageous one. So then how can you activate the alcohol without following a classical path? How can you bypass this step? Okay, and yeah, I'm going to coin. I'm not coining this word. This already is known. Just for the students, just a terminology called borrowing hydrogenation. You know this hydrogenation as well as the terms of hydrogenation. This hydrogenation is different than the whatever is known in the literature that's called as a borrowing hydrogenation reaction. So what do you mean by borrowing hydrogenation? For in the presence of transition metal, first this alcohol undergoes dehydrogenation. Dehydrogenation means a removal of hydrogen from this alcohol under oxidant-free condition. So hydrogen will be liberated, and you will have more activated carbonyl compound. Once you have this carbonyl compound, that undergoes a condensation reaction with the amine, say example any nucleophile, particularly it just say as amine. So that undergoes a spontaneous condensation reaction and leading to water as the byproduct, and you will have imine. The moment you have imine, and whatever the hydrogen is liberated in the first step, that will be utilized in the final step by the same metal catalyst, and you will have a selective hydrogenation of imine. You can get the amine. Okay, so directly this overall transformation. So you are going to use amine and going to use alcohol as a alkylating agent, and leading to a selective alkylation. Very important thing is you don't get a multi-alkylated product, and leading to water as the only byproduct. And then yesterday, and the wonderful talk by Jagdish, where he discussed about the amination reaction and catalyst development for heterogeneous catalysts and other thing. Okay, and I hope all the students are a bit inspired by his talk. Okay. And with respect to this, and we have designed a non-phosphine complexes, particularly the NNM system as well as SNM system. These are well characterized. And why you have to move from phosphine ligand to non-phosphine ligand, I don't want to defend on this, because you know these phosphine ligands are tedious to work in this system, because these are highly electron rich phosphine, and you always get its oxidase product. And also people talk about the homogeneous catalysis, or though we talk about the metal is a very important, and ligand also, the cost comes from the ligand side also, right? The moment you talk about the phosphine, the cost shoots up like anything. So if you are looking for a fundamental approach for the application point of view, you must work on non-phosphine ligand, or like other cheapest ligand. So we started working on NNN system, and these are well-defined complexes. This reaction is very clean, and we can handle these complexes and left and right under even aerial temperature without any problem. And also we can scale up the process also, and these are well characterized spectroscopically as well as structurally characterized. And the first interesting thing which I'm going to show is using these complexes for CN bond forming reaction. So this is the first phosphine-free cobalt-based catalyst. This is the first phosphine-free cobalt-based catalyst, and wherein we have used alcohol as an alkylating agent. The reaction follows hydrogen autotransfer or the borrowing hydrogen, which I discussed. Okay, and I don't want to go into detail. Just let me show how the reaction is very facile and all the thing first. And we have taken benzyl alcohol as a benchmark substrate. We have varied the amine part and alene part. We can have a selective N-alkylated product. We can see both the electron donating, electron withdrawing, halides, and particularly the heterohalyl. Heterohalyl fails in the precious metal catalysis. We do get the product, alkylated product in 72% yield. And also this NO also is preserved, highly electron withdrawing group, and also it's more reducible functional group, and which also gives the N-alkylated product in decent yield. And next, we have shown that the substrate scope with respect to alcohol, and both aromatic as well as aliphatic alcohol works very beautifully and leads to an alkylated product. And here again, a selective substrate scope is shown here. A very interesting point here, what I want to mention is not only the aromatic alcohol, aliphatic alcohol. You know, aliphatic alcohol dehydrogenation is much more challenging than the aromatic alcohol, because aromatic alcohol highly activated alcohol. One can get the product, but aliphatic alcohol is very difficult. Okay, so this reaction is also applicable for methanol. So you can have N-methylation of anilines also. Okay, not only the amines, so you can use the benzylamine and also even secondary alcohol also. These are the few selected substrate scope, and both secondary alcohol activated as well as inactivated secondary alcohol also gives a product. Okay, and finally we apply this strategy for this synthesis of very interesting pharmaceutical, industrially important chemical, particularly in the pharmaceutical industries, and few listed chemical I have shown here. Okay, and also the pyrimidine, which is used for the treatment of Parkinson's disease. In one step, you can synthesize this molecule in very good yield. Okay, presently the Serenity Pharmaceutical is working on this system, and this is a company which makes the pyrimidine, and we can make the pyrimidine in one step process. Okay, and this is a typical catalytic cycle, and maybe due to short of time, and I don't want to go into detail. If someone is interested, please do let me know, then we will have a deep informal discussion also. But all the intermediate and then kinetic studies and spectroscopic studies, DFT clearly shows that the reaction follows the metal ligand cooperation approach, and also it follows the borrowing addition strategy, which I mentioned earlier. Okay, and whatever I have shown is only for activated amine, for example benzylamine or aniline thing. And can you use ammonia as a source? Okay, and this is known mostly for the precious metal catalysis. I know that you have heard from the judges yesterday talk, and this is the first homogeneous catalyst, and particularly based on non-precious metal, where you can see the ammonia as a nitrogen source can directly convert this alcohol into amine. And typically, if you want to do this reaction, if you ask any organic chemist, they do say that for this alcohol to be converted into a kind of under Michinobu condition, using a calamide, you need to convert this alcohol into that activated product, and followed by hydrogenation, then you can have amine. This is the only strategy in organic chemistry is known, that's known as a Michinobu reaction. But under one of our catalytic conditions, one of our complexes can perform such kind of reaction under optimal condition. And we have been working with another industry partner. The expanded polymers basically is based on medium scale company, which is located in Bombay, and where they wanted to convert this alcohol particularly, and long range polymer based alcohol, polyhol, and they want to convert OH into NH2, and we have been working with them also. Okay, and this is a kind of okay, so now we have shown that amines as well as ammonia as a nitrogen source. Suppose if we have another alcohol which is in the part of your amino group, okay, instead of taking a simple amine, suppose you take another functional group wherein you have another OH group, can you have a good complexity, and can you have a kind of annihilation type of reaction? So for example, if you take a secondary alcohol, first this undergoes dehydrogenation under our catalytic condition, and followed by a condensation reaction with this NH2, then we can expect to have a kind of amine formation as I shown earlier. And then since another alcohol is present in the system, this undergoes another step, dehydrogenation reaction. One can have a aldehyde. Now we have aldehyde and we have a methyl group, and then under base catalyzed condition, one can have an annihilation type. So if that works, we can have a di-substitutor or multi-substituted pyrrole. Okay, and as we expected, and the reaction works very nicely. Both 1,2-amino alcohol as well as the 1,3-amino alcohol underwent a hydrogenative coupling, that is called acceptolus dehydrogenated coupling, and you can have a multi-substituted pyrrole as well as two substituted pyridine as well as the quinoline with the formation of hydrogen as a co-product. Okay, and this reaction is catalyzed by SNN system based on Popol complex. This reaction follows a sequential dehydrogenation, condensation, and annihilation step, what I shown here. And also selectively, we can make a CN followed by CC1 formation. And this is the substrate scope, and just 1,2-amino alcohol, we can vary both 1,2-amino alcohol part as well as the secondary alcohol part. One can have a 2,5-substituted pyrrole in almost good to moderate to good heal, and with the formation of H2 as well as water. The reaction is very clean, and both the starting materials are abundantly available and highly inert in nature. So we can activate those substrate and can have a value added to this system also. And similarly, the 1,3-amino alcohol also can be converted into quinoline system. And if you ask any typical organic chemist, how do you make this two substituted pyridine or quinoline? First, these need to be brominated and followed by cross-coupling reaction. One can have this, and again, it's a multi-step process. But under our catalytic condition and abundantly available starting material, and one can have a quinoline, a two substituted quinoline and pyridine with the formation of hydrogen and water as the byproduct. And both, we have shown the varieties of reaction for the CN bond forming reaction. And can you apply this strategy for a CC bond forming reaction? Okay, and yes, of course, instead of using amine as a source, you can use a methyl carbonyl as a source of carbon. So as I mentioned in the beginning, first this alcohol undergoes dehydrogenation, you will have activated carbonyl compound. Under catalytic condition, we can have a base mediated cross aldol type reaction or novo type reaction also. Suppose with cyano, we will have that. And then whatever the hydrogen is liberated in the first step, that will be utilized for the selective hydrogenation of the double bond. We can have N-alkylated product, okay, and leading to only water as the byproduct. And if you look at, if you want to do the alkylation of the alpha carbonyl compound, particularly amides, esters, and carbonyl compound, you look at this bronzed acidic of alpha hydrogen. This is a simple carbonyl compound. This is ketone, and this another one is ester and the amide. If I look at the bronzed acidity, for example, you take this carbonyl compound, it just had base and then had alkyl halide, we have alkylation. But such kind of things is not possible in ester as well as the amide, because that alpha as hydrogen bronzed acidity is more for ester as well as the amide. For example, the pK of this particular hydrogen is almost 45 or 46. So you cannot do any alkylation on this part. Okay. So you need to design a catalytic system. Both this amide part also should be activated and alcohol also should be activated subsequently. Then you can have an alkylation of amides using borrowing hydrogen strategy, via borrowing hydrogen strategy. And one of our nickel complexes shown this excellent reactivity towards the N-alkylation of amide as well as the esters. And this is the substrate scope, and this is only the selected substrate scope. You can see this the cyclopropyl ring remains intact in the system, and as well as the bio-derived alcohol, furfuryl alcohol, also can be used as a N-alkylated C-alkylation reaction. And this is with respect to the substrate scope with respect to amide, and not only the acetamide and several amides also can be used for this reaction. And very interestingly, N protected amine. Suppose you have an N Bach protected amine. In that particular case, D protection followed by N alkylation of amide happen. Instead of C alkylation, we have observed N alkylation, and we have been working on this particular system to show a substrate scope for this kind of reactions. Okay. And this is alpha alkylation with respect to ester, and we have chosen tertiary butyl acetate as a benchmark substrate because when you have a tertiary butoxide as a base, and always the competitive reaction is a esterification reaction, that is trans-esterification reaction. In order to tackle that, we have chosen the T-butyl acetate, and then the T-butyl acetate, methyl T-butyl acetate as a benchmark substrate. Under our optimized condition, one can have alpha alkylation on this particular site using a various alcohol, both aromatic and still the aliphatic system. And similarly, this scope of the reaction was extended for methyl aromatic also. I don't want to go into detail. And this next, whatever the fundamental contribution for the C alkylation of amide, ester, as well as N-methyl aromatic compound, and what is the application of this water. So being working at research organization, you also have to look for kind of fruitful applications that would be applicable to the either industry or the society. Then you feel you completely feel satisfied, right? And that is one which always everybody wants it. And we apply this strategy for the CC pump strategy for making self-extinguishing donor. So we have been working with Reliance almost for 5 years, and one of the research program with Reliance is apart from the Ziegler catalysis, and there they wanted to have a kind of donor molecule which showed a self-limiting or self-extinguishing property. And presently they are importing such molecule from China is almost $332 per kg. But using our catalytic system, this cost analysis done by the third party, and it shows only 98%, 98 USD per kg. So you can see there is a huge cost difference. Okay, and presently the Reliance is working on the system using the third party, and they are scaling up the process. Okay. And this is the application of our. Pardon? Yes.
Sorry for disturbance. Last 5 minutes.
Okay, thank you. Yeah, this is maybe it'll not take more than that. Yeah, and we do have another program converting a homogeneous catalyst into heterogeneous catalyst. And yesterday's talk by Jagdish and from the Beller group, and the heterogeneous and the homogeneous catalyst is very interesting thing. Mostly these kind of catalysts used in the electrochemical reaction for OR reaction or HSR reaction, and never been used for a chemical synthesis. And the Beller and Jagdish one which developed this kind of catalyst, and they use for value-added chemical, both pharmaceutical industry and other things also. And it is very important to note that, and when you change the metal precursor as well as the pyrolysis temperature and mode of operation, you will have a different reactive. That is the very beauty of this system. And one can control this also. One can have whatever the catalytic species you wanted to have, you can have it. And we adopted a similar kind of procedure, but we use a different metal precursor, as well as we did not itch the catalytic system, and that shows a very beautiful system. This is a core shell compound, core shell formation, where the core is made up of carbide and the shell is made up of oxide. And this was spectroscopically characterized using various state-of-the-art techniques, and this has been used for dehydrogenation of alcohol, amines, diols, varieties of substrate. And one can think of two things. One is a kind of selectivity. One can use a catalytic system for a selective chemical formation. In another case, you can have a robust system where you can play like a kind of all-rounder. So you can come and bat, ball, keep whatever thing you want to do that. And such kind of system is this one. Okay, so we can use this catalytic system. This is the first ion-based core-shell compound which has been used for dehydrogenation of alcohols, amines, diols, and other things. May I audible? Hello?
Yes, sir.
Hello. Okay, thank you. Yeah, and this reaction is highlighted in several local newspaper as well as other things. Okay, And this strategy was extended for the synthesis of various heterogeneous material, for example, cobalt-based nanocatalysts, manganese-based nanocatalysts, and these are the few reactions which are shown there, and wherein we have been collaborating with Dr. Manoj in this particularly nitrocoamine as well as an alkyne to the double bond, where recently this paper got published in ACS Sustainable Chemistry and Engineering. And this overall, I'm going to summarize this slides, summarize everything, and we have shown that the bifunctional catalysis, how this bifunctional catalysis can be applicable, effectively used for dehydrogenation and borrowing hydrogen strategy for the formation of CC and CN bond formation, particularly amination reactant as well as alpha alkylation of amides and esters. And also we have also shown a translation potential of our fundamental research for the commercial application. We do have a decent patents with one of the indigenous company, and also we do have a decent application on the discuss field like dehydrogenation and CN and CC bond formation. And this is possible by highly energetic students, of which I'm very lucky to have it. And the red black color one already they completed their PhD and they have in a different position. And Garima Jaiswal, and she is a scientist at IOCL now. And Vinod and Manoj are working as a postdoc in University of Florida and South Korea. And other people are NPDF, and presently they are in India. They are working in different places. And now my group is Shinkan, and then we do have very talented student, and they are working on to achieve our goal. And finally, I would like to thank all the funding agencies, like starting from Reliance, Expanded Polymers, and GAIL. These are from sponsored project, as well as the DSD and the CSIR for academic research. And I must thank both ICEEE as well as the CSIR NCL. Most of the work, I would say, is all the work was carried out when I was a scientist at NCL. So I must thank and acknowledge NCL Pune also. And finally, I would like to thank Professor Smita Lile and Professor Manoj Kawande. Now, previously people used to work on the first two transition elements. Now there is a gap because those reactions operate only at higher temperature. By suitably designing a new catalytic system, one can have a good reactivity. So now we are waiting for the back to the future from Manoj and for the next version, maybe in the next year. And thank you for this opportunity. And I will be happy to take a few questions. And thank you for your patience. Yes.
Thank you very much, Professor Balraman, for an excellent presentation and a very detailed talk about how to develop a new catalyst, how to design it, and starting from how to activate alcohols in a greener way. So now session is open for a discussion from audience. If you have any question, please unmute your mic.
One thing.
Yeah, so first question we have from Professor Manoj Kawande.
Yes, hi, Naman. Yeah, very nice.
Hi. Good. Thank you. Thank you, Manoj.
I would like to, as you are discussing about this replacement of noble metals by iron, cobalt, and nickel, and you're also working on manganese.
Yeah.
It's very interesting and very inexpensive metal.
Yes.
That we can use for organic synthesis. As we know that there are multiple oxidation states, and we are not sure that which one will be the active for which reaction.
That's true. Yes.
So my question is that can we control the oxidation state of the manganese? Can we design such kind of catalyst? Suppose we want like +5 state or +3, or we always get the mixed oxidation state when you
yes. I agree.
Comment on that.
Yeah, thank you. Yeah, good. It's really a very interesting question. So first, let me categorize this question into two parts. The first is the homogeneous catalytic system, another is the heterogeneous catalytic system. Suppose you just talk about the homogeneous catalytic system, and these metal salts are commercially available. It's starting from manganese 1, manganese 2, and manganese 3 also. So the moment you have this kind of bifunctional complexes, suppose you design a homogeneous catalytic system where the ligand also takes part, then you no need to worry about the oxidation state, because throughout the catalytic cycle, the oxidation state remains same or not change, right? So with respect to the homogeneous catalytic system, it's not a problem at all, provided you must have a cooperative complex. But when you convert that into heterogeneous catalytic system, is really difficult because, as I said, the manganese, you cannot control the oxidation state. So you will have a manganese 2, 3, 4, and you will have a multiple oxidation state. But you must know that it's not only the oxidation state plays a very critical role in the heterogeneous catalytic system, and the type of supports what you use, that also plays very important role. And what kind of structure you are going to get, that also plays very important role. Suppose you make an individual oxidation state. For example, you have a heterogeneous system where you have a mixed oxidation state. You synthesize same oxide independently, and you just try the same reaction, it will not work. Okay, because you need to have certain kind of balance, not only the oxidation state, it also must have support and structure. All the things plays very important role, and particularly the manganese is very important. Why? Because you all know this manganese is being used for oxidation chemistry, right, and not for the hydrogenation chemistry. Okay, this is kind of switching the reactivity, and as well as the dehydrogenation chemistry. And this first reaction was reported in 2016 by the two groups. One is the Professor Mailstein as well as the Beller, and they are almost at the same time. It came in the 2016, so it's a very brand new reaction. So there are several opportunities to work on the manganese. Yes.
Okay. Yeah.
Yeah. So I hope I answered to a question. Yes.
Thank you. Yeah. But it is always, I feel that, you know, when we are starting preparing this manganese, so we are not sure that at every step, every preparation step, we will get the similar content of manganese oxidation state. For example, once you prepare that +3 +4 is there in the first batch, and when you trying again, maybe it can be changed. So
no, that's the issue. That's correct. I agree.
Difficult to control the oxidation state.
I agree, because that's this kind of problem we face is one of our initial project, and finally we start out on the issue, because this always, whenever you work on the heterogeneous catalysis, and always the reproducibility the issue. So you must have a good experienced person, and the student should write each and everything very clearly. Okay, each and everything should be written very clearly. For example, starting from the gasoline for the pyrolysis technique, whatever the gas, what is the flow rate, and how you are passing to the system, how many hours you are passing, all the things plays very important role. But always there will be a plus or minus 5% difference is there. It will not be an issue. That's what I feel. Okay, but if there is a more than that, and it's a very this need to be taken into account seriously. Yes, that's true.
Thank you, Raman.
But you need to have a good experienced person, particularly to work on the system. That's always is a challenge. Not only for us, it's all of us as overcome this issue, and we sorted out these issues also. That's the reason sometimes it takes slightly longer time when you publish this kind of article. Yes. Sometimes because of these issues.
Thank you, Raman.
Yeah, thank you,
Professor. If there are any question, like if we can have 1 or 2 more questions, we still have few minutes from audience. If anybody
wants students, particularly from students.
Meanwhile, I would like to ask one small question.
Yes, yes, Dinesh, please.
For activation of alcohol using ammonia, there is a selective formation of primary amine.
Yeah.
Have you observed any secondary amine during this?
Yeah, correct. We do have observed a secondary amine, but that's not a great amount. Okay, so the selectivity for this reaction is almost 80 to 85%. We do get a secondary amine. Yes, we do have a secondary amine. And also, particularly for this reaction, we do face a separation issue, because we have been working with the industry partner. They wanted to have a polyhol. So the separation of OH as well as the NH separation is slightly difficult. You are aware about it also.
But that's great to know that it's a selective. And
yes.
Any other question from audience?
Since that's related to the industrial thing, and then we do have a patent, but we have to spend some more time we have to get a lot of clearance from their side to publish the paper. That's all. Keep waiting for them.
Yeah, true.
Yeah.
If there are no questions, I just have one small last question.
Yes, please.
In one of the slides from homogeneous to heterogeneous catalysis using pyrolysis, you have used that catalyst for many reactions and got excellent results. So what kind of ligands in the beginning are very good for making good catalyst?
Oh, no, see, I would suggest, like, not suggest, I would say, like, presently we have bbeen working with phenanthrolene based system. This is the thing, phenanthrolene based system we have been working, and this is exploited by many people. Like they use this system for electrocatalysis, and then this adopted by other group, particularly significant contribution from Beller and Jagdish, and also Kempi and other people also work to mention. And it's shown that there is a recent article by Beller and DFT calculation, so that we need to have a certain parameters. So this got published in Journals of ACS, not Journals of Catalysis, and I don't have that particular reference. It's the combination of experimental as with the DFT studies, and what it shows that you need to have a kind of rigidity in your system. For example, instead of bipyridine, instead of phenanthrolene, if you have a bipyridine, you will not have the similar reactivity. You will not have any reactivity also. So when you have a phenanthrolene system, which is the planar and two nitrogen will be very close proximity with the metal center, that gives a very extraordinary stability as well as the reactivity. Okay, and that's what we understood, and we have been extending this approach for the saline-based system also, wherein the saline also that NNN, which will be very close proximity to the metal center. So you should not have a flexible ligand like a bipyridine or pyridine. Those things, even terpyridine also is not working. So you do have some reactive, but not up to the mark with respect to the phenanthrolene. Phenanthrolene is a good system, as well as a saline-based system also you can have such kind of reactive. This is by experience. So, but several studies need to be performed, then must know the thing.
Yeah, thank you very much, Professor Balawan, for such a nice lecture, and also for
and thank you for Dinesh. That's really, I think, good, and
yeah. So, on behalf of organizers, I would like to thank you.
Yeah, Dinesh, sorry, yes. I think there are some one or two questions. So maybe you can see in the chat and.
Okay. Yeah.
Okay, can you, because I don't know how to look at the chat box. Can anybody, Dr. Dinesh, can you please read it? I can.
So there is one question from Mr. Gajanan Shinde.
Yes.
Selectivity of ligand depends upon which factor? So that's one of the questions.
Selectivity with respect to the homogeneous system, I believe, right?
Yeah, I guess so. Yes.
Yeah. So basically, you need to have. So our aim is to design a catalytic system based on a tridentate system. Okay. So tridentate means one ligand and another ligand, and my mouth is another ligand. Why we are choosing that kind of system is, for example, you just imagine I have a mobile, this is a metal. I can hold my metal like this. This is one ligand, it coordinates like this. Another ligand coordinates like this, my mouth. Okay. All the three ligands will be in the same plane. Okay. And we must have this. Even this comes out also, we have the metal rolled by your mouth as well as another ligand. Okay, that gives the stability. So you will not have a metal leach out from the metal center. Okay, but another type of coordination is like this. So you hold like this, my mouth and another one. I assume there is two things coordinate. Another can come from other side. That is called Scorpion coordination. Okay, so you need to choose a system wherein these all three ligands will be in the close pocket, and then we can have a planarity. And if you have a kind of flexible thing, then one will be like this, another one can like this means, and then you will not have a reactivity. That's a basic principle you must have. The ligand should be in the close proximity, wherein it's coordinated to the metal center in a meridional operation. That's all. And also you need to have some active center where is NH or metal ligand cooperative. In order to happen, you must have aromatic to diaromatic or amidol to imidol. These two should be there. That's all. These are the two parameters we always keep it in mind.
Thank you very much for detailed answer. There's one more question in chat box. Sir, can you please explain metal center catalysis, and is the type of ligand chosen for this type of catalysis plays a major role?
Metal center catalysis. Metal catalysis, you just take any well-known reaction, the Nobel Prize reaction, even it's a, for example, metathesis reaction. So only the metal center, only the reaction happens only at the metal center. And as well as cross-coupling reaction. Cross-coupling reaction, palladium is the only active center. And ligand, what the ligand does, it comes out from the metal center. And a typical organometallic people, they say that if it's a coordinatively saturated species and one of the ligand comes out, you make the vacant site, and then the substrate activates by the metal complex. Everything will happen at only the metal center. What the ligand does, ligand just gives the stability, or it will come out from the metal center. Such kind of ligand system are known as metal center catalysis. This has been known in the several years also. Okay.
True. Yes.
Yeah. So these are metal center. I'm talking about the only homogeneous catalysis. Only these are metal center catalysis. Okay.
So we will take last a question from Dr. Jagdish. He just posted message in chat box. He would like to ask one question.
So Jagdish, good.
Yeah.
I'll mail this separately also. Good.
And after that,
it was a wonderful talk. And yesterday it was a very wonderful talk. And indeed, I'm privileged to. I mean, first I would like to thank Manoj. Yeah, good to see you.
So how are you?
Fine, thank you. Good.
Yeah, actually, I didn't log in. My student was logging. Just
yeah,
I was watching.
Please.
So actually, this manganese, it's very interesting.
Yeah.
So you know the heterogeneous manganese is even the
I see Manoj is pushing me a lot. Actually, you wanted everything is ready now. So only thing is we have to communicate that.
Let's complete the story as early as possible.
Yes, please.
Yeah. So I think this is a very good actually. So have you observed with the hydrogenations? Why? Because we have a very good manganese catalyst for hydrogenations actually.
Yeah.
So have you tried with hydrogen?
Yes, of course. The hydrogenation is working fine for this.
So it's working with hydrogen also.
Yeah. No, this year we also performed under float condition. So
okay.
Yeah.
Yeah, manganese is very interesting compared to other metals. Right
other
now
metals, yeah, that's true. Thank you for your compliment.
This is very nice. So yeah, I listen sometimes your text is very nice, huh? Yeah. So
thank you.
You're using a magic technique, pyrolysis, huh? Very nice.
Yeah, thank you. It's adopted from you.
Nice talk, huh? Yeah.
Yeah, thank you.
Thank you, Dr. Jagdish, and thank you very much to the speaker. Without taking
thanks, Dinesh, huh?
Yeah. So I would like to mention, if you have any other question from the audience, you feel free to contact a speaker through their official mail ID. So on behalf of conference organizer, I would like to thank Professor Balraman for such a nice talk with a detailed explanation of the catalysis as well as its application part. Thank you very much, sir. And it was our great pleasure to have you as a speaker for today's last session. Thank you.
Thank you, Dinesh, for wonderfully conducting this section, and as well as once again I thank Manoj for this good platform to interact with the eminent people in this particular area. And thank you. I'm really happy to be a part of this thing. Thank you, ma'am. Thank you.
Yes. So now we would like to proceed for the next talk from Professor B.M. Bhange, sir. So let me first introduce our next speaker for today's session, and last speaker, Professor B.M. Bhange, sir. He is currently working as a professor of industrial and engineering chemistry, and he is also a dean of infrastructure and campus development, and working at Department of Chemistry, Institute of Chemical Technology, ICT Mumbai. And today, sir will be delivering talk on green synthesis of nanomaterial and its application in organic synthesis. So let me briefly introduce sir. So Professor Bhange sir has obtained his doctoral degree from CSR National Chemical Laboratory, Pune in 1995. And afterwards, he spent several years in Japan at Tohoku University and Hokkaido University at various positions. Then he joined ICT as a full professor of industrial chemistry in 2003. And during 2009 to 14, he was also a head of Department of Chemistry. And as I mentioned, currently he is also Dean at ICT Mumbai. So Professor Bhange sir has contributed in the area of catalysis for activation of small molecules like carbon dioxide, carbon monoxide, and hydrogen for various reactions. He has developed novel strategies for various reactions like Hague coupling, Suzuki coupling, Sunogashira coupling reaction, and their carbonylative forms as well. Hydroformylation and aminocarbonylation and alkoxycarbonylation, so which is the extension part of this Hague, Suzuki, and Sunogashira, you can imagine. And then he has also a lot of contribution in amination and hydrogenation reaction. So his work is also focused on developing strategies for catalyst product separation and catalyst recycle. He has developed several homogeneous transition metal-based catalysts for these reactions and solid-based catalyst for carbon dioxide fixation reactions. He is also active researcher in the field of nanoparticle synthesis and its application in organic reaction as well as in other reactions. His research group is also working on enzymatic catalysis. So with overall broad area of catalysis, today he's going to speak about his recent contribution in area of nanocatalysis and other aspect of catalysis. So far, Bhange sir has published almost 394 research publications in reputed international journals with 36 patents as well. So he has received more than 16,000 citations with H index 56, and so far he has guided 41 doctoral students and currently guiding 20 research scholars for their doctoral research. And it's my great honor and great pleasure to introduce, and I'm also one of his PhD student from ICT Mumbai. And now onwards, I would like to invite Professor Bange sir to deliver his talk in this conference. Welcome, sir.
I hope all of you can see the slide.
Yes, sir. Slide,
okay.
Now it's full screen.
Thank you, Dr. Dinesh, for kind introduction. It's a really wonderful conference to see various top-level researchers working in the field of nanomaterials and catalysis, and come to know lots of development about this area. So I focused myself today on metal and metal oxide-based materials. And I will also discuss about how this synthesis can be green, as well as we'll see their catalytic applications. At ICT, we are working on different areas like green chemistry, homogeneous and heterogeneous catalysis. We had extensively worked on CO2-based applications, reactions using supercritical carbon dioxide solvent. We also prepare and characterize different types of organometallic complexes for catalytic applications. We focus on separation technique development for homogeneously catalyzed reaction. This technique can be biphasic, supported liquid phase, and many more. Then our main focus is to develop catalyst for different types of organic synthesis. We focus on how we can bring down the multi-step synthesis into few-step synthesis. So it's typically green chemistry-based concepts. And while doing so, we also use non-conventional techniques like ultrasound, microwave-assisted synthesis, and material synthesis. As you know, there are different types of nanomaterials, and their origin can cause physical properties to change. For example, if we bring material to nano size, we get large fraction of surface atom, which is very important for catalytic behavior. And that is a major advantage of using nanomaterials for catalytic application. This also results in large surface energy, spatial confinement, and reduced imperfection. All these properties will lead to better catalytic improvements, and that is what we are going to discuss in coming slides. So while doing so, if we want to develop nanoparticles, there are also challenges. For example, multiple modality and functional nanoparticles we want to develop. These nanoparticles have tendency to get adsorbed, or they get agglomerated, or they can do many other toxic effects. All that we have to consider while developing these materials. There are two major methods which are reported or which are well known in textbook knowledge. That is, when you can prepare nanomaterial from top-down approach or bottom-up approach. In top-down approach, we are taking bulk metal to powder and powder to nanomaterial. So we typically use ball milling method, melt mixing method, laser ablation, electric arc, ion milling. So these are mainly physical or mechanical based methods. While chemical methods starts with atoms, so Solgen method, solvothermal reduction, chemical vapor deposition, laser pyrolysis, electrochemical method. Out of that, we work on solvothermal reduction and electrochemical, but today I will mainly focus on solvothermal and reduction method. And broadly, if you consider, most of the physicists prefer top-down approach, chemists prefer bottom-up approach. We can say that because typically we observe this classification when you look into the literature. I will first explain about the templated procedure which we follow for preparation of nanomaterials. So based on this templated procedure, we have prepared different types of material. For example, I have taken example of preparation of cuprous oxide. Cuprous oxide is very important and their nanoparticles are also important because they find several applications which I had mentioned here, like solar energy, gaseous sensors, electrochemistry, catalysis, and many more. So when we started the work in those days, most of the wet chemical reduction methods were known, electrochemical methods known, these type of methods were known. But most of them, they have disadvantages like use of toxic or expensive reagent, longer reaction time, high temperature. There was also need for calcination. And last part is very important. That is what we have focused our method because they affect the catalytic performance. For example, if you look for the methods of nanomaterial synthesis, they require base, stabilizer, capping agent, reducing agent. Now, if you are adding so many chemicals to prepare nanomaterials, these chemicals interfere in their catalytic activities. So what we have done, we have developed method in which these chemicals will be reduced or minimized as much as possible, or we have used such a chemicals which will not interfere in their catalytic performance. So our goal was always to develop non-toxic or less toxic reagent, shorter reaction span, no need of additional reagents. As far as possible, if we can avoid calcination also, that also we have seen in some cases. And for that purpose, we use different techniques. For example, here I had mentioned microwave. So microwave can give you quick heating, and that also leads to the good preparation of nanomaterial. For example, I have taken copper acetate, added benzyl alcohol. So our invention lies in addition of benzyl alcohol, because benzyl alcohol plays a role of capping agent as well as fuel, what they say in the preparation of nanomaterial. And as it is alcohol, it can be act as a solvent. It will never interfere in your catalytic performance, and that is the benefit of using benzyl alcohol. So just we did it microwave heating at 600 watt. You can see that depending on procedure, which is mentioned in that original publication, you can get copper 2 oxide also and copper 1 oxide also. And of course, we have characterized that using standard techniques like XRD, EDS, and confirms that we got Cu2O. Look at the TEM image. We could able to obtain the copper oxide nanoparticles in the range of 5 to 20 nanometers. HRTM also confirms even 2 nanometer copper oxide nanoparticles were observed. So conclusion, we can say that this templated preparation method is very simple. So let us see how we can use it further. So once we develop this method, we have prepared different varieties or different mobs of this particular method. For example, copper acetate and 1,4-butanediol. So what I have changed here, instead of benzyl alcohol, I have taken 1,4-butanediol as a reagent here and did it microwave heating and monitor it with respect to the heating wattage. We can see that at 600 watt, we get nice nanoflowers, microparticles. This microparticle contains nanoparticles of copper oxide. And this was used for Buchwald-Hartwig amination reaction. So this amination reaction worked very well using nanomaterials. 80 degree 24 hour under nitrogen atmosphere, we can very easily do Buchwald-Hartwig amination using copper oxide. Now, when you change your solvent from 1,4-butanediol, which was used here I use 1,3-propanediol. The change in solvent also changes the morphology of copper oxide nanoparticles. So we did exactly same. Now we could able to get different type of copper oxide nanoparticles, and that we have tested for Sonoga-Shira coupling reaction. So reaction is mentioned here. We can see that Sonoga-Shira coupling reaction with terminal alkyls. When we look for the literature methods, before our work was published, there were many methods were known. Most of these methods were based on palladium cycle, palladium on carbon, or palladium homogeneous complexes. Some heterogenized palladium complexes were also known. There was one report on copper iodide cryptad, which was again a complicated system. So we replaced such expensive catalyst like palladium with simple catalyst like copper oxide nanoparticle. So works at 90 degree right-hand amine base 24 hours, you can get very easily sono-acyl coupling. You can see here acetylene and benzyl chloride and nanocatalyst. We can get the good results for many different types of substrates. You can have substituents on both the types of coupling partner. You get the better results. After copper oxide nanoparticle synthesis, we have focused on nickel oxide nanoparticle synthesis. Nickel oxide nanoparticles are important because they find applications in antibacterial and antioxidant agent in biosystems, electrochemical supercapacitors as an anode material for lithium-ion batteries. They are also catalytic decomposer, dye-sensitized photocathodes, and many more. They are also used for wastewater treatment to remove pollutants as well as catalytic application. So the method is same. What we did now, earlier we took copper acetate, now we have taken nickel acetate. Microwave heating, here you need to do the calcination because after microwave heating you are getting nickel oxide powder, and at appropriate calcination temperature you can get nickel nanorods. So you can see the procedure. Nickel acetate in 1,4-butanediol, microwave heating, you get nickel hydroxide, and after calcination, we get nickel oxide nanorods. So they were characterized using FEG cell. We can see the nickel oxide nanorods which were formed. And we use this nickel oxide nanorods for preparation of benzimidazole. You can take orthophenylene diamine, OPD, which is popularly known as OPD. So orthophenylene diamine and benzaldehyde. Both of them were coupled together in presence of nickel nanorod in ethanolic solvent, 60 degree 4 hours, and you can get benzimidazole very easily. If you take excess of benzaldehyde, what will happen? You get substitution for one of the nitrogen group here. You can see that that gets in a 90% yield. So we get 1,2 disubstituted benzimidazole if we change the ratio of coupling partners. So based on same logic, we have also prepared benzoxazole. So instead of this NH2, we have O here, and we can get benzoxazole. Same way, instead of OH, if you take SH, you can get benzthiazole. So such type of aromatic heterocycles you can prepare in presence of nickel oxide nanorods. We did scale up of this reaction also, and we did it at say 15 gram scale. We could able to get same yield, 82% yield of benzimidazole. And as a curiosity, we have compared nickel nanorods with bulk nickel oxide. We can see that the difference in the yield. Because nanoparticles gives those advantages which I had mentioned earlier, we could able to get higher yield using nanoparticles. Now, copper oxide nanomaterial, earlier I used microwave as a driving force. Now I have used sonication as a driving force, and I could able to obtain good nanoflowers of copper oxide. And these copper oxide nanoparticles obtained from sonication were also effective for Buchwald-Hartig combination reaction. And I have compared them with nanoparticle and commercial copper oxide. And you can clearly see the difference when you use the copper oxide, which is at the bulk scale and nanoscale. Nanoscale is always giving better improvement and better performance as compared with the conventional. Thereafter, we have prepared magnetically separable iron oxide nanoparticles, and they were found to be effective catalysts for acylation of alcohols, phenols, amine, and most of these were prepared using sonication energy source and under solvent-free condition. So we have taken here phenol and acetic anhydride and NaNoFe2O3, which is magnetically separable, solvent-free, 1 hour, room temperature. You can see that very easily we get acylated phenol, and catalyst can be separated very easily by putting the magnet there. And such type of catalyst can be very easily separated and recycled. So here are more details about the reaction. We can see that catalytic concentration, typically optimized catalytic concentration is 5 millimole %, 1 hour. 92% yield we can get and turnover number of 18.4. This occurs at room temperature. We did substrate study also. Different types of phenols were tested for acylation, and in all cases we got reasonably good yield. Instead of phenol, later we took alcohol, aliphatic alcohol, and again with nano iron oxide, you can do the acylation. In a way, you can couple acidic anhydride with alcohol very easily. But in this case, yields are lower as compared with the phenol. You can also couple acylation of amines, aromatic amines like anilines, and you can do it very easily using nano iron oxide catalyst. As a curiosity, we had also interest to see whether precursor can play a role, because if you look for all the previous methods, we have used acetates. Fine. So whether such type of precursor can play a role on the morphology of nanomaterial. That was our goal to see that. So we started with palladium acetate precursor. And palladium acetate, using similar methods, gives us good nanorods. You can observe here nanorods, and these nanorods containing palladium nanoparticles. So you get palladium in nano form, but they are supported on the nanorods. If you use, instead of palladium acetate, palladium chloride, you never get the nanorods, but you get the spherical nanoparticles. Again, you can prepare that, but just by the changing the precursor. If you take, instead of palladium chloride, if you take bromide, so this anionic part of your metal also plays a role on the morphology of the nanomaterials which you get. So here firm leaf-like structures we can observe using palladium bromide. So you can see that palladium acetate, palladium chloride, palladium bromide. So change in the other counter anion, you get the change in the morphology. We have used this for typical Suzuki coupling reaction. Again, it works with simple base like K2CO3, ethanol, water, solvent system, 60 degree 8 hours. It gives excellent coupling, Suzuki coupling. As a curiosity, we thought that let us check whether shape of these nanoparticles has any effect on the nanomaterial synthesis. You can see that even partial conversion or full conversion, we didn't observe any effect of the shape with respect to the Suzuki coupling reaction. I had earlier mentioned about the nickel oxide nanoparticles. We didn't explore well in those days to get for the other reactions. So we thought that let us check this application of nickel oxide nanoparticles for other reactions. And we have tested it for 3-component coupling reaction between amine, aldehyde, and alkyne. You can get propargyl amines very easily using the nickel oxide nanoparticle. You can see the typical reaction conditions 120, 22 hours and toluene, and you can get the yield of propargyl amines in a reasonably good quantity. We have compared that with nickel oxide bulk. You can see that here difference is large, bulk and nanoparticle. If you take bulk, it is just 30%, and if you take nanoparticle, it is 90%. So it clearly indicates that nanoparticle has a role in getting the better performance. And of course, other nickel precursors like nickel oxide, nickel chloride, nickel nitrate, they found to be ineffective for this reaction. Nickel oxide nanoparticles were also tested for 4-component coupling reaction to prepare pyrols. Nickel oxide nanoparticles, room temperature, and these are the coupling partners. You can very easily get the pyrols, and these pyrols were prepared in a reasonably good yield. You can find more details in the publication which is mentioned there. Then, copper oxide nanoparticles, which we had prepared earlier, can be used for application of beta-enamine synthesis. So you can see here it is a beta diketone, and you can easily prepare enaminones with just one carbonyl group. Other carbonyl group remain as it is, and such reaction can happen using copper oxide nanoparticles at 60 degrees. No need of any solvent. You can have alkyl or alkoxy groups as a substituents on either side. You can get reasonably good yields. After preparation of nickel and copper oxide nanoparticles, we have focused our attention on preparation of magnesium oxide nanoparticles because they are also important, finds lots of applications in pharmaceuticals. So we use same approach. We have taken here magnesium acetate and benzylamine. Earlier we tried with benzyl alcohol. Benzyl alcohol can act as a capping agent as well as fuel. Amine also can act as similar manner. You can see that after interaction with benzylamine and microwave irradiation, we can get the magnesium hydroxide, and which you can do the heating after this calcination of magnesium hydroxide nanoparticles, you get magnesium oxide nanoparticles. And these magnesium oxide nanoparticles were used for preparation of formamides. So you can take amine and formic acid and use magnesium oxide nanoparticles under microwave irradiation. Within 1 to 2 minutes, you can get the formamides in reasonably good yield. Same way, nickel oxide nanoparticles, which we had prepared earlier using microwave, can be prepared using sonochemical technique. But in this case, we have used cyclodextrin, which can act as a capping agent, which avoids the agglomeration of nickel oxide, nickel hydroxide nanoparticles, and they were calcined to give you nickel oxide nanoparticles. Using this, 3-component coupling reactions we have performed, and it is performed from benzene and aldehyde and ammonium acetate. We can get 2,4,5 tri-substituted imidazoles in a very simple fashion. If you try to prepare this using conventional organic chemistry, it's a typical multi-step synthesis, whereas this can happen in just one step using nickel oxide nanosheets, which we had obtained using this method. And important point is, this cyclodextrin also plays a role in type of nanomaterial which you get. We got nickel oxide nanosheet with nickel oxide beta cyclodextrin. Alpha and gamma gives different types. So you can see that 120 degree, 60 minutes, you can get 97% yield of the 2,4,5 tri-substituted imidazoles. You can see various types of such type of substrates were prepared in reasonably good yield. Thereafter, we thought earlier we had prepared iron oxide based magnetically separable nanomaterial. So we thought we can prepare another type of magnetic nanocatalyst, that is copper nickel ferrite, and you can prepare that and using the method which I had mentioned earlier, and we can use it for selective synthesis of benzoxazoles. So how we have done this? You can take metal nitrate like copper nitrate, citric acid, urea, stir it, you get sol. Then after sol, you can get gel, and heating to dryness, you get dry powder of copper nickel ferrite, and you can do the calcination, you get the corresponding material. And you can see that here we have prepared very easily benzoxazoles using this method. The advantage of this method is we don't use any noble metal, easy recyclability, very high atom economy, and use of alcohol as an economical source. So lots of substrate with different types of variation on both the sides you can prepare once you optimize this particular method. Afterwards, we had prepared ultrasound-assisted copper oxide nanocubes, and very nice nanocubes were obtained using another method which we have developed. This method, these nanocubes which we had obtained, were used for synthesis of quinazolines. So you can see here nanocubes which we had got. You can do the ultrasonication, and finally you end up with nice nanocubes of copper oxide, and these nanocubes are used for quinazolone synthesis. So This is typical synthesis of quinazolines, and we get reasonably good yield, say 92 to 87% we can get. You can have all types of substitutions on aldehyde part as well as other part. Same way, copper oxide nanoparticles we have prepared, and since copper oxide is not magnetically separable, we have supported them on the iron oxide. So we got Cu2O, Fe3O4, which is magnetically separable and reusable nanocatalyst. And again, it was used for quinazoline synthesis, but coupling partners are different. You can see here coupling partners are different. Here we have taken simple coupling partner like benzylamide. And sodium azide is of course required during this synthesis, and you can get good yield of quinazolines using magnetically separable copper oxide, which is supported on iron oxide. We also thought that let us have another form of catalyst in which metal is in form of nanoparticles. Eventually it will happen on graphene oxide. So we have taken palladium metal ions, which can act as an efficient catalyst for alkoxy, amino, and phenoxycarbonylation reaction. This work we did with collaboration with Professor Sasaki from University of Tokyo under Indo-Japan J-Space project. The method which we have used for preparation of this catalyst involves the graphene oxide, and we are anchored here ionic liquid, and this ionic liquid can act as some kind of ligand to hold up your palladium chloride, and this palladium chloride during carbonylation process will form PDE in nano form, which is hold up on your graphene oxide material. And you can do the reactions which I had mentioned here. You can take iodobenzene, carbon monoxide in presence of base and solvent. You can have lots of substitution on iodobenzene. If you couple that with alcohol, you get esters, amides, and phenoxy esters. So such things are possible using this type of catalyst. There is one more interesting study which we had observed while preparation of NANO-SA-based nanomaterials. And these NANO-SA-based nanomaterials, I will tell you the observations while preparation of NANO-SA. This catalyst, NANO-SA catalyst, was used for synthesis of alpha hydroxyamides via reduction of unusual class of beta ketoamides. So you can take such diketone, and out of that selectively you can reduce this part of ketone and using sodium borohydride. Please note that if you don't use any catalyst, reaction doesn't work. Just sodium borohydride will not reduce. If you prepare ceria as a catalyst, only then it works at methanol and room temperature at 30 minutes, you can get the alpha ketoamides. Now, when we prepare the nanocatalyst, that's what I would like to mention, that the reducing agent, capping agent, and temperature played a role for the shape which I had obtained of the nanocatalyst. And these shapes I had mentioned, but I will tell you the SEM pictures of all these shapes so that you will understand that. Suppose I take ceria, I can get nanobelt if I use succinic acid as a capping agent at 35 degrees centigrade. You can see nice nanobelts of ceria is formed if I use succinic acid at 35 degrees centigrade. Now, if I heat this to 70 degrees centigrade, this nano belt will form into nanorods. Of course, little bit higher size. Instead of succinic acid, if I take adipic acid, I get the micro rods, which I can show it here. If you take instead of adipic acid, oxalic acid, all these are dicarboxylic acid with the variable chain length, and you can see that the nano material which you are obtaining are changing their shape based on the molecule which you are using as a capping agent. Now you can get nanoflower instead of adipic acid or succinic acid, you get oxalic acid, you get nice nanoflowers of ceria. Same way, succinic acid if you heat it further to 140 degrees centigrade, those nanorods were broke and we observed nanocubes of cilia. You can see the nice nanocubes of cilia obtained using such change in the procedures. If you take succinic acid at 110, you get the nanosphere. So if you monitor your process while synthesizing the nanomaterials, you can see the different shape changes happens depending on the capping agent, depending on the temperature. By the way, when we use these materials as a catalyst, they remain in their original form. Even after third recycle, this same was taken, you can see that they remain in their original form. So they doesn't agglomerate. And that is what is required when you develop nanomaterials as a catalyst. So this catalyst, their shape, as I mentioned there, their shape is mentioned, XRD also remains same. So there is no change in XRD, even you do the recycle study. So it indicates catalyst retains its shape and size. Nanosphere cilia, you can use for hydrogenation of alpha ketoamide synthesis, which I had mentioned, methanol and room temperature. So this is good. Heterogeneous recyclable shortages, green solvent, and you do the chemoselective reduction in less times. Now, I had showed you several same images and several different sizes of the cilia, and we have compared their yield with respect to the formation of a reduction process. We can see here bulk and nanoflower yield doesn't affect too much. Nanocube at 8 hours, again more or less same. Nanosphere 2%, 30 minutes, 99% yield of the product. Of course, I changed the catalyst loading also. You can say 5 millimole, 81%, 10 millimole, 10 mole percent, 94%, 50 millimole, 99%. So these processes were optimized with respect to the nano-size materials. Preparation of gold nanoparticle, you can find lots of literature. So we thought that let us prepare gold nanoparticle using our methods. So we have prepared gold nanostructures using ketones, and we have tested its catalytic activity towards reduction of para-nitrofenol, because para-nitrofenol is quite often observed in the pollutants. Whether we can reduce it, that is also important. So you can see here gold nanoparticles which we had prepared using our methods. It can reduce this nitro group to NH2 group very easily using gold nanoparticles. So what the study we did while preparing this gold nanoparticle, our capping agent was ketone. So cyclohexanone, then beta diketones. Then these beta diketones were separated by more carbons, or we can take cyclohexane 1,4 ion. Check the different types of ketone and shapes of the nanomaterials. So if you have just one ketonic group, it is 75 nanometer. If you have two ketonic group, it brings down to 46 nanometer. Doesn't matter. And if you have such type of ketonic group, they are forming more smaller nanoparticles, say 33 nanometers. So point is, if you change your capping agent and if you change the functional groups on the capping agent or number of functional groups on the capping agent, that also affects the shape and size of your nanomaterial. You can see further here, cyclopentane 1,3-dione, cyclopentanone, and many more. So shapes are changing, size are changing. So this is summary of just now what I had mentioned about this gold nanoparticle synthesis. We have studied LSPR study properties with respect to the gold nanoparticle, and we can see the typical UV spectra. You can see the change in the color with respect to gold nanoparticles when you get the change in the shape and size of gold nanoparticle. Nice change in the colors were observed depending on the size and shape of your gold nanoparticles. Now this is the monitoring of the reaction of para-nitrofenol. you can see very easily decolorization of this yellow solution of nitrophenolate to a phenol group to the aminophenol group. Can monitor very easily. Visually also you can see this particular change. Interesting observation in this particular study is that when we do the recycle study of gold nanoparticles, fresh catalyst was less active than the recycled catalyst. After recycled catalyst, probably we are getting more active form. During the subsequent recycles, we are getting better catalytic performance. Then, same reaction we have studied, but with respect to different types of method for the preparation of gold nanoparticle. And we have prepared here spherical, mixed polyhedral, truncated cubes, cubics, tetrahedral, octahedral gold nanoparticle, depending on the capping agent which we had studied. We had earlier mentioned that we had prepared quinolines molecules, and same reaction we continued, but with the different types of coupling partner. We want to have some simple coupling partner, cheaper, inexpensive coupling partner, in-reactive coupling partner, but final goal is to prepare quinolines. So here, in this case, we had chosen 2-aminobenzyl alcohol and with simple alcohols, and you can take magnetic copper nickel ferrite nanocatalyst, which we had prepared earlier. So no hydrogen acceptor is required. This is heterogeneous recyclable catalyst. We showed 28 examples and with up to 94% yield, and we could able to achieve higher scale synthesis also using this type of catalyst. So these are those nickel, copper nickel ferrite magnetic nanocatalyst. This is EDS spectra, which shows that all these metals were uniformly distributed on the catalyst support. XRD was also confirmed with respect to the recycled catalyst and fresh catalyst, which indicates that catalyst is stable under reaction conditions. And this catalyst was tested for different types of substrate. You can see here many substrates we have prepared using this developed methodology. Recently, we have developed copper aluminum hydrotulsides also, and we could able to convert fructose to 2,5-diformylfuran using this copper aluminum catalyst very easily in one-step way also and one-pot way also. There are two ways which I had mentioned here. You can use oxygen DMSO, and the catalyst you can have one-pot, one-step synthesis of fructose 2,5-diformylfuran, or you can do with two steps also, using step 1 as dehydration under nitrogen atmosphere in DMSO, and afterwards steps 2 as oxidation with oxygen with DMSO. So you can prepare that. The catalyst was prepared using conventional technique, like we took metal nitrates and co-precipitation, filtered and dry and calcined the final form of the catalyst in the nano size. And you can see that after variation between copper and iron catalyst, you can get the different types of yield with respect to this reaction, but optimized yields are given. This is our optimization study, and you can get the catalyst very easily. If you want to do this one pot, this is more important because no one showed earlier how you can do it one pot, and we did it using this particular catalysis. So this catalyst is again recyclable. We have recycled it many times. So conclusion for this particular study, we have synthesized the copper cobalt aluminum hydrotulside, and which was used for dehydration of fructose to HMF and oxidation of HMS to DFF, and also in one-pot fashion. Next reaction we have studied using biomass derived 4-hydroxymethyl furfuran to produce 2,5-methyl furfuran using ruthenium, zirconium, MCM41 catalyst. Again, this catalyst we have prepared, although this is heterogeneous, finally your ruthenium is in nano form, and that's why I mentioned here. And we have got this catalyst from our collaborator, Dr. Parida from SOA University at Bhubaneswar. So we could able to convert HMF to DMF very easily using this catalyst at 160 degree, 15 bar, and THF as solvent in just 1 hour. So this is the typical method for preparation of ruthenium supported catalyst. Why this particular reaction is important? Because you can see that there are several possible products. Out of that, we could able to very easily control our selectivity towards DM. You can see that different types of catalyst were used, different conversions, and we have optimized the selectivity based on the parametric effect. And all parameters for this reaction with respect to time, catalyst loading, and temperature, we have studied to get the specific selectivity for synthesis of TMF using ruthenium catalyst. Here also, we perform whether we can prepare DMF directly from fructose. Yes, you can do that. You can start with fructose. Step 1 is dehydration. You can prepare 5-hydroxymethyl perfenol, that is HMF, and you can do the hydrogenolysis to get the DFF. So thereafter, we had prepared graphene oxide catalyst, which I had mentioned earlier. Instead of palladium, now we have supported ruthenium. And this was used for levulinic acid, which is also a biomass-derived platform molecule to prepare the pyrrolidons. And using such type of graphene oxide ruthenium anchored catalyst, you can very easily prepare levulinic acid to pyrrolidons. In this case, we had different types of substitutions which we had taken. This R can be alkyl or aryl. We had taken 18 examples of different pyrrolidons for this particular synthesis. We got very good yields, catalyst is recyclable, and we could able to get wide substrate scope for this reaction. This is the typical ruthenium GeoIL catalyst synthesis, which is similar, exactly similar to what we did in case of palladium GeoIL catalyst. And this was that reaction: benzylamine, levulinic acid, catalyst, time, temperature, solvent, hydrogen pressure. These parameters we had optimized to get 1-benzyl 5-methyl pyrrolidone to on. So all the optimization studies with respect to catalyst, solvent, we can see that we could able to get 93% yield very easily. These are the optimized reaction conditions. And you can see the substrates. The wide range of substrates of these pyrrolidons were prepared using this particular methodology. 130 degrees centigrade under 15 bar hydrogen pressure. Whether we can prepare fructose to pyrrolidon, that was another question. So yes, you can do that. You can take fructose. Levulinic acid is formed after if you do the acid treatment, and levulinic acid can go to the pyrrolidon. So we did it in one step fashion also. Also, we did it biomass waste to the pyrrolidons very easily using this particular. This is the typical reaction mechanism, which I would not like to discuss. Catalyst is recyclable. We tested it up to 6 recycle. Further was also active. So finally, I would like to conclude my talk with following important statements. That is, nanomaterial synthesis can be simplified using capping agent containing hydroxyl group. Use of metal precursor decides the shape and size of the nanomaterial. Use of solvent also plays a significant role in the synthesis of nanomaterial. Your catalytic activity will always depend on the size and shape of the nanomaterial which you had prepared. And quite often, they're found to be superior than the conventional catalyst which are prepared. Finally, I would like to thank you for your patient hearing, and I will be happy if you have any questions to answer.
Hello, Dinesh, are you there?
Yes. There's some network issue, but now it's okay. I got reconnected. So thank you very much, sir, for excellent presentation and very good information about all the work we have done in our group previously. And now the session is open for discussion. So I'd like to ask participant to ask questions.
Hello, sir. This is Brijesh from Novartis. Brijesh Gadu from Novartis. So I would like to ask one question to Professor Bande.
Yes.
Hello.
Yes, I'm hearing.
Yes, sir. So you utilized the ruthenium nanoparticles or ruthenium-based nanocomposites for the synthesis of pyrrolidones by using
Yes.
levulinic acid.
Yes.
So, is there any possibility that this particular catalyst can be used for the levulinic acid to gamma lactone, because it's a hot topic reaction in the organic synthesis?
There are already some reports on this, and we have not explored this for that particular reaction, but it is possible. We have to explore that. And the reports are there. I'm not saying that ruthenium is known for that synthesis.
Yes, sir. Yes, sir. That's right.
So we have not tested our catalyst for that synthesis.
Okay,
we can
because you have carried out many optimization studies pertaining to many organic transformations. That's why I asked these particular questions. But
we have not tested that particular.
Really a nice piece of work, sir, and truly, it's a great honor to listen to you after a long time. Thank you, sir.
Thank you. Thank you.
Thank you. Now we can take a few more questions if there are any other questions from audience.
Dr. Dinesh, can I ask question to the speaker? So this is Balraman. So
yes, Dr. Balraman.
Yeah, so really, so wonderful and exciting talk, sir. Please accept my compliment. Yeah. So regarding this slide, particularly you're using a ruthenium catalyst and converting acid and amine, you are getting amide. So is it applicable for a simple acid and amine to get amide without using any activator?
Acid and amine.
Yes,
no,
exactly.
I actually, it was a very simple reaction. I should have tested it, but I never tested because I started with directly gamma levulinic acid. I never tested that, but I think it should be, because my goal was cyclization. No, so I was looking for a molecule which can cyclize.
Exactly. Yeah, no, if the reaction works, then without using any acid activator, you are converting feedstock acid to directly to
and of course,
amide.
hydrogen is required here. Huh? Let me tell you, hydrogen and autoclave and all those parts are obviously part of it.
Okay.
Without that, it will not work.
Okay, because that was
you can see the condition here: 15 bar hydrogen at 130.
Yeah, that's true.
And
This is
what you are
130 is the bath temperature, I think.
What you are talking is without that it may be difficult. We have to test it, because my goal was to prepare cyclized molecules. So naturally, I was looking for such type of substance.
Yes, I understood. But a simple acid, maybe benzoic acid.
I will test it. It's a good suggestion. I will do that.
Yeah. This is one of the dream reaction for the industrial.
Yes,
I mean, you are aware of it. That's the reason I asked. Yeah, sir. Another thing, and you have used cuprous oxide, one of your earlier slide, and for the Ullmann type coupling. Yeah. So that's very interesting reaction. So you have taken this N-nitro cycle and then coupled with the iodo compound, iodobenzene and other stuff. Yeah. So in continuation of that, on the other previous slide, I think. Yes.
This one? No.
Yes. Cuprous oxide one, sir.
No? This one?
Yes, exactly, sir. And this cuprous oxide is highly photoactive material. And can it be used, this material, just for the extension of your study for a CH bond activation using the similar strategy, like under photo redox condition?
Yes, you can try that, because copper has switchable things. No?
Yes, exactly.
That is exactly what is required there. So you can test that.
Okay, yeah. The Louis Ackerman and this group, and they work on copper-based homogeneous system, but using the photocatalytic reaction. And this seems to be very interesting thing. It shows some.
See, this work I did 6 years back. After that, I forgot about this catalyst.
Okay. And it is a wonderful system for now CH bond activation under photo redox condition using this cuprous oxide. Yeah. Okay. Yeah. Thank you, sir. Thank you, Dr. Dinesh.
Thank you, sir. Thank you very much. So, still we have
Sir,
time.
I have one question.
Yeah. Yes, please continue.
I'm Shobha from Abasab Garware College, sir. It was very nice talk, sir. Sir, I have one question. When we use these nanomaterials as a catalyst, you said that size and shape of the material definitely affects. So is it that there is a relation when we decrease the size of nano catalyst, yield of the product increases?
Yes, there is a possibility. I told you how many these surface atoms which you are getting, corners. If you get more corners, your catalyst is better.
Yes, because
and let me tell you by experience, it is not easy to do the prepare the reproducible catalysis using nanomaterials.
Okay. But with size, yield of the product increases.
Bange sir, you are mute, I think. Please unmute yourself.
Okay. Okay, now regarding the question, preparation size and shape is very important. And next point, once you achieve some method, to reproduce that, you have to ensure that again and again by reproducing the same method, you are getting same size and shape.
Okay.
Otherwise, you may end up with variable results. And that is a very important part when you are preparing the nanomaterial. Most of the time we are using homogeneous solution. We don't see those. Sometimes we precipitate them also. Centrifugation and separation is also tedious. It's not that easy what it looks like.
Okay. Thank you, sir.
Thank you very much. So if there are no more questions.
Shukla here. Sir, I have one question. Sharad
Yes,
here.
yes.
Sharad. Yes, sir.
Yeah. Yes, sir. Nice presentation. Sir, you have very good explore this platinum, this iron particle, palladium, and nickel nanoparticles, which has very good activity and selectivity for the few reaction. So did you explore these nanoparticles by supporting on like solid support like alumina, silica?
Yeah, but you lose some reactivity performance because they are supported, no? Their electronic density and all those will change.
Because that is a real challenge.
Free-from is always more active.
Yes, that is a real challenge. How will you stabilize these nanoparticles?
Otherwise, heterogeneous catalysis as such will work. Most of the heterogeneous catalysis, you will find them there in nano form.
Yes, agree. But if you can make the supporting system, then we can use in fixed bed reactor operations.
But if you are prepared to lose some reactivity, fine, you can do that.
Yes.
The activity performance will reduce. That's what I want to say.
Yeah. Thank you, sir. Thank you very much.
Sir, one general question I have, and whether this nano catalyst can be used in the kilogram scale, whether it is reproducible?
See, at least from milligram to gram level, I have checked the reproducibility. From gram level to kilogram level, I didn't. Gram level, it works. Even 100 gram, I have prepared and used it. But above that, I didn't test it because that was not my objective.
No, whether there are any reports they are using in the industry.
At least I have not observed. Even gram level reports also we will find very few.
Okay.
But let me tell you one more point in continuation of this. Today, you will find many companies who are giving you the nanomaterials in higher scales also. The only problem there is the cost is very high because they have their own proprietary methods and all that. Commercially, most of the catalysts in nanoscale are also now coming in the chemical catalog. You can directly procure them and use it. That is also another thing.
Thank you, sir. Thank you very much for detailed answer for all the questions. And it was excellent presentation. And if there are no more questions, on behalf of organizing committee and as well as on behalf of all the audience, I'd like to thank Professor B.M. Bange sir for such an excellent and nice presentation with detailed discussion on all the aspects of catalysis, nanocatalysis, and its application in organic reactions. Thank you very much, sir. It was a great pleasure to hear you after a long time. And now, without taking much of time, I would like to hand over this session to Professor Manoj Gawande, sir.
Okay. So thank you, Dinesh, for chairing this session. It was, you really organized very well. I would like to thank our first speaker, Dr. Balaraman, for your interesting talk on earth abundant metals. You really explained very well this catalyst and what is this catalyst demand. It's a really sustainable approach to use this inexpensive metal and replace this noble metal. Okay, so particularly you have focused on three metals: iron, cobalt, and nickel, and definitely they are inexpensive. And how we can use this manganese for various applications. This is also like new addition in these metals. You also explained very well this how this metal and ligand cooperation work for the various organic reactions and how these various pharmaceutical synthons can be prepared by these inexpensive metals. So thank you so much. I would like to thank Professor Bange for delivering a lecture on how to prepare these metal and metal oxides in green catalytic process. Sir, you really explained very well that various methodology, for example, this how this salt we can use in various different medium, for example, sonochemical approach or microwave approach or simple ball milling or mechanical, and we can prepare various kinds of nanomaterials from 5 nanometer to 100 nanometer. Even it is also possible that how to make them different kind of shape selective catalysis that you have shown in your the copper oxide and other environmental processes. So it's very interesting talk, sir, and thank you so much for your time and accepting our invitation. Now, within 5 minutes, we will move to our next function, validatory functions. So we will have the 5-minute break and we'll start the validatory function. So 4:15 we'll start.
Hello. Hello, Manoj sir. Yeah. Hello, Manoj sir. Can you hear me?
Yes, I can hear you. Bange sir?
Yes.
Can I ask you one question? Just wanted to ask because of
Yes,
time.
sure, you can.
Yeah, actually, you have shown that the two different material, that is the synthesis of copper nanoparticles. You have shown that cuprous as well as cupric. It is like how it is separated or it is prepared differently?
Prepared it differently.
Okay, so what is the like?
So those methods are given in the publication. There is minor difference in preparation.
Okay, okay.
You can get those.
Or maybe like the salt is used differently, cuprous chloride.
No,
or...
salt is same, method is same. The conditions are different.
Okay, okay. Yeah. And what is the interaction of this palladium with this GOIL?
Palladium is remains supported on graphene because graphene is, you know, that it's a good adsorbent. It contains lots of hydroxyl group, carboxylic acid group. So it remains on the graphene surface.
Yeah, so it is a sturdy, right? It is also
yes, it is a sturdy.
Okay. Thank you. Thank you.
Thank you.
Hello, ma'am. Ma'am, can we start? Madam, you are not audible.
व्हॅलिडिक्टरीचा सिक्वेन्स काय आहे? पहिलं सुरुवात माझीच आहे का?
नाही, पराग सर बोलणार आहेत.
हा, आधी हे करेल, रिकॅप करेल ना?
येस येस.
हा, ठीक आहे. नंतर माझं आहे.
Yes.
आणि नंतर मग भंडगे सर ऍड्रेस देतील व्हॅलिडिक्टरी. आणि मग वोट ऑफ थँक्स, राईट?
येस येस मॅम.
चालेल ना, सुरू करू शकतो.
कॅन वी स्टार्ट? ओके.
खूप छान झालं हा, मनोज. मनोज, छान झालं सगळं.
थँक्यू मॅम, थँक्यू.
लॉट ऑफ हार्ड वर्क, आय कॅन सी दॅट.
Good afternoon, ladies and gentlemen. The two-day International Conference on Nanomaterials and Sustainable Applications 2020 is now drawing to a close. I would like to take this opportunity to extend our sincere gratitude and appreciation to all of you for your invaluable contributions in making this event a great success. We hope these 2 days have been fruitful, and through a wide range of keynote speeches and discussions that were presented will help us to deal with the challenges related to the energy crisis using nanotechnology tools and sustainable methodologies. Let's welcome all the dignitaries once again. Respected Director Professor Smita Lele, Chief Guest of Valedictory Function Professor Bhange, ICT Mumbai, Convener of today's virtual international conference Professor Manoj Kawande, all distinguished speakers, professors, all respected faculty members, researchers, and my dear friends of science, technology, and innovation. Warm greetings to all of you. May I now request Dr. Parag Nemade to present a brief account of all the lectures. Over to you, sir.
You're not.
Hello. Parag.
Am I audible?
Yes, yes, you're audible, sir.
Oh. Yeah, there was some issue regarding unmute. It's a great privilege for me to summarize the proceedings of this first international conference on nanomaterials and sustainable applications. It is convened by Professor Gawande, and it's the first international event organized in our newly established fledgling ICT Marathwada campus at Jalna. This topic of sustainability and nanomaterials for catalysis and for new chemical synthesis is very relevant in modern times. And it is very relevant for educating and disseminating the advances that have happened in the drive towards sustainability, which is aided by nanotechnology. We had excellent talks by eminent international and Indian speakers with session chairs that were chaired by accomplished researchers. Our kickoff session was by our Vice Chancellor, Professor Pandit. He exhorted on applications and advances in nanotechnology and to take holistic approach towards studying the nanotechnology, including its safety aspects. Next talk was by Professor Yadav, our previous Vice Chancellor. He exhorted on necessity of chemicals for human life. He gave a wide perspective on green and sustainability engineering, stressing on hydrogen economy and use of crude and biomass, not as a fuel, but for chemicals. He also told about the beauty of chemistry and chemical engineering. It lies in the ability to manipulate matter at molecular level, and that is where our nanotechnology comes into play. This theme was further expanded by Professor Day on his talk on how to design catalysts by changing the profile of the product's form by introducing stress within the molecules, steric hindrance, or injecting electrons or removing electrons in the electronic structure of the molecular orbitals, and tailoring the products to generate hydrogen, carbon monoxide, or formic acid from carbon dioxide. Professor Paul Shettiwar work discussed on carbon dioxide conversion using dendritic nanosilica, defect engineering in nanosilica, excuse me, without use of metal ligands, use of dendritic plasmonic nanoparticles that can not be used only for performing the reactions, but also be used to harness energy. He showed how the acidity of solid aluminosilicate catalyst, amorphous catalyst, can be used for plastic recycling and improving the sustainability of our daily use products, where you not only use carbon-based fuel, but in a cyclic manner, recycle the carbon dioxide to obtain fuel back or chemicals again. In his talk on sustainable chemical synthesis through catalysis, Professor Jagadish Rajanhalli spoke extensively on approaches toward use of non-noble metal catalysts. He highlighted particularly the use of carbon ion-based catalyst for selective hydrogenation of nitro compounds, as well as directed core shell nanoparticle catalysts through metal organic framework strategies for direct amination using ammonia. Heterogeneous catalysts as following the similar strategy as homogeneous catalysts. Another aspect that was discussed by him was eliminating the use of metals for catalyzing chemical reactions. This topic was further discussed by Professor Pablo. He stressed on use of abundant or earth abundant metal for catalysts rather than use of noble metal and rare metals. We discussed how to tune shape and composition of materials for stabilization of metal nanoparticles, use of core shell nanometal catalysts for oxidation of methane emissions, use in fuel cells, etc. His passion for routes to reduce metal or to go metal free for catalysis was deeply appreciated. Next talk, Professor Maniyar discussed about sustainability through catalysis by performing reactions at mild reaction conditions or in water through the rational catalyst design by vacancy engineering, by introduction of promoters, and he demonstrated those principles for fissile fatty acid to hydrocarbon production, glycerol reforming through photocatalysis, etc. In his excellent talk, Professor Asefa discussed rational design for sustainable renewable energy systems. In today's session, Professor Selvam discussed porous materials, how the knowledge of the materials by use of structure property relationships can be used for engineering porosity, tuning pore geometry, implanting active sites for tuning the selectivity of chemical reactions, and how the zeolite-based catalysts have been instrumental in changing the selectivity of the catalysts and how they can be tuned for performing specific reactions. That particular theme was also picked up by Professor Srivastav, who also worked on stressing the importance of fouling and minimizing fouling by controlling the porosity and active sites for synthesis of petrochemicals or biochemicals. The next talk about fundamentals and practical aspects of catalysts was given by Professor Jairam, who also discussed how the principles of green chemistry can be employed in similar multiple ways toward the same reaction. For example, NONOGel addition reactions. How the role of surfactants, metallomicelles, ionic liquids can be, as well as Pickering interfacial catalysts, can be used towards sustainable synthesis, as well as synthesis in green solvents like water, etc. Professor Balraman discussed use of earth abundant metal for catalysts for activation of alcohols, CN bonds, CC bond, CN and CC bond formations for N-alkylations, use of bifunctional catalysts, as well as use of cooperative metal manganese complexes, organometallic catalysis for tuning of alcohols and his work, particularly on tuning of alcohols as alkylating agents, is truly innovative, and it is, as was the direct amination of alcohols, which is really, really important reactions for industrial synthesis. These sessions were capped off by talk by Professor Bhange on catalysis through metal oxide catalyst. Professor Bhange shared his experiences on tuning nanomaterials, their morphology through synthetic methodology, precursor control, capping agent control, and resulting in tuning of product selectivity. Methodologies were adopted for catalysts such as nickel oxide, cuprous oxide, ruthenium zirconia MCM, or hydrotalcite-based catalysis for production of biochemicals through sustainable raw materials for biorefinery concepts like use of fructose or dimethyl or use of furfural, etc. The expanse, it is often found, and one of his conclusions, which is very important that can be taken as a take-home message, is it is often found that the shape and size of nanomaterial catalyst often governs the specificity and heats. It is truly, this conference has been very, very interesting. It has been very, very informative. The expanse of the topics covered is breathtaking, as also was the detailed discussion on the finer aspects of catalyst design, directed synthesis strategies, adherence to the green chemistry principles, and sustainability. Now, I would like to yield the floor to Professor Lele for her remarks.
Thank you, sir. May I now request Professor Smita Lele to enlighten us with few words of wisdom.
Yes. Hello, everybody. My friend and colleague, Dr. Bhange, today's conference convener, Dr. Manoj Gawande, Dr. Parag Nemade, the Deputy Director, who so nicely summed up, then all the speakers and chairman and audience of this 2 days conference. It gives me an immense pleasure to once again get connected with you today. Yesterday morning, I had a brief talk with all of you, and I feel overwhelmed that I again get this opportunity to share a few of our dreams here. And as said by Dr. Parag, we are just hardly 2 years old campus, and this is our first international event which we had to conduct online mode. But I think it was very, very successful and unique in many ways. And the most striking thing which I found here, that in many, many conferences, I have seen speakers complaining that they did not get adequate time to share their work. So here, I think, Dr. Manoj, I must compliment you that you really gave 1 full hour to talk to the person who has spent decades in that field. And there was ample opportunity for the audience to interact and talk to them. And this was further flavored by chairpersons of every session. So I think we had over a dozen speakers, including chairpersons from yesterday. And really it touched A to Z of life. As we all know, chemistry touches all part. And now we are all talking of nano, soon we'll be talking of pico and even further down. And how we can really try to make this world more useful to live with minimum harm to the environment and combating the problems and having food security with increasing population. So even fuel is one very important thing. All these catalysts were focused on organic synthesis, but since I'm working in food, somewhere I can see down the line, we are trying to aim at using chemical molecules directly so that through a set of enzymes, catalytic reactions, I'm able to get bread, butter, jam as my direct output. And I don't think the day is far, and in such processes also, nanotechnology is going to play a very important role. So I'm not going to take much time, but I thought let me continue my talk of yesterday in line with our beloved new campus, ICT Mumbai's Marathwada campus, Jalna. And so I thought I will share our dream, which all of us have together seen in just 4 or 5 slides, and look for collaborations from all of you in your future. Next one. Yesterday I had shown, but I'm again showing it, that this is our formal vision statement, and we have broken it into missions of education, developing research and helping industry, and developing entrepreneurship. We have further broken it for next 5 years. Yeah, next. Yeah. So in order to do this, we really have to ensure that we are imparting the highest level of education there. And since we are only about a dozen of teachers, this new platform of e-teaching has come to our rescue, and we have access to not only Mumbai teachers, but all other teachers across the world. And we are trying to give really the highest level, and we have to maintain the same passion. And we are establishing a complete horizontal network. Our mother institute is ICT Mumbai, with 2 more arms or organs, one at Bhubaneswar, Odisha, and another one at Jalna, Marathwada. So all the teachers, all the students, and even the common people should have this, that we are all 3 in 1, 3 parts of the one great institute. We really want to have more ties with industry and government and do the cutting edge research. Yeah, next. Of course, our guiding principles, as usual, those are there even at ICT Mumbai. I've spent all my life, more than 4 decades, I've spent in ICT Mumbai, right from my student days, and we bring the same DNA and genes here of maintaining a very high level of commitment of excellence, integrity, ethics, and accountability. We want to promote collaboration. We want to have intellectually stimulating, open, responsive, and conducive environment for learning, teaching, working, and living. In all great institutes, including ICT, IIT, ICERS, we have 4 principles of learning: unlearn, relearn, and self-learn. And a lifelong learning is a mantra for every teacher, and all of us are lifelong students. At such occasions of conferences like this one really helps all of us to even continue to learn and think of new ideas, and also appreciate what has been happening across the world, and perhaps collaborate in future. Yeah, leadership is and entrepreneurship. Again, these are our 2 strengths of ICT Mumbai, and we want even ICT Jalna to grow in that direction. Next. These are the courses we already have. That is integrated masters in chemical engineering major with some chemical technology minor simultaneously for 5 years. And yesterday, our Vice Chancellor, Professor Pandit, mentioned about it, that this course is having a lot of component of industrial training, so that 4 months the students study, 4 months they go to industry, and they are hardly 18 years old, 10 plus 2 at that time, and they are directly doing subjects like analytical chemistry, and they are doing programming like Python, and they have the first batch has already been to industry twice. Then I'm very happy to share that we also started now 2 years MTech program. That is, what about those who have already graduated in those areas? They are not at 12th level. Can they come to ICT Jalna? Of course they can come. We have already admitted students for these 3 programs, and we'll be starting other programs, all the 2 years programs of chemical technology, which are there at ICT Mumbai, will start offering at 2 of campuses also. And in ICT, as mentioned even by Professor Pandit yesterday, that the first engineering PhDs pre-independence were from ICT, that is UDCT. So we always start like digging the tunnel from both sides. So we have an undergraduate strata, and we have a senior PhDs. And so keeping that culture, we already admitted more than 25 students PhD fellows in the Jalna campus. Yeah. So I just want to share the centers of excellences which we plan. The list is quite long, but I'm just giving the one which are our priority, that is water and wastewater. Particularly Marathwada area where we are situated, there is a scarcity of water, and Aurangabad is a big hub of industry for pharma and for chemical, and for Jalna is a big hub of industry. It's a steel city of Maharashtra, the recycled steel. And so there is a big problem of adequate water, drinking water, industrial water, and wastewater. So that is one of our center of excellence. We have already started some projects in that direction. Then agri, India has agri economy, but as of today, agriculture is not viewed as an industry because the kind of returns you are getting per acre per year are not worth calling it industry. So as our Prime Minister Narendra Modi has also aimed at doubling farmers' income, we in our own ways are working in that direction. And this center will be doing state-of-the-art research for lab meat, for vegetarian meat, for meat analogs, and so something which is now very popular in Western culture like vegan culture, and also what will give some more living or returns to our local agriculture farmers. We are aiming at one such center in Jalna. We have already put up proposals to appropriate authorities, and we are open for collaboration with industry also. And then the third center, again, materials. So it's not just nano, bio, novel, and sustainable, because you may have a very wonderful technology, but ultimately if it is not economically viable and if it is not sustainable, then it is not really going to make a dent on the socio-economical requirements of the country in general, country in particular, and world in general. Yeah, next. So this is, I have called it autocatalytic circular growth. We have been doing catalysis. So the most wonderful thing will be if the system generates its own funds and own requirements, just like a automobile where the car battery gets charged by using the car and not by not using the car. So that dynamo principle. So we would like to put our institute, and being the first founder director of ICT Jalna Marathwada Center, I thought from my side, with the help of all my colleagues, we have already tried to reach the critical speed and perhaps cross the critical speed, so that we continue our circular growth using all the limbs of the structure: administration, infrastructure, human resources, academics, research, as well as outreach activities, about which I talked yesterday, because personally I've been doing that as a scientist in my own life. Next. So what I would, this is my last slide, what I would appeal to all of you is please join hands with Marge, maybe as a student, as a research fellow, as faculty, as scientist, as collaborator from academics, industry from India or abroad, no geographical limit. We are looking for partners with grit. So I refer to the TED Talk by Angela Lee Duckworth. Those who have not seen it, please see it. She is also a teacher, and she has done extensive research to finding out that maybe 50 years back, people were talking of, for Toyota story, they were talking of IQ, and then they started talking of EQ. And today in 2020, people are saying that it's not just the IQ, EQ, SQ, PQ, but you need people who have passion with perseverance, and that has been named as grit. So we all have grit in my family, the extended ICT March family, and I'm looking for many more partners in near future to come and join hands with us. Thank you very much. Namaste.
Thank you, ma'am.
Thank you, ma'am. Without taking much time, may I now invite Professor Bhange, Chief Guest of Valedictory Function, to express his thoughts on this occasion.
Respected Professor Smita Lele, Director, ICT, Marathwada, Jalna Campus. Dr. Manoj Gawande, Convener for this conference. Dr. Parag Nemade, and Dr. Ritika Joshi. And all speakers, session chairs, and audience. I'm really happy to see such a scale of the conference because it's truly international conference. And that kind of topics selected are really the frontier topics in the area of catalysis, nanomaterials. Particularly the knowledge which we have gained through this conference will be really useful. We come to know all the latest development in this area. Second point, I'm not guest to this particular conference because I'm also part of ICT Mumbai Jalna campus. And I'm happy to see that how this campus has grown from zero, because initial days I was involved in just from looking for the land, space, and to such a stage. And this institute has grown up like very significantly in a short span of time. And I must congratulate Professor Lele for her excellent leadership to develop such a nice institute. And we can see that the kind of faculty members recruited there, they are really brilliant, talented faculty members. And organization of this conference itself indicate that the level at which our faculty members are there. I have seen several international conferences. It's far better. It's really good. And topics are really good. Very frontier topics like CO2, small molecules, how you can activate, how you can prepare materials, many more. And all the speakers I know, they are frontier researchers in their field. They are who's in their particular area. And they have happily agreed to give talk here, and really indicates that, yes, it is really a good one. So again, I would like to thank Dr. Manoj and his team, because behind the scene, there is a lot of work which one cannot imagine. It's not easy to prepare. It starts from scratch, looking for speakers, developing website, consider calling all the speakers, collecting all together. It's a vast task. So Manoj, I must congratulate you on having such wonderful and successful conference. And you can see the feedbacks from this audience. They are really good feedbacks, and it indicates the success of this conference. With the knowledge which we have gained through this conference, we can think over new areas on which we can work, because why we should have conference? Everything is published in literature. It is something like that. Books are there, why teachers are required? So it's not like that. Since we are interacting with the who's who in that particular field, we come to know what is happening there and what type of scope is there. And we always think how we can correlate that particular scope to our research. And from that perspective, I feel everyone here would have thought in a different way, and this can lead to a different types of new knowledge, which can lead to many breakthroughs. And that is the purpose of having conferences. Unfortunately, we couldn't meet physically, which is more better, but virtually is nothing less, because now at our convenience, we can attend, we can select the topics, we are doing our routine work as well as gaining the knowledge. And that is the biggest benefit of having virtual conferences. And I'm quite sure, even after Corona days, virtual conferences will remain to stay. And that is a big success of, or what is a big advantage of having virtual Zoom platforms or Google platforms to have such type of conferences, because at remote places, you can able to get the access to the advanced knowledge, and that is possible with virtual platforms. And you have seen that you could able to interact with all speakers. Whatever questions in your mind, you could able to express. They have given the answers what they know. So it's a really good. I'm quite sure that Professor Lele has shared her vision about the conference, which is a really nice one to see. And particularly, I like the idea of having these 3 new centers, which is very much required for that vision particularly region is agro-based economy, so center on food and makes very much sense. Materials are important when you want to do these things, so material center is also important. Water is a problem there, so water-related center is required. So it's carefully thought what type of vision this institute will have in future. So I must congratulate Professor Lele for initiating this concept of having 3 new centers there. So Manoj, I will not take much time because I'm not a guest for you. And I must say congratulate to you and your team for having such a wonderful conference. And congratulations to all speakers for sharing their knowledge and share with us. Thank you.
Thank you. Thank you, sir.
Thank you, sir. May I now request Dr. Manoj Jadhav to present the vote of thanks. Hello.
Yeah, hello. Yeah, thank you, Dr. Ritika. So good evening to all. Respected Professor Smita Lele, Director of ICT Jalna. Chief guest of this validatory function, Professor B.M. Mange. Dr. Parag Nemade, Deputy Director of ICT Jalna. Professor Manoj Gawande, the convener of conference. And our most valued invited speakers from the science fraternity and dear participants. It is my privilege to propose a vote of thanks on this occasion. I, Dr. Manoj Jadhav, on behalf of ICT Mumbai Jalna campus and the entire conference committee here together extend a very heartfelt gratitude to all the speakers from India as well as from abroad for gracing us with your important research talks, sharing your findings, opinions in the field of nanomaterials, engineering, sustainable chemistry. I must mention our deep sense of appreciation to Professor Aniruddha Pandit, Vice Chancellor of ICT Mumbai, for his support, motivation, and encouragement. I would also like to thank Professor B.M. Mange, chief guest of this function, for giving his valuable time and sharing his thought on the theme of this conference. I also wish to express my gratitude to Professor Smita Lele, the Director of ICT Mumbai Jalna campus, for her minute-to-minute guidance and support and encouraging us at every point of time. I take this opportunity to extend our most sincere thanks to all our participants from different universities, institutes, for their support, cooperation, and enthusiasm throughout during this program. An event of this dimension cannot happen overnight. It requires meticulous planning and a perfect execution. I congratulate Professor Manoj Gawande and his entire team for organizing such a beautiful virtual international conference. Congratulate, sir. In the end, I would like to say every beginning has an end, and every end is actually a new beginning of something. So I hope this is the beginning of new ideas to the researcher and a new direction to the budding researchers. Ladies and gentlemen, once again, I want to state that we are all grateful to all the speakers and participants, and I officially announce this conference is over. Thank you very much for your being a part of this virtual conference. Thank you.
Thank you.
Well done.
Thank you. Thank you, ma'am.
Well done. Well done.
Thank you.
Pat on the back.
Thank you.
Bye, Ritika.
Bye.